from Vellore Institute of Technology, Vellore. My presentation topic is about enhanced tribolotic property of dual surface modified ecoflexible polymer. Contents of the presentation includes introduction, tribolotic property enhancement, ecoflux synthesis, experimental analysis, results, inference, practical demonstration, and conclusion. Coming to the introduction part, as the world is marching into the era of Internet of Things and fifth generation wireless networks, various self-powered electronics are considered as the fundamental building blocks for the foundation of the coming industrial revolution towards a smart world. The wide distribution of self-powered electronics covers many applications ranging from industrial electronics, personal, wearable, implantable, and to a sustainable system in every corner of our life. With the development trends of electronic devices in miniaturization, lightweight, and portability, a sustainable power supply solution is needed to meet the requirement of the upcoming intelligent world, where the traditional batteries are facing many challenges due to their limited lifetime, environmental impact, and periodical replacement. In order to overcome such drawbacks of traditional batteries, the best solution is to design devices that can harvest energy from their surroundings. As a matter of fact, mechanical energy is one of the most widespread and abundant energies in the environment. Making mechanical to electrical energy conversion is a promising technique for powering small electronics. Many mechanisms for energy harvesting have been already developed, including piezoelectric, electrostatic, pyroelectric, electromagnetic, and so on. However, those technologies normally have complicated structures and they operate under high frequency stimuli with low transmission efficiency and low voltage output in the low frequency domain. Uh, these limitations dramatically constrains their potential applications in the intelligent world. To overcome these disadvantages, the tribolectric nano generator or TANG was first invented by Zhongling Guan in 2012 and has attracted worldwide research interest and underwent significant developments, becoming a promising technology in becoming a promising technology in energy harvesting and especially in nano energy and nano systems. The working mechanism of tribolectric nano generator or TEN comes from the coupling of triboelectrification effect and electrostatic induction effect. When two dissimilar tribolectric materials come in contact and separated from one another, electrons will flow back and forth through the external circuit to keep balance because of the instantaneous voltage difference. For better understanding, I will play this video. Here, the triboelectrification is associated with the charge transfer uh, between the two different dielectric materials. Here, I mentioned in this by color triboelectric material 1 and 2. These are two dissimilar dielectric materials, and this orange colored one is the two electrodes. The triboelectrification effect associated with the charge transfer between the two different dielectric materials during mechanical contact. Material which gain charges becomes negatively charged, and those lose charges becomes positively charged. And electrostatic induction happens. Induction happens when two surfaces are separated. Transferred charges on the contacting surface of the both materials induce accumulation of opposite charges on the electrodes that are attached to the materials. The transferred charges on the contacting surfaces create an electrical potential difference between the two electrodes, and this causes electron to flow in an external circuit connecting the two electrodes in order to attain an equilibrium. So as shown in the video, a periodical voltage or output can thus be generated across the materials as a result of the periodic and relative motion between the two materials. Normally, the working mechanism of triboelectric nanogenerators can be divided into four fundamental modes: vertical contact separation mode, sliding mode, single electrode mode, and freestanding mode. For time being, I am skipping this explanation on these modes. There are many factors need to be considered while fabricating triboelectric devices. Their structural design, selective material, fabrication technique, surface modification. Out of that, the selection of constituent material is the most important one. Electrical performance depends, or triboelectric performance depends on many factors of materials like the chemical properties, the mechanical properties, dielectricity, charge density, contact surface area, surface roughness, stiffness, and flexibility. Actually, in this study, I tried to enhance charge density and flexibility of ecoflexible polymer material by modifying its surface properties. I have synthesized the three types of ecoflexible polymers with the different surface properties, which are surface modified ecoflex film. Then secondly, I synthesized the ecoflex sponge, and finally, I synthesized surface modified ecoflex sponge. Coming to the synthesis part, initially I synthesized a thin film of Ecoflex having surface roughness. For that, I have chosen Ecoflex 0030 preparation kit containing two liquid bottles A and B, where A is the monomer and B is the elastomer with the platinum catalyst curing agent. Both are taken in 1:1 ratio, then mechanically stirred for 1 minute and poured on a mold and left to cure on hot air dryer for 5 minutes. A piece of anti-slip plastic kitchen sheet with the micropyramidal structures fixed on an acrylic sheet was taken as the mold for getting surface reference. The coiled film was then peeled off from the mold to get a solid, flexible, and stretchable Ecoflex rubber film with preferred surface modifications. A thin copper electrode was also attached, was coated on the bottom side of the surface modified Ecoflex thin film or SME film. Secondly, I synthesized the Ecoflex sponge. For that, I mixed sugar granules with the Ecoflex solution, stirred using mechanical stirrer for 2 minutes, poured on into a petri dish, and dried using hot air for 10 minutes at 60 degrees Celsius. After cured, the solidified Ecoflex sugar compound was taken from the petri dish and put it into a beaker having water and allowed to dissolve sugar granules in water. After 4 hours, it was taken out from the water and squeezed well and dried using a hot air dryer. The obtained Ecoflex was highly porous like a sponge. A thin copper electrode was also attached to the bottom of this Ecoflex sponge. And finally, I synthesized the Ecoflex sponge with additional surface roughness. Uh, For that, after pouring Ecoflex sugar compound into batteries, a piece of anti-slip plastic sheet was placed on the top of that, as shown in figure C. A uniformly distributed small weight was inserted on top of the anti-slip sheet to spread the effect of mold evenly on the under surface of the Ecoflex and allowed to dry in hot air for 15 minutes. After cured, removed the mold and taken out the solidified Ecoflex sugar compound from the petri dish and followed the same above steps. The obtained structure was also similar to the second one, which is the ecoflex sponge, but the additional feature is that it has additional surface roughness on its top due to the presence of the anti-slip kitchen sheet or the mold. These are my synthesis parts. And coming to the experimental analysis, for testing the triboletic performance of these three synthesized ecoflexible polymers materials, a contact and separation mode arrangement was made using Ecoflex aluminum, and copper on a linear motor as shown in the figure. This is the arrangement. Ecoflex is the negative triboletic material, and aluminum act as a positive material, positive dielectric material, and the copper is the bottom electrode, and aluminum also act as one top electrode. Analysis was carried out for all the three synthesized decomplexing materials in two ways. That is, with air gap between triboletic material and without air gap between the dielectric materials. In two ways, I conducted the analysis with and without the air gap between the materials. Materials and electron dimensions were fixed to 3 centimeter along length and breadth. Results show that the surface modified ecoflex sponge or third one has more triboelectric properties than the previous two ecoflex materials. The maximum output voltage with an air gap between the materials I have obtained as 70.1 volt, and a short circuit current obtained maximum of 7.1 microampere at the same at the 4.5 hertz operating frequency. And in the case of analysis without air gap, here also surface modified ecoflex sponge exhibited higher performance. It has obtained a maximum open circuit voltage of 19.4 volt and a short circuit current of 1.1 microampere for the same operating frequency of 4.5 hertz. Actually, the pore structured surfaces possesses superior charge generation capabilities compared to the smooth surface of the same material due to the enhanced contact and friction areas. Actually, the gap between triboletic materials while preparing contact and separation mode triboletic nanogenerators is an important considerable parameter. But during my test without air gap, also I obtained some voltages and currents, and I understood that this is also due to the internal porous structures of the ecoflex film. Flexibility, stretchability, and twistability tests also of these three ecoflex materials were also carried out as shown in the figure, and analyzed that the surface modified ecoflex sponge has more flexibility, stretchability, and twistability also than the other surface modified film or ecoflex sponge. Here, surface modified ecoflex sponge has 180 degree. I obtained 180 degree of flexibility, 100% of stretchability, and 360 degree twistability. The high performance of dual surface modified ecoflex sponge can be utilized for making wearable and portable nano generators or nano sensor devices. Based on the results, the the triboletic output performance of triboletic nanogenerators can be effectively improved by introducing porous structures on the materials and by making surface roughness. Because porous materials can increase the contact area upon compressing and can generate more charges and more output power. In this work, the surface modified porous ecoflex or SL sponge showed a significantly higher performance than surface modified film and ecoflex sponge. To demonstrate the practical application of the higher performed surface modified ecoflex sponge as an energy harvester, a fully packed water resistive oval shaped SMES tank was fabricated, and it used as an energy source to turn on 42 LEDs and to drive a Lumex LCD display. That's about my work. coming to the conclusion part, here I have synthesized three different e-complex materials with different surface roughnesses, and the reliability performance were conducted in two modes, with and without air gap between the diabatic materials. And the results showed that the SME surface modified e-complex sponge with additional surface roughness has higher regulated performance, and it is analyzed that it's due to the increased porosity and additional surface roughness. For conducting a practical demonstration, I fabricated one oval-shaped SMES stability NAM generator to demonstrate the practical application. And that device used to source 42 LUTs and drive an Lumex LCD display. So the porous materials with additional surface roughness provide new insights to fabricate efficient energy harvesting and self-powered devices. That's about the conclusion, and these are my reference. Thank you.
Thank you so much, Dr. Syed Abdul Basit, for a wonderful talk. I would like to request the participants to ask questions if they have any from the speaker. If there is any question, you can ask. The speaker is here to clarify. I think there is no question. Thank you so much, Dr. Basit. Now I
Okay.
would like to invite our next speaker, who is Dr. Jagriti Behel. Dr. Jagriti, are you here?
Dr. Isat, we have been reported that Jagrati won't be attending the conference, so we can go to the next person.
Okay, okay. Thank you,
Kamala
madam.
Kannan Kailas.
Okay, okay. So I would like to invite Dr. Kamla Kannan Kalasam. He is from the Institute of Nanoscience and Technology, Knowledge City, Mohali, Punjab. So, Dr. Kanna Kannan, you can start your talk. You are not audible, sir.
Yeah, can you hear me now?
Yes, yes, we can
Yeah,
hear you.
thank you, Dr. Ahmad, for the introduction, actually. So let me share the slides. I thank the organizers for providing the opportunity to present our results there. So I am Dr. Kamala Kannan from, just a second. Whether the slides are visible, ma'am?
Yes, sir, it's coming. Yes, sir. Yes,
Yeah,
sir,
okay.
it is visible.
Full screen. Okay, all right. Yeah. Okay. Thank you. Thank you for organizers for providing the opportunity. So I think let's start the talk. So you might have wondered what is the title, like solar fuels from sunlight, realizing Siamesian's dream. I will come to that. Who is Siamesians? I think probably some of you know it if you're working in energy or hydrogen production or sunlight reactions. So solar fuels, of course, you can imagine photocatalysis, of course, to produce hydrogen and fine chemicals. This is the base of my talk. So for next 20 minutes, then I will provide the talk on the topic. And before that, this is our group, is Advanced Functional Nanomaterials. This Institute of Nanoscience and Technology, probably not many known because this is the newest institute, started 8 years back in Mohali, Punjab. It's from a DST institute. So my group is working on energy and environment materials actually. So here we use do water splitting, biomass valorization to fine chemicals, so porous materials and CO2 conversion to chemicals and sensings. So today I will give a talk on photocatalysis to produce hydrogen peroxide, or biomass oxidation to fine chemicals by using carbonated as a photocatalyst. So that is the flavor of the talk. So I will divide it into 2-3 parts where I give some introduction. There's a lot of students, I'm sure. So I will give you some overview, then I will get into the talk. So why sunlight, of course, and yeah, why hydrogen, why hydrogen peroxide, why biomass to use to find chemicals, and why carbon nitrides? Because this is an organic semiconductor, first organic semiconductor, heterogeneous semiconductor to produce hydrogen peroxide, and it's used in every field actually, from biology to physics, everywhere. It's being used. So let me start the talk. There are visionaries, who give a lot of ideas and thoughts they share, so that scientists to develop a lot of processes. One of the guys here is Julius Verne, and he is one of the novelists. He's a novelist. Okay, he's not a scientist. From Austria, he wrote a novel as The Mysterious Island in 1875, where he proclaimed water will be the coal of the future. So what he mean is, of course, it contains hydrogen, water, hydrogen, oxygen. So the hydrogen will be the molecule of the future, he said. It's a future energy source. Yeah, that up to the moment now, of course, that's the moment came now. So another guy is called Shyameshan, which is in the title. Who is he? He's an Italian scientist from the Bologna University. Giacomo Shyameshan, his name is. He's one of the scientists who was nominated for Nobel Prize 14 times. Unfortunately, he couldn't get it. And the thing is, he did reactions in sunlight in his balcony of the lab in Bologna. Many reactions, and he characterized and then even complicated molecules. Even at the time, you can imagine, 1900 starting. So he used the methods available to characterize the compounds. Where you can see here the article, which is in Science, that is the photochemistry of the future. So he's in father of photochemistry, usually people say it, organic photochemistry usually. And this article, everybody should read it. And you can see the lab here, and Shyameshan standing with another scientist who carry out a lot of reactions using a Erlenmeyer flask and other things in the balcony. You can see it. So many reactions. Anyway, so I will not get into it. What does that mean now? So use sunlight to produce energy in the form of hydrogen, or then you can convert to electricity by using fuel cells. These are the ideas. So let me show one slide of what Shyameshan did that you will cherish it. So he used the complicated molecules like also between glycol and acetone to form menthone, then to isogetanol. So many of the compounds, these are the compounds he produced, and he not even did the reactions in the lab, but he also calculated how much energy is required to for example, when compared to coal, how much is the solar energy needed to produce energy. For example, the one thing I will show you is the sunlight falling on Sahara Desert per day is equal to 6 billion tons of the 6-year requirement of electricity for the Europe and America together. So you can imagine. So at the time he did all these calculations. I mean, this is really an forcing scientist, and now some of the results are picked up in real sunlight. Okay, it's not just solar driven. I mean, it's really natural sunlight reactions. Anyway, why hydrogen? So hydrogen, of course, it is have the specific energy higher than when compared to diesel or petrol. I'm just comparing with the energy sources which are available now or which are currently used in large scale. You can see the unit. You can see the kilowatt hour per gram. You can see it's about 40, and then diesel and natural gas, you can see the values is supposed 3 times higher for hydrogen, and when compared to, of course, lithium and lead acid is far away 40 times more here. So that is the beauty of the hydrogen. Of course, obviously it production at the moment the industries are producing it as a byproduct, and of course we can do electrolysis process or photoelectrochemistry or photocatalysis. So which I'm going to talk about photocatalysis, which is one of the most toughest process to produce hydrogen. So obviously there are a lot of research going on anyway. So you can see how much metric ton of hydrogen is produced, and it when we produce hydrogen of then obviously you produce more CO2 than hydrogen. So that is the values you can see here. So obviously that is one of the biggest story. So there are different type of hydrogen, blue hydrogen, green hydrogen, and gray hydrogen, and 1 or 2 more there. But of course, at the moment, people are considered, and blue hydrogen or green hydrogen is, of course, is the future, which you limit your greenhouse gas emissions. Anyway, that I'm not going to go in detail. So then I'll share what is photocatalysis. Of course, photocatalysis is the process you can also use it to produce hydrogen. How? Of course, you know it in semiconductor. For example, if you take have conduction band and valence band, and when you shine the light, the electrons get jumps to the conduction band. When the exciton gets separated, so the holes will stay in the valence band, and the electrons will in the conduction band. Then you can use the electrons to reduce water to hydrogen. And in the valence band, you can oxidize water to produce oxygen. Okay, so it means overall water splitting, right? But that is not so easy, because there are only few catalysts that are available to do the job. So mostly people, most of the almost 99% people concentrated on half reactions, whether to produce hydrogen or oxygen. So in our work, we produce hydrogen and chemicals. That I will say you why, and you can see that before getting into it, you can see what is the this is one of an endothermic process. You need 237 kilojoule per mole of energy to split the water. So that's why semiconductor is used. And if you say in potential way, it's about 1.23 electron volt. Okay, this is the potential you need to split water. Okay, if you want to do electrolysis, of course, you want to apply this potential and split the water. If you use photocatalysis, of course, you need to you have the conduction band and valence band, which should match your reduction potential, oxidation potentials to produce hydrogen and oxygen. Okay, so this you can see here. This is the cartoon we show it, and then so okay. So all right. So you produce hydrogen. So what? So of course, the storage at the moment. The storage is the biggest challenge. How to use the hydrogen purity. Of course, that is not really a bigger story, but main thing is the storage. How to store, and then, for example, fit it in a car or big vehicles. At the moment, of course, people are using it in the form of cylinders, but still, the explosion problem, all these things, because there are a lot of worries there, right? Of course, research are going on. Many companies are doing it, and some are available. You can refill hydrogen, and you can, for example, 1 kilogram hydrogen, if you fuel it, and I think 250 kilometers you can run. But of course, stations and storage stations, all these things there. Anyway, so the thing is a gas. Of course, to liquefy, there's a lot of cost involved, and this is the problem. And of course, when you want to use hydrogen directly, you can't use it, right? You need to send it to fuel cell, then you produce electricity, then you run the car, right? That is the way to do it. So it means additional cost, because it in the, for example, proton exchange membranes, fuel cells. The electrodes are made up of platinum and activated carbons, which is really needs a lot of cost actually. Anyway, and the Nephron membrane, obviously, I don't need to say it. So obviously there are challenges there by using hydrogen. So what is the another source is the hydrogen peroxide. It is one of the heavily produced chemical in the world, because it's one of the best oxidant. It everywhere you use it. So it is usually produced by anthraquinone process. Okay, it means still now this is the 99% that people producing by using anthraquinone process, which is really a lot of CO2 emitting process, and a lot of the catalyst costly, and many things there actually. So the anthraquinone process, but it's a well-known process, obviously. So if you use hydrogen peroxide as a fuel, whether it have a comparable energy density like hydrogen peroxide, yes, it is almost, the open circuit voltage, you can see it is about 1.09, and the energy density is it's almost, a little less, more than a half, 60% or so. You can imply as hydrogen peroxide, in the form of fuel cells also people are doing, and then by doing different other processes, you can generate energy. So then why biomass? So I told you biomass is the, it after the biomass is the new form of, from the plant waste, whatever the wood waste or plant leaf, anything. They're made up of, there's the plants, they're usually made up of lignin, cellulose, and hemicellulose. This is the constituent of any plant or leaf. Of course, the constituent vary depend upon the trees or whatever the leaves or other things. So these are the main constituents. Of course, if you take out cellulose, for example, and lignin, also one of the upcoming sector for the chemical industry. For example, the oil sources, you know it, it's our it's depleting, and probably it will stay for more than 100 days or 200 days for sure. But still, we need to find the new renewable energy sources. So converting lignin or cellulose or hemicellulose to fine chemicals are very most important, because our chemicals are coming from oil industry right now. So any polymer, anything you fuel, everything is from there, from the fossil sources, oil sources. So the one of the platform chemical here is called HMF, which is the holy grail for these biomass compounds, where you can produce about thousands of chemicals from using the HMF. HMF is called hydroxymethylfurfural. It's a furan ring. You can see it with an alkylic group and then aldehyde groups. Okay, so this is called HMF. This is the platform chemical, where you can see it here. You can produce so many chemicals. From there, you can go to anything, many things. From nylon to any synthesis. Actually, the uses, you can see it. Where all is used, polymers, plastics, everything you can produce by using this chemical. Anyway, so now let's come to I told you hydrogen peroxide, why important, and biomass, why you need to have fine chemicals from biomass. So how to do it, which is the photocatalyst we use here. It's a carbon nitride. I think everybody probably know it by the name C3N4, GC3N4, people say it. But of course, it's not C3N4 because there are a lot of hydrogen left, actually 1 or 2 8% hydrogen left. So why is it really 1 or 2% matters? Yes, it matters because these are the defects. You know it in metal oxides. So always we say defect sites and what is the defect sites and how it helps in the reactions, right? So I hope everybody hearing. If any, please interrupt, please. So this is the carbon nitride scheme, where you can use urea or diazynamide or melamine, which are very cheap. And then if you put it in the furnace and heat it to high temperature, then you produce carbon nitride. So it's very easy synthesis, actually. Okay, it's a nice yellow powder. You can see it. It is a nice semiconductor and visible light absorbing. You can see it from the color itself. Then you can see you might have carbon nitride as a photocatalyst is started from 2009 onwards. Okay, so you might have asked, is the newest compound? No, not really, because it is one of the second oldest compound after urea, discovered by the scientist, one of the scientists who worked on this is called Liebig in 1834. He published just give some name like about some nitrogen compounds. So he produced melum and this yellow color powders, but he didn't name it at the time. So at the time itself, they characterized a bit. Okay. All right. So the carbon nitride produced here is how much is the surface area? You know it. If you want to do catalysis, you need to have a high surface area to have a high activity, right? This is the usual trend, and this is usually holds, right? So then the carbon nitride, whatever it produced here, is having surface area about 10 meters square per gram. Okay. So how to increase the surface area? You can use different type of templating. So I think I'll rush it up because already done more than 10 minutes over. So you can use template methods to produce porosity so that you can have high surface area. So what are the templates? You can see it actually. So I don't want to get into it. So our idea used to use the carbon nitride here. You can see this the band energy diagram. As I have a conduction band and valence band, which you can see here. H plus H2 or H2O oxygen, you can see it, which is written there. It is an reduction potential, oxidation potential to achieve the reduction and oxidation. You see here in the conduction band, you can see the protons are reduced to hydrogen from the water, and in the valence band, we don't produce oxygen, but we add some chemical which will take up the holes and oxidize. So it means if you take an alcohol, then it oxidizes to aldehyde or ketone. So these are carboxylic acid. This is our idea by using biomass substrates. So this is the good strategy where you can produce hydrogen at the same time and also fine chemicals at the same time. These are very important. Why? Because for industrial processes, we should not there's a sustainable reactions, and then of course the economy is the most important thing. Where you can produce different chemicals, which I told you before. We used, these are the chemicals which are listed here. We try to utilize it to produce different chemicals, and let's see how much we achieve. Let's get to the first project where we used the carbon nitride, which is porous. I told you we use template method to produce porosity, where you can see here where we use directly HMF to produce DFF as oxidation process, and in the reduction process we use produce hydrogen. Okay, so here you can see with the increasing time we produce amount of hydrogen is increased. You can see around 48 hours we were able to achieve around almost a milliliter of hydrogen. Is not too high, of course, when you see it because it's a simultaneous process. Okay, it's not half reaction. We are doing both reduction and oxidation. So in oxidation part, what happens? You see the HMF is converted to DFF. It means oxidized from oxidized, and you can see the graph there. With the time, of course, it's increasing, but we're able to achieve only around 40% conversion. And the selectivity is the only one chemical you can produce, HMF to DFF. The selectivity is very, very important in organic reactions. Everybody know it, I'm sure, who do catalysis. So that is the good thing with here. And we're able to achieve the light to fuel efficiency is called LFE. In natural sunlight, is about 0.15 in sunlight. Okay, the whatever the graphs here showed is all from the lab, of course. But of course, we did sunlight reactions. I will show you what is the efficiency when compared to the lab when we use the solar simulator. Here, the good thing is the HMF. I told you can produce hundreds and thousands of chemicals, right? You can go through any path route. Okay, so here the good thing is be able to produce only just one chemical selectively, so DFF, and you can also produce to the other chemicals like carboxylic acids, like furan dicarboxylic acid, which are main compounds. So where if you do tune the band gap, then you can produce these compounds. So then we check with the stability cycles. We run four reactions, and of course there's a little bit decrease in activity. Then we checked why there's a decrease in activity. The surface area is not too much low, but the platinum is started leaching. Okay, so we did by photodeposition process the platinum, which is not the really effective way. We need to immobilize it on the catalyst very well. So that is the reason for the lower activity we think. And then of course we did it in sunlight, the reactions, and we get only half of the hydrogen amount produced in the lab. Is about 2000 there, and it's about 1000 micromole per gram. And DFF yield is even less, it's 7.2. Of course, it's very low. But of course, this is the way to start, sunlight reactions in sunlight. So of course, by utilizing this, we started developing a big reactor, not just in a vessel. In INST, we made on 1 meter square per reactor, which is one of the DST nanomission project, where what we did, we shine the light and be able to produce. You can see the sunlight intensity with time, and it is the date we did it in last year July. We did it almost a year back, and you can see the temperature is almost around 35 degree. It's not too high in like May or April anyway. So then we able to produce around 760 milliliter of hydrogen. The catalyst we used on the coated on the substrate is about on the plate is about 15 gram. Where we also used 3% platinum. Of course, we need a co-catalyst, just organic photocatalyst, which is not do the job. Of course, I will show you some, maybe not now, but we can also use nickel, and you can also use metal free to make different reactions. Not for hydrogen, of course, not possible without platinum to produce, or nickel. But nickel, if you use them, there's an 5 or 6 times decrease in amount of hydrogen produced. Okay, so what we achieve here is in 8 hours we run the reaction and we able to produce around 6 liters of hydrogen. So how do you calculate the efficiency, which is called STH, where is it about 0.4 to 0.6. So what does it value mean? See, the STH is if above around 5, then it's in commercial process. Okay, so we able to achieve around 0.8 or so at the moment, but of course it's well below, but still we are in good way to produce hydrogen with if you do some chemical engineering to different coating and layers, then of course we can improve it, or a different catalyst that we are working on it now. And you can see the different part of the reactor sites which we put it in sunlight and do the reactions. Okay, so at the last project I will discuss about hydrogen peroxide production, which I told you before, and also we also do here biomass oxidation. All right, so here we use the oxygen linked carbon nitride. So I sorry, I didn't show the carbon structure very closely, and you can see here now it is in heptazine ring. You can see C6N7 ring. I think hopefully you can see it. Yeah, maybe you can see here, and the right hand side you can see in the top. It is in the C6N7 nucleus. Okay, usually they connected by nitrogen. I will show you. Think, sorry, I will just show you the structures. It's very important. Sorry, I didn't explain it. Yes, you can see here. This is the carbonate structure. It's a polymer. I told you, right? It's a polymeric produced from the urea. You can see it is an C6N7. It's called heptazine. 7 nitrogens there, so it's called heptazine, azine. So for nitrogen. So they're linked by nitrogen. If you see carefully, NH, one ring, the 3-member ring connected by another ring by NH. If it's the other H also can react to form tertiary nitrogen or secondary nitrogen. In the end, you will get always polymer. You know it. Always you have terminal groups, which is called NH2 groups. So it means you have NH2 groups, NH groups, and N groups. That's why the hydrogen coming. Always, I told you there are 1 to 8% of hydrogen left in the carbon nitride because of this hydrogen. Okay. So, but what we did, we replaced in this what we replaced the nitrogen, which are connecting bridging nitrogen with oxygen. You can see here this below structure. By how to do that, and a lot of reports there by they use different methods, but we used an really precursor which only give oxygen in the bridging positions. It means to reduce your defects. So these compounds, I'm just rushing up. Ma'am, have her time? How many minutes more? Hello? Hello?
Sir, you have time, 3 more minutes to complete
Okay.
your
All
presentation.
right. Thank you. Sorry. Yeah, just so yeah, hopefully you see that. So I will just try to finish it. So here we produce hydrogen peroxide, and here you can see we use different solvents, as a sacrificial agent. I will tell you why. And then we able to achieve more hydrogen peroxide production with the IPA, I mean isopropyl alcohol. You can see it's in millimoles. This is a really good value. In 24 hours, we able to produce around 6.5 millimoles. And we also did some scavenger studies. It means to know which species is responsible for producing hydrogen peroxide. Okay, so then different cycles we did. It is the reaction was perfect. We able to produce hydrogen peroxide using isopropyl alcohol. So it means the isopropyl alcohol, what it will do, it will take the holes and it also produce acetone. So you produce hydrogen peroxide and also acetone at the same time. So we always balance the reactions. Okay, so use the electrons to produce hydrogen peroxide. It is called 2-electron reduction process. Okay, and then you produce acetone. And what we did also within sunlight, that I don't want to get into it. Let me see. This is the biomass substrates we used. HMF or DFF, you can see it, and be able to get the oxidized product. Yeah, be able to achieve, and which is it's not too high, but of course this is a really promising value. Is about 76 micromole per gram of compounds. And of course, the good thing is in sunlight we able to get around the same activity, and it's really the DFF, the HMF to DFF. I mean, the oxidized biomass compound, we able to get 15% yield. So it is one of the highest actually. And this really the sunlight reactions is promising for the hydrogen peroxide production actually. And you can see the profile, how much is produced in sunlight. And this is the table where we can compare our work with the other benchmark studies.
Dr. Kamala Kannan,
Yes, ma'am.
I would like to request you to please wind up.
Yes, ma'am. That's finished conclusion. Yes.
Okay,
So
thank
this,
you.
yeah. So we showed both hydrogen peroxide and DFF yield, good yield. So like in the conclusion, I will just hope it's a short time, but still we able to hope you got the message. So we use carbonated as a catalyst, organic semiconductor, to produce hydrogen and biomass compounds like simultaneous oxidation and reduction to produce hydrogen and fine chemicals. And next I showed you the big reactor, what we produce to produce a lot of hydrogen. And in the third work, I showed oxygen linked carbon nitride to produce hydrogen peroxide and fine chemicals. So hope, yeah, this research will go on more to produce a lot of sun fuels. And I thank my group. And for the, of course, without them, obviously they did all the research to get the results which I'm presenting now. So the funding agencies, And I thank you all for your kind attention.
Thank you so much, Dr. Kamla Kannan,
Yeah,
for a
thank you.
wonderful talk. It was really an interesting lecture and a
Thank you.
very interesting work which you are doing. Thank you
Thank you.
so much. I would like to request the audience if there are any questions from Dr. Kamla Kannan. If anybody has any query, they can ask. I think there is no query,
Thank you.
Dr. Kamla Kannan. You explained everything so well. Thank
Thank
you
you.
so much. Thank
Thank
you.
you so much. Yeah, thank you all. Yeah, thank you, ma'am. Yeah, thank you.
So we can move on to our next speaker of today's session, Dr. Lakhya Jyoti Bothakar.
Yes.
Is he here,
Yeah, I'm
the
here.
speaker? Yeah.
Shall I
He
start?
is from Department of Chemistry, Nagaon College, Assam. And the topic of his talk is graphene functionalized carbon nanotubes composite for the fabrication of supercapacitor electrode. So, Dr.
Excuse me,
Lakhya,
ma'am.
please.
Dr. Kamala Kannan, can you please stop the presentation? Okay, thank you.
Yes, Dr. Lakhya. Now share your screen, please.
Yeah, 1 minute, please.
Yes, sure.
Is it visible?
Yes, yes. It is visible, sir?
Okay, thank you. So, good morning, everyone. I'm Dr. Rakhyajyoti Borthakur from the Department of Chemistry, Nagaon College, that is situated in the northeast Assam. So, my topic for today's discussion is graphene functionalized carbon nanotube composite for the fabrication of supercapacitor electrode. So as we all know that fossil fuel feedstocks are declining and we are having many environmental issues. So development of renewable and sustainable energy devices has attained much attention in recent time. And among these various devices, batteries, chargeable batteries, fuel cells, supercapacitors, etc., has potential to be replaced, that they have the potential to replace fossil fuel and other, that is renewable, non-renewable device energy. And in this aspect, supercapacitors, they are very promising because they have high specific capacitance, high power density, they have fast charge discharge capability, they have long life cycle, lightweight, tiny volume, and many more advantages. So the idea of supercapacitor was first put forwarded by Baker in 1957. And if we try to define supercapacitor, we should say they are energy storage devices with much higher capacitance value. And in comparison to conventional supercapacitors, in conventional capacitors, supercapacitors have nearly 10 to 100 times more energy storing capability. So based on the storage mechanism, that is how energy is stored, supercapacitors are of two types, basically are of two types. One is electrical double layer capacitor, that is EDLC, and in other case it is pseudo capacitors. So in electrical double layer capacitors, what happens? We have two porous electrodes, that is one positive electrode and one negative electrode, separated by a separator, that is a dielectric medium, and the electrolyte is soaked in that dielectric medium. So when we apply voltage, charge is developed on the electrode surface. That is, this is because oppositely charged ions move to opposite electrodes, and because of this directional movement of ions, we get current. Energy is stored in this way. And in pseudocapacitors, pseudocapacitors mainly consist of electrodes having redox active materials, and the capacitance arises from the first and reversible Faraday reactions at the surface that involves passage of charge across the double layer. So in pseudo-capacitors, the charge discharge process is not controlled by diffusion and no phase transformation occurs on the active electrode material. Whereas in EDLC, that is electrical double layer capacitors, charge discharge mechanism is controlled by diffusion rate. So our emphasis is on development of EDLC, electrical double layer capacitors, and in EDLC, the active material that is used for electrode fabrication is of immense importance. The active material should have good pore size, good surface area, and for that, development of porous and having larger surface area active material is a major research concern in supercapacitor field. So if we look at the literature, we will find many nanomaterials like metal oxides, metal disulfogenides, carbon nanotubes, carbon dots, quantum dots, and their various composites have been extensively used as electrode material for electrochemical supercapacitors. And among these materials, graphene, in this last decade, graphene, which is a 2D, as you all know, it's a wonder material, has been getting much importance as an electrode material for supercapacitor electrodes. So why graphene? Graphene has many advantages. We all know about this, that they have tunable band gap, they are highly conducting in nature, they have large surface to volume ratio. This factor is very much important, very much interesting for electrode point of view, because we need large surface area to store energy. They have excellent thermal, electrical, and mechanical properties. Their theoretical specific capacitance value is as high as 526 Faraday per gram. Because of these interesting features, graphene is extensively used as a active electrode material for supercapacitor electrodes. However, pristine graphene has some limitations. The main limitation is that graphene, as we all know, they are having numerous number of nano layers, nano sheets, and during the fabrication of electrode process, that is during electrode fabrication process, these nano layers has a tendency to restack. That is, they undergo pi or van der Waals interaction and they form irreversible agglomerates. And because of this restacking, the overall surface area of graphene decreases. And due to the decrease of this surface area, the diffusion of ions through these layers becomes somewhat hindered, and this results lowering of electrochemical performance. So using pristine graphene as electrode material is not encouraging. So to address this problem, graphene is often combined with various nanomaterials to form composite. And among these heavy metals, metal oxides, metal disulfogenides, etc. are used to solve this restacking problem. So here the main target is to achieve high surface area and high specific capacitance value. However, when we are using metal, there is always a cost concern, as well as there is always a probability, there is a chance of creating toxicity, or there may be some environmental issues. So it is better if we can use other carbon materials as a companion of graphene to form composites. And in this respect also many materials has been tried. And even though a lot of research is going on in this field, yet we are not being able to achieve 526, that is the theoretical specific capacitance value of graphene we combined with other carbon materials. And carbon nanotubes are often combined with graphene to form this kind of electrode materials. So with this motivation, what we are presenting here today is that we are preparing two composites of graphene and carbon nanotube, And in one case, carbon nanotube is functionalized with carboxylic acid functionality, and in other case, the carbon nanotubes are functionalized with amine functionalities, and it is believed that due to the presence of this ionizable hydrophilic group on the surface of the carbon nanotubes, it will improve their dispersibility, their solubility, and interfacial bonding. And this will result the resultant composites will have better electrical performance. So now directly moving to the experimental part. First, we will be dealing with how we have functionalized carbon nanotube. So for functionalization of carbon nanotube with carboxylic acid functionality, we have treated carbon nanotubes with sulfuric acid and nitric acid mixer and heated it. And here you can see we are introducing this carboxylic acid functionalities. So what happens, addition of the acid to the pristine carbon nanotubes leads to the oxidative etching along the side walls of the carbon nanotubes, which in turn leads to the formation of functional groups at the defect sites, as well as opening of the tube caps. And for amine functionalization, we treated carbon nanotube with hydrogen hydrate in a medium of sodium nitrate and sulfuric acid and heated at 60 degrees Celsius for 1 hour. And this way we have introduced amine functionalized groups at the surface of the carbon nanotubes. Next, we synthesized graphene by modified Hammer's method. As you can see in the diagram, we used sulfuric acid, we added graphite and phosphoric acid to sulfuric acid, and this way by addition of water and hydrogen peroxide, maintaining the temperature within 0 to 5 degrees Celsius using ice bath, we are getting graphene. So this is the graphite. When modified Hammer's method is treated, this way we produce graphene oxide. And we have prepared 2 sets of composite using graphene and this functionalized carbon nanotubes, as I have already mentioned. One is carbon nanotube functionalized carboxylic acid, and the other with carbon nanotube functionalized with amine. So this is a schematic representation. I am symbolically showing only functionalized carbon nanotubes with acid functionalities. Here we can see when graphite is subjected to modified Hammer's method, we initially get graphene oxide, and during the drying process, this nanosheets has a normal tendency to restack. So when you are using this restacked graphene oxide and forming composites of functionalized carbon nanotubes, we can see this carbon nanotubes enters at the within the graphene nanosheets, and because they are entering within the graphene nanosheets, it may be believed that they act as a pillar within the graphene nanolayers and solves this restacking problem. So restacking problem is very much lower when we incorporate functionalized carbon nanotubes within the graphene nanolayers. And using these composites, we have fabricated supercapacitor electrode using nickel foam as current collectors. And for that, we have used a nickel foam of diameter 1 centimeter square. And this we use as a working electrode in a 3-electrode system, where silver chloride was used as the reference electrode, platinum wire as the counter electrode, and sodium sulfate as the electrolyte. So now let's move to the results and discussions part. First, we confirmed for functionalization of carbon nanotubes with these desired functionalities by FTIR spectroscopy. Here we can see that we are getting prominent peak at 1700 centimeter inverse and 3400 centimeter inverse, implying presence of carboxylic acid functionalities at the surface of the carbon nanotubes. Similarly, for amine functionalities, we are getting characteristic peaks of NH stressing and bending, and CN stressing for aliphatic amine. So this proves that our carbon nanotubes are successfully functionalized with the desired functionalities. And we then conducted XRD analysis for our synthesized composite. We have 2 composites here. One is the reduced graphene oxide carbon nanotube functionalized carboxylic acid, and other is reduced graphene oxide carbon nanotube functionalized amine. And we can see we have a peak at 2 theta 25.97, reflecting the presence of carbon functionalities on both the composites. and two peaks at 2 theta 43.46 represent less ordered assembled layers of reduced graphene oxide sheets in between the carbon nanotubes. So XRD also confirms the formation of this composite. We also conducted Raman analysis, and these are the two spectra for Raman spectra. For this is one is for graphene oxide, other is for reduced graphene oxide C and D. That means we have synthesized composite with carbon nanotubes that is not functionalized. So RGOCNT means composites with non-functionalized carbon nanotube, and this is composites with functionalized carbon nanotube with acid functionalities. And we can see we are having 1371 and 1610 centimeter inverse, two peaks. One is D peak, which indicates structural defect, and another is Z peak, that implant carbon-carbon bone stressing. So we evaluated the ID by IG ratio, and here you can see for reduced graphene oxide, this value is 0.9. For the composite with non-functionalized carbon nanotube, value increases to 1.04, and for composite with acid functionalized carbon nanotube, the value increases to 1.13. And for this amine functionalized carbon nanotube reduced graphene oxide composite, this value for IG by IG value is 1.09. So what we can predict from here, that with the increase of ID by IG ratio, we may infer that more defect sites are being introduced in our prepared composite than pristine graphene, or this composite which that is not functionalized carbon nanotube reduced graphene oxide composite. So introduction of more defect sites means we are introducing more pores, or maybe we are increasing the surface area of the material. So these are SEM analysis. So SEM images show the wrinkle and silk line sheets that are characteristics of graphene. And in the composites also we can see that these carbon nanotubes are properly entangled with a homogeneous network. The interconnected networks of carbon nanotubes act like bridge between reduced graphene oxide and provide conduction pathway and increases the accessible surface area. So from the same analysis also we can say that the surface area of the synthesized composites has increased. So we also employed XPS analysis. So here you can see we have intense for this 284.84 electron bond, that is sp2 hybridized carbon-carbon double bond. We are having this peak for all the cases, and peak at 286.21 and then 287.92 electron volt represents the sp3 hybridized carbon atoms and remaining oxygen functionalities. The increased intensity of the peak at 288.39 in case of B clearly indicates the presence of carboxylic acid on the side walls of the carbon nanotube. And for this amine functionalized carbon nanotube reduced graphene oxide composite, we have a deconvoluted nitrogen spectra, reveals that we are having peak at 399.5, 400.1 and 402.1 electron volt, corresponding to CnH2 and C and N oxygen bond. So XPS analysis also confirms the formation of the composite successfully. So now let's move to the electrochemical analysis part. I have divided the electrochemical analysis part into two. In the first case, we will be discussing the electrochemical performance of carboxylic acid functionalized composite, and in the other case, we will be discussing the this is amine functionalized carbon nanotubes composite electrochemical behavior. So this is the CV curve. So you can see this A figure is for this CV curve for non-functionalized carbon nanotube and reduced graphene oxide composite, and curve B is for functionalized carbon nanotube reduced graphene oxide composite. From the CV curve itself, we can see that there is a larger area within this CV curve, and we calculated the integrated surface area. And for the non-functionalized case, the value is 6.023 into 10 to the power minus 3 centimeters square. And for the functionalized, that is acid functionalized composite, the value is 8.66 into 10 to the power minus 3 centimeters square. So there is a substantial amount of increase in the surface area, implying that our synthesized composite would be a better candidate as electrode material for supercapacitors. So we investigated the effect of scan rate on the CV curve. Here you can see this rectangular shape of the curve. It is this oval-like shape with no distinct redox peak. It implies the capacitive behavior of the material. And you can see when we increase the scan rate from 20 to 80, even then this oval shape is retained. So from here we can say that the CV curve of the composite retains its oval shape without any distortion even at high scan rate. And this suggests that the material has a fast charging discharging rate, and this fast charging discharging rate itself is very much significant for the material to be used as supercapacitor electrode. So we also conducted galvanostatic charge discharge analysis for the materials, and we calculated specific capacitance by using this equation, that is I into delta T by M into delta P. And this way, for the non-functionalized case, we are getting a specific capacitance value of 230 Faraday per gram, and for functionalized case, this value increases to 302 Faraday per gram. So we also investigated the effect of current density on the specific capacitance value of the composite, and here we can see that at 1 ampere per gram current density, this value is 302, which reduces to 239 Faraday per gram at a current density of 5 ampere per gram. So we can predict that there is 79% retention. Now, in general, what happens that in supercapacitor electrodes, this specific capacitance is retained by nearly 90%. But in our case, we are getting only 79% retention. This may be because that we are using aqueous electrolyte and we are testing this in a 3 electrode system. So it may so happen that during the process of study, the material may have a tendency to get detached from the current collector. And
Dr. Lakkijodi, you have to complete the presentation in 2 or 3 minutes.
Okay. Okay. So in that case, this decrease we have observed. So we also evaluated the effect of current density on specific capacitance value, and we can see for reduced graphene oxide, capacitance retention is 47% only, and for this non-functionalized case, that value is 72%, and for this functionalized case, retention is 79%. So from here, we can say that we have a better material. So this is the electrochemical impedance study. So here in electrochemical impedance, this is a semicircle region of the plot at the high frequency region correspond to the electronic resistance, whereas the linear curve, the low frequency region corresponds to the diffusion control process. And we have also calculated the electrochemical active surface at the area of the material from this Nyquist plot, and we can see that the value for this non-functionalized case, the value is, that is contact resistance value is 165 meters square per gram, which enhanced to 353 meters per gram for our functionalized composites. So we also calculated our stability, and the material is quite stable. And these are the electrochemical analysis for this amine functionalized case. Here also, similar to this carboxylic acid functionalized case, we are getting better results for our synthesized composites. And but we can say that the specific capacitance of this amine functionalized composite retains 90% of its capacitance, even at a current density as high as 5 ampere per gram. The triangular shape of this galvanostatic charge discharge curve also implies superior capacitive properties, and specific capacitance value for this amine functionalized case we are getting is 384 Farad per gram. So this is the electrochemical impedance study. Here also we are getting good results. So this is the cycling stability. We have carried out this cycle for 10,000 cycles, and even after 10,000 cycles, we are maintaining this shape, and this means the composite is quite stable to be a fine potential application. So in conclusions, we can say we have synthesized 2 electrodes. One is with reduced graphene oxide functionalized carbon nanotube with acid, and other with functionalized carbon nanotube, amine functionalized carbon nanotube with reduced graphene oxide. For this SiC functionalized reduced graphene oxide composite, we are getting 302 Faraday per gram specific capacitance with energy density 41.65 watt hour per kg and power density 496.49 watt per kg, and the electrode retains 79% of its capacitance even at a current density as high as 5 ampere per gram. For the amine functionalized carbon nanotube, and the current at 1 ampere per gram current density, we are getting 384 Faraday per gram specific capacitance, and at 5 ampere per gram current density, we are getting 345 Faraday per gram specific capacitance. That is 90% of capacitance is retained even at a high current density. So here the energy density and power density values are 53.33 watt hour per kg and 499.13 watt per kg respectively. So both the electrodes have shown good mechanical stability and flexibility, and we may believe that they can find potential applications in energy storage devices. These are some publications related to this work. So I thank you, organizing committee, for giving me the opportunity to share my work. So thank you all. I wish all of you happy Independence Day in advance. Thank you.
Thank you so much, Dr. Lakshya Jyoti, and same to you also. Wish you all a very happy Independence Day in advance. Thank you so much, Dr. Lakshya Jyoti, for a wonderful talk. You discussed some of your very interesting findings. Now, I would like to request the audience if they have any questions from Dr. Lakshya Jyoti. If there is any query, they can ask.
Sir, I have a question.
Yes, sir.
The self-discharge rate of super capacitors are fairly less than that for, it's fairly higher than that for lithium-ion batteries. So how can we improve this discharge rate?
So for that case, we have to have better surface area and good porosity. And for that, we have to devise materials with good porosity, and that is what we are doing. We are trying to increase the specific. We are yet not getting 526 Faraday per gram specifically. So nobody is getting 526 Faraday per gram without metal. So that is a task. So to have better charge discharge, we have to have better surface area as well as better porosity, and we have to have good synthetics for this.
Okay, sir. Thank you. Thank you for answering.
Thank you.
Is there anyone else who would like to discuss or share anything with us? So I think we have come to the end of this session. All the speakers were wonderful. They discussed very interesting talks, very important findings, and the lectures were insightful and very helpful to all the researchers in the field. Thank you all. Thank you so much.
Hi, and I'd like to thank Dr. Ifat Sareen Ahmed and Dr. Sadish Pisini for chairing this wonderful session and being active all the time.
Thank you
so much, ma'am.
Thank you.
Next session is on biomedical application, and I invite to him Subrasantra, Department of Engineering Design in Indian Institute of Technology, Madras. He will be presenting on biomedical micro-nano devices for cellular therapy and analysis. You are most welcome, sir.
Yeah, good morning, everyone, and thank you to ICN committee to invited me for this presentation. So this slide is visible, right?
Yes, doctor, you can start your presentation.
So here my talk is biomedical micro nano device for cellular therapy and analysis. and we'll discuss the couple of device, how this kind of device can work for different cellular therapy and analysis. So due to shortage of time, we'll discuss just 2 or 3 devices in this talk. So first, for cellular therapy and diagnostics, so we need to understand the different drug delivery system. So we have that commonly used that endocytosis process where the drugs or molecules just surrounded that cells, and it can randomly enter inside the cell, and which is very time consuming and that uncontrollable delivery. Then next we have that bulk electroporation where you applied that very large voltage, that kilovolt to megavolt order voltage with millions of cells together, and due to large voltage and uniform electric field, then maximum cells can damage, and it cannot go for uniform delivery where basically for uniform delivery you need for regenerative medicine purpose or personalized medicine purpose. So another is gene therapy using the virus. In that specific gene you need, a specific virus you need, and you need to code with that gene, and then you need to deliver inside the cell. So here that specific virus needed and the toxic issue become a big issue for this delivery. Then another most popular is the micro injection. So we can just inject that needle inside that cell and we can deliver the drugs or molecules. But when we withdraw this needle, then cell membrane have deformation, large deformation, and cell can die easily. So it's have that cell can damage easily and it is very hard to handle. So now for this kind of drug delivery, so main the question that ideal tools for drug delivery is that how we can deliver that very small to large cargo delivery, high delivery efficiency. Of course, we need after the delivery. Then you can do the different kind of disease analysis after delivery, delivery into different cell types, and uh, delivery into cells into directly. And then of course we need to achieve high cell viability, high throughput, and easy to handle. So in 2011, Professor Rask from MIT just make that one commentary article in Nature Method that is there any easy method to deliver that unpackaged cargo into different kinds of cells with high delivery efficiency and high cell viability. So we will try to develop a couple of devices. We tried, and we tried to that achieve that high delivery efficiency and high cell viability at single cell level. So nowadays, the single cell research is very boom because to understand that cell to cell variation or cell to cell communications, even to understand that cellular heterogeneity study or rare cell events and even cell mutation study, uh, so that single cell research is booming research, and it is very difficult to do the single cell research because we need to fabricate the different kind of sophisticated device and which can isolate or which can separate single cell, and then you can go for single cell analysis. So here we'll use that nano-localized single cell nanoelectroporation device which we developed, and we can see that this is completely microfabrication based silicon device where in top side you have that very tiny nano electrode, and this nano electrode gap between two nano electrode is 60 nanometer, and then cell can seated on top, and each nano electrode, then middle of this nano electrode we have that vertical hole, and which can connect it into the bottom of the channel, and where drug or reservoir can present into the bottom of this device. So by this syringe we put the different kind of drugs or molecules which can go into that channel into that bottom of this device, and we seal that outlet, and syringe is continuously pushed, and then the drugs or molecules through the vertical channel of the in each tip, so drugs or molecules can continuously release. So now when cells are seated into the top of this chip, then we applied that applied that external voltage, and due to that external voltage, then electric field can highly intense in between two tip, and whenever this kind of electric field can interact with that cell membrane, then membrane can deform due to that electric field, and it can open that nanopore, and then the drugs or molecules can enter from that bottom of the channel to that inside of the cell. So this we published in Lab on a Chip in 2020, and this work is also its media released a new method of shipping of materials inside the cells in Hindu business lines on 6th July throughout that India. And now how we fabricate this device and how we simulate this device. So we did that COMSOL simulation, and we applied that 6-volt electric field, and we have this kind of tiny nano electrode which have that 60 nanometer gap. And whenever we applied that voltage in between these two tips, then we can find that electric field can very highly intense in between that two tip. And this is the zooming area where we can see that electric field can highly intense, and uh, intense of that electric field is around that 0.8 into 10 to the power 8 volt per meter, which is high enough to deform the cell membrane, and drug or molecules can deliver, and after withdraw the electric pulse, then membrane can reseal again, and we can successfully deliver the drugs or molecules, and cell can be live for a longer time. Because we are just deforming into that 60 nanometer area of that cell membrane, where you have that single cell dimension is nearly 25 to 30 micrometer. And the resistive heat we calculated by COMSOL multiphysics. Again, we can see that resistive heat effect also just in between two tip into 60 nanometer area of the tip. And that zoom of that resistive heat, we can see that only in each tip we have the resistive heating, which is nearly 1.4 into 10 to the power 6 watt per meter cube. So heating effect also may deform the cell membrane, and so combination of that electric field and resistive heat and affecting into that cell membrane deformation, and drugs or molecules can deliver. So now this is the fabrication process. Will not go to that in detail. So we considered that silicon material 225 micrometer and 100 nanometer silicon nitride membrane. And then we, by microfabrication process, we etch the nitride by potassium hydroxide. And then we etch the nitride by reactive ion etching. Then we use that potassium hydroxide to etch that silicon material. And after that, we did that oxide formation, deposition, then tetramethyl ammonium hydroxide etching and formation of that membrane. And then silicon nitride is completely transparent, and then we coated that indium tin oxide and patterned that electrode. After that, to passivate that electric field, we deposited that plasma enhanced chemical paper deposition oxide, and then we make that 60 nanometer gap in each electrode by that focused ion beam. And we bonded that glass into the bottom of this device, and cell can be seeded into the top, and microscope objective can be set up into the bottom of this chip. And because we consider this kind of very thin material to fabricate this chip, because for inverted fluorescence microscope, you can see the fluorescence if your thickness is less than 1 millimeter of your any material. So more than 1 millimeter is difficult to visualize that live fluorescence. So now this is the final chip fabrication, where we fabricated that ITO lines by microfabrication process. Then by focused ion beam we cut, and it is a 60 nanometer gap between two tip. So cell can seeded into top of this tip, and when we apply that electric field in between these two tip, then cell membrane can deform, and drugs or molecules can enter from that bottom of this channel to that inside of the cell. So this is final chip, where we have that inlet, outlet, and main chamber. And in main chamber, we just put that cancer cell or stem cell. And after visualization of the cell position, then we applied that electric field for nano electroporation. So this is the experimental results, and where we can find that this is the electrode position, and this is the cell that which is that human lung cancer cell. We applied that 6-volt peak to peak 20 millisecond pulse, and then we can see that within 1 second we cannot see that any fluorescence. So this PI dye cannot deliver inside the cell. If you deform that membrane a particular area, then PI dye can enter through this cell, and it can make that red fluorescence color. So after 3 seconds, we can see that as the electrode position, then PI dye is entering, and the dye is accumulating into particular this area, and then it is diffusing throughout the cell. So finally, these results is confirming that if we apply this kind of electric external voltage, then around 20 to 25 seconds, then PI molecules can enter into that cell successfully. So this okay, somehow this video is not going to on. So this is the live cell imaging, like how that fluorescence is entering inside the cells, that image. So then we deliver that quantum dot inside that cell with that human lung cancer cell with 6 volt peak to peak, that 40 millisecond and 2 pulse. And we have the 2 electrode, and cell's position is in just top of these 2 electrodes. And we can see that quantum dot size is like approximately 10 nanometers. So again, that when that quantum dot is outside of the cell, so it will not give the color. But when we'll deform the cell membrane, and quantum dot can enter inside the cell, and it can give the red fluorescence color. So we can see that nearly that 35 to 40 minutes, like the quantum dot slowly can enter, and it can give the red fluorescence color. So now this is the confocal laser scanning, and where it can confirm that inside the cell we have that quantum dot or not. So this is the 1 micrometer step size, and we can each 1 micrometer step size, and we scan the by confocal laser scanning, and which can confirm that this is the top to bottom of the cell, and it confirmed that quantum dot successfully enter inside the cell. Then we tested that plasmid delivery, and where that plasmid DNA can enter inside the cell when we deform the cell membrane. So you have that 3 nano electrode, and this is the cell position. In particular, 3 position, 60 nanometer area we can deform, and then plasmids or DNA can deliver. This is the Hodges dye, staining dye, where we can see the nucleus of the cell with the different time. And this is the plasma membrane dye, which can stain the plasma membrane. And this GFP expression, generally, if we put this kind of plasmids into that cell by endocytosis process, it cannot enter, or even after 3 to 4 days, you can visualize a little bit of protein expression inside the cell. But however, this kind of technique, you can see that within 2 hours and 4 hours, that protein can express just into the cell cytosol, and in 10 hours, that protein can completely express into that inside that cell. And this is the just membrane and nucleus position. We just merge that image, and then membrane plus GFP protein expression, then nucleus and GFP, where it can confirm that the protein can express inside that only that cytoplasmic area. So now we have that next device. Due to a time limitation, we are not showing that all the experimental results. Here the next device, we use that laser based energy. So previous device we use that electrical energy to deform the cell membrane and successfully deliver the molecules, and we can test the cell viability. Here we considered the glass substrate. Again, this is complete microfabrication process, and then this is the titanium micro disc, which the dimension is just 3 micrometer circular area, and gap between 2 titanium micro discs is 15 micrometer. And after fabrication of this by microfabrication process, and then we culture the cells into this throughout this chip, and this chip is 2 centimeter into 2 centimeter area. And when after that we scan the laser through this chip area, and whenever we scan the laser, then this kind of titanium disc, it can heat up, and due to heat up, whatever the surrounding medium, it can vaporize, and it can produce that micro bubbles or cavitation bubbles, and these bubbles can force this membrane. And generally this kind of membrane thickness is 5 nanometer, and whenever this bubble can force the membrane, then particular this kind of disc area, that cell membrane can deform, and drugs or biomolecules which is outside. So by simple diffusion process or concentration gradient, because outside of the cell you have that high concentration gradient, and inside of the cell low concentration of that molecules. So by simple diffusion process, after cell membrane deformation, these molecules can enter inside the cell, and it can give the fluorescence or any kind of DNA or RNA delivery results. So here this we published in ACS Biomaterial Science and Engineering, and accepted for that cover page publication due to the novelty. And this is the device fabrication, where cover glass, and then coat that photoresist, and then photolithography or UV lithographic pattern. And after that, we deposited gold or titanium into top of this glass with this pattern photoresist. And finally, we use the lift off technique, and then the titanium deposited into with that 15 micrometer gap with 3 micrometer titanium area. So this is the ACM image, where we can see the titanium disc, and this is the single titanium disc. And after that, we culture the cells on top of this device, and we scan the laser. So now this is experimental results. So here we can see that human cervical cancer cell and N2A cell line is that neuron cell line, and HeLa cell also human cervical cancer cell. And we tested with that PI dye delivery. So PI dye again, whenever it is outside the cell, it cannot give any red color. And if we only deform the cell membrane, and then it can stain into that cell cytosol, and it can give the real red color. And then we tested that viability using that calcium AM, and calcium AM can sell permeable dye, and it can, whenever we can put, and it can stain the green color. That means that after delivery cells are live. So here that we use this kind of 20 millijoule per centimeter square laser energy, and we scan the laser scan with that 120 millimeter per minute, and we can see that in CR cells that PI dye successfully deliver. And after delivery, all cells are live by testing that calcium AM, and that Mars image is also confirming that there is no more red color, which also confirm that almost 99% or more than 99% cells are live after delivery. So this is same again for N2A cell lines, and this is for HeLa cell lines. We can see that couple of cells are red color after that Mars image, so which is indicating that after delivery cell membrane is not resealed for particular HeLa cell, and couple of cells are dead after delivery. So this depends upon that membrane to membrane and cell to cell types to achieve that high delivery efficiency and high cell viability. And this we tested with that dextran delivery. And after dextran delivery, again that dextran delivery is it is a dextran 10K large molecules, and after delivery it will give that red color. So we can see that after delivery cells are red, and then we tested with that calcium AM, and after delivery that most of the cells are live. And Mars image is also confirming that using this kind of device that cells are live after day 1, day 2, even after day 3, we can see that none of the cells are dead after delivery. So by using this kind of technique, then we can specifically deliver the different kind of DNA or RNA, we can do that different kind of cellular analysis. So again, this is the last device, and due to time limitation, so here we did that single cell patterning and that intercellular molecular delivery. And here that silicon or glass substrate, and then we did the lithography technique to pattern that SU8 membrane, and which have that nearly 50 to 60 micrometer array of hole. And after fabrication, then we release this kind of membrane, and then this membrane we put into that cell culture petri dish, and then we culture that cancer cells or stem cells. And then after 10 to 15 hours, we release this membrane. So then now you can see that single cell is patterning into that array. So this kind of single cell patterning is very useful for cell to cell communication study and cell heterogeneity study. And we are currently doing this kind of cellular heterogeneity study in our lab. But this is not part of this talk. So here after patterning of this kind of single cell, then we added that drugs or biomolecules. And in top, we have this kind of glass substrate with that gold.
Excuse me, sir. Sir, can you please conclude your presentation?
Yeah, we have 4 minutes still now. Or 20 minutes. I started in 9:50. So when we align this kind of device and we scan the laser, then this kind of gold micro disc, it can heat up and it can produce that cavitation bubble, and it can force the membrane and deliver that molecules. So then this is the design and fabrication, where we can fabricate this kind of SU8 membrane with that array of hole, 50 micrometer hole, where only single cell can pass, and it can seed as a array of hole. And this is the delivery experimental result. So where we use that defined kind of hole size. If we use that almost 100 micrometer hole, and if we use this kind of device, and we can deliver that PI molecules or different kind of molecules, and which is confirming by that red color. And after that cell viability test we did, and we can see that after delivery that almost all cells are live after delivery. So less than 20 cells per pattern. So we use like 60 micrometer area of that whole microarray hole. And then finally, when we use that 40 micrometer array of hole, then we can pattern that single cell and successfully deliver the drugs or molecules, and cells are live after delivery. So this is siRNA delivery. Also, if siRNA can enter, then it can give the green color, which is confirming that this kind of technique can do that siRNA delivery. And after delivery, we tested with that calcium arrow that which can stain that live cell with that red color. So after this kind of siRNA successful delivery, we tested, and cells are almost all cells are live after even after 3 days. So this is L929 cells, and that SIHA cells we tested, and again we did that very large enzyme delivery. Again, this enzyme, if it enter only inside the cell, it will give that red color, and we tested that calcium with that green color, that cell viability, and we can see that enzyme can also successfully deliver inside the cell. So the conclusion again, so here we successfully deliver different kind of quantum dots, plasmids, and very large molecules to that more small molecules, and delivery efficiency in some of the device like more than 98%, and cell viability is almost 100%, and different cargo delivery into different cells we tested, and most of the devices are easy to use. So whatever the commentary of that from that MIT that into the nature method, and we hope we successfully solve that couple of points for that drug delivery by physical energy. Then as a editor, like we published couple of books like Handbook of Single Cell Technology in last 2 years in our domain. Currently, I'm the guest editor for different journals like Cells, Impact Factor 7.6, and Journal of Micro Machines, Frontiers of Bioengineering and Biotechnology. Patents, like we applied like almost 10 patents in 2020, which is the highest patent from that individual law from IIT Madras. And currently we are going to start up using this concept. We are opening that one company with that optoperator device, which can transfect any kind of cells with if you have that any kind of molecules which can give that successful delivery. And this is our like very large group with that postdoc and 13 PhD student. And thank you very much for your attention.
Thank you so much, sir, for your wonderful presentation. I would like to request audience to please participate in the discussion. Okay, so we will move on to next presentation. I would like to invite Ifat Zareen Ahmed, Department of Engineering, Integral University, Uttar Pradesh, India. She will be delivering her talk on development of photoprotective nanoemulsion of cyclotonin to evaluate its anti-cancer activities on skin cell line.
Thank you so much, madam. Is my slide visible?
Yes, ma'am. Ma'am, can you make it to full screen? Yes, ma'am, it is visible. You can start your presentation, ma'am.
So, very good morning to the chairpersons and all the delegates who are connected here online today on this wonderful morning of this session. Myself, Ifat Zareen Ahmed, I am professor in the Department of Bioengineering at Integral University, Lucknow. First of all, I would like to thank the organizers and particularly Professor Sabu Thomas for giving me this opportunity to share my work with you all. So today I'll be talking about development of photoprotective nanoemulsion of cytonemin to evaluate its anti-cancer activities on skin cell line. Before going into the details of cytonemin, I would like to share the history of algae with you all. As according to the Lewis Thomas, the life of the planet began the long, slow process of modulating and regulating the physical conditions of the planet. The oxygen in today's atmosphere is almost entirely the result of photosynthetic living, which had its start with the appearance of blue-green algae among the microorganisms. This saying of uh, Lewis Thomas very clearly shows that the living organisms which arose first on this planet Earth were blue-green algae, and they were responsible for converting this reducing atmosphere into the oxidizing one because of their photosynthetic activities. This is my cyanobacteria lab where we culture our microorganisms, the colorful microorganisms, and we give them different types of stress. The stress which I will be speaking today will be UVB stress, because the cytonemin pigment which we isolated is having a role in the UV protection. So under the stress of UVB, the production of cytonemin is enhanced. And we were interested to we were uh, intending to enhance the production of cytonemin pigment because of its biomedical significance, which I'll be discussing later. These are the cyanobacterial cultures, and this is a small setup in my lab where we expose these cyanobacterial cultures to UVB stress. Under UVB stress, the cytonemin pigment synthesis is enhanced. Algae are the primitive plants. They do not have any true roots. They have only attachment-like structures. They produce spores for reproduction. Most have sexual and asexual reproduction. They are non-vascular and they do not possess any internal connectivity. There are several morphological forms of cyanobacteria or blue-green algae. They range from unicellular to filamentous, non-heterocystous and to heterocystous. They have false branching also sometimes. So there are several types of morphological forms in which they exist in nature. Cyanobacteria, I must tell you, they're wonderful organisms and they are the first life form on Earth. Now, why microalgae research is one of the thrust areas these days? Because they are the models for higher plants. Any stress mechanisms can be studied very well on these. Bioremediation and bioaccumulation, they are the models for these studies. They are very good biofertilizers. They are nowadays used to produce biofuels, nutraceuticals, pharmaceuticals products. They are very well used in cosmeceutical products and in the wastewater treatment. This is one of my publications where I have collected the literature where in the thrust areas, scientists are using cyanobacteria based water treatment plants. So cyanobacteria is being used to treat water nowadays. These are some of the metabolites from algae and cyanobacteria which find significance in the pharmacological industries. They are lipids, pigments, polysaccharides, chemicals, proteins, which shows significance bioactivity against bacteria, against cancer. They are anti-inflammatory agents, anti-protozoal agents, antiviral agents, antioxidants, antifungal agents, and anticoagulant. So there are vast activities shown by these bioactive metabolites derived from these cyanobacteria. This is one of my chapters where I have put in the cyanobacterial peptides with respect to anti-cancer activity. Now, nanotechnology is the branch of science which deals with manipulating the matter at atomic and molecular level. Nanotechnology in dosage form development had many advantages, like they have enhanced solubility, increased dissolution rate, enhanced stability, reduction in dosage can be done with nano materials, with nano drugs, increase in bioavailability can be achieved, and they are very rapid in their action and less toxic also. So there are several benefits of nanotechnology in drug delivery. There is improved understanding of the chemicals at the cellular or molecular level. We can study the mechanism of action of the drug, increased throughput, improved identification and validation of target is there, improved visualization of drug interaction is there. So we can study how the drug is interacting at the molecular level, how it is entering inside the cell, how it is interacting with the receptors for the targeted drug delivery. These are the advantages of the nanotechnology and the nano drugs. This is one of the publications where I have listed the applications of surface modified nanomaterials for cancer theranostics, for the therapy of cancer as well as for the diagnostic of cancer. And in another publication, I've shown the antibacterial potential of one of the cyanobacterial strains. This is unicellular strain, Senecococcus species PCC7942. under the influence of UVB radiations on skin pathogens. Nanoemulsions are a very good form of drugs to be delivered inside the cell. They can be defined as an oil in water emulsion with the mean droplet diameter of 50 to 100 nanometers. It is a lipid monolayer enclosing the liquid lipid core. The inner core is consisting of any oil. Drug molecules are entrapped within the source, and the emulsifier layer is there to stabilize the nanoemulsion. There are several methods of nanoemulsion preparation. High energy method is there, low energy ultrasonication method is there. So these are the several methods to prepare nanoemulsion. Several applications of nanoemulsions are there in cosmetics and drugs, in antimicrobial agents, cancer therapy, and their vehicle for transdermal drug delivery. Ultraviolet radiation have very harmful effects on the skin, and it leads to various types of skin disorders, especially cancers in European countries where they are not exposed to sun much. So the UV radiations have damaging effects, and since the depletion of ozone layer due to pollution, UV radiation is entering the earth, and especially the UVB radiation is and the wavelength entering the earth's surface and creating lots of damages. There are several cyanobacterial formulations available in the market for skin care. Most of them are available in the European market, and very less are there in the Indian market presently. These are the skin care formulations which have been prepared using cyanobacterial bioactive metabolites. Cyanobacteria based nanoformulations and their intended marketed rules and regulations are there. We have to develop a nano formulation and we have to test them in the preclinical trials on the animals. Then we have to go to the clinical trials, several phases of clinical trials and human studies before they are marketed into the system, before they are commercialized. Patent also could be obtained on these products. So my work is to develop some cyanobacterial based cosmeceutical products which is incorporated with cytonemin, which I have told cytonemin is a UVB protective pigment present in cyanobacteria. What we have done, we have raised the cytonemin pigment by giving the UVB stress to the cyanobacteria. This is the UV radiation, the effect of UV radiation on the cyanobacteria. They can cause DNA damage and the damage to the thylakoid membranes of cyanobacteria. They can degrade D1, D2 protein, and they can reduce the cell metabolism ultimately and alteration in the protein synthesis. They can also damage the formation of carboxypeptidase D protein at the molecular level. They can also have an effect on the messenger RNA, misleading of transcription and translation. They can generate lots of reactive oxygen species, filament breakage is there, pigment bleaching, and decreased photosynthetic performance is seen. Now, because of these deleterious effect of UV radiation on cyanobacteria, they have evolved several mechanisms to avoid these UVB radiation and to avoid the harmful effects of these radiations, like avoidance, migration, and mat formation. Antioxidant systems are very well established in these small microorganisms, enzymatic as well as non-enzymatic. Synthesis of UV protective compounds like cytonemin and mycosporine like amino acids. DNA repair mechanism is well established. Expression and resynthesis of protein is there. And they can also go to apoptosis or programmed cell death when they could not avoid the UVB radiation. So there are several mechanisms by which cyanobacteria can mitigate the harmful effects of the UVB radiations. So I am interested in the pigment cytonemin and to prepare the nano emulsion of this cytonemin. By nano formulation, because they increase the effectiveness of the active compound, they increase selectivity and efficacy. At a lower dose, they are very effective. They have reduced side effects. They have the sustained release of the drug, and they increase the stability and solubility of the drugs. So I was interested to prepare the nanoemulsion of cytonemin. The methodology which we adopted is that we grew the culture of Cytonema javanicum. They were allowed to grow in BG11 medium. Cytonemin pigment under UVB stress, they produced lots of cytonemin. Enhanced production of cytonemin was seen, and we have extracted and purified the cytonemin pigment from the cultures under UVB stress. We prepared the cytonemin extracted nanoemulsions, nanoformulations. We have characterized it by means of measuring the size, PDI, zeta potential, by quantification and by chem analysis, by the percent entrapment of drug, and by in vitro release assays. Then we have, once we have prepared the nanoemulsion and characterized it, we have done in vitro analysis using several assays on the skin cancer cell lines. There we have used the HICAT cell lines, which are transformed keratinocyte cells, and the assays which we have done to establish the anti-cancer activity were MTT assay, colonogenic assay, intracellular ROS generation by microscopy, DAPI staining, cell cycle analysis, apoptosis analysis, ROS generation assay by FACS, mitochondrial membrane potential depolarization. These assays established well that cytonemin is showing a very good anti-cancer potential on skin cells. Then we have prepared the cream and gel cosmetics we have prepared incorporating this nanoemulsion, and we have studied the physical properties of these cosmetic products, their thermal stability, pH, and we have done the patch test to see whether any allergic reaction is there. We have done spreadability studies and microbial growth test. After this, we have tested this cream and gel on the animal model system. We have used Vistar rat's skin. We have applied these cream and gels on the skin of the Vistar rats, and we have done the several analysis. We have also studied the cytonemin pigment using in silico assays like ADME drug likeness screening, molecular docking studies, and simulations. These are the results of the nano characterization of nanoemulsion. The size of nanoemulsion was in the range of 80 to 100 nanometers. The TEM micrograph shows that the nanoemulsion which was prepared was homogeneous in nature. They were having the round morphology. The pseudo-ternary phase diagram tells what ratio of the S mix, that is our oil phase and the surfactant and co-surfactant makes the most stable nanoemulsion. Then we have seen the purity using the calibration curve, and in vitro release of the drug was also seen. Then we have evaluated our nanoemulsion on the HICAT, that is the skin cancer cell lines. Our cultures were grown, cytonemin was extracted, nanoemulsion was prepared. This figure shows the human keratinocyte, that is HICAT cell line. Using MTT assay, the dose optimization was done. A particular dose of UVB was standardized to be given to cyanobacterial cultures, and then to these when they were treated with to the skin cell lines. The MTT result shows that the cytonemin nanoemulsion was very good in inhibiting the growth of the cancer cells. This is a result of cytonemin extract alone. These are the IC50 values of 24 hours, 48 hours, and 72 hours. The cytonemin nanoemulsion without the extract and the nanoemulsion with the extract. So the cytonemin nanoemulsion with the extract showed the IC50 value of this 50 micrograms with the co-exposure of UVB, and it was 54 after 48 hours and 43 after 72 hours. So this data showed that the cytonemin nanoemulsion is acting on the skin cancer cell lines in a dose dependent manner as well as in a time dependent manner. With time, there is more killing of the cancerous cells. This is the colony forming assay, which also shows that nanoemulsion is acting on the HICAT cells, and there is less colony seen. Then we have seen the reactive oxygen species generation in HICAT cell line, skin cell line, and there was more ROS generation when it was the cancer cell line was treated with our nano emulsion loaded with cytonemin extract, leading to the killing of the cells. In DAPI staining also we have seen the killing of the cells. Then we have done the apoptosis analysis to see the cell the stage of the cell cycle in which there is killing of the cells. Cell cycle analysis is being done by FACS. ROS generation was also seen by FACS, and mitochondrial membrane potential was also studied using
Excuse me,
FACS.
ma'am.
Yes,
Ma'am, will you conclude your slide in next 2 minutes?
yes, sure, madam.
Okay,
I
thank
still
you.
have time, madam. I started at 10:20. It is
And
only 10:28. I have 20 minutes time,
okay,
but I will try to conclude before that, madam. I'm trying.
okay, ma'am.
What we have done, we have prepared the nano emulsion based gel and cream, and these are in the purpose of creating these nano emulsion based gel and cream is to use them as cosmetics. If we can apply them on skin, we can be protected from UVB radiation, and we have well established also that they are effective on skin cancers also. So with the nano emulsion, we have prepared the nano emulsion based gel and cream, and we have studied their texture, color, odor, pH value, thermal stability, and degradation. They were very stable products, and they were showing antimicrobial activity also. We have also evaluated them on the bacteria. We have seen their effects on some bacterial strains, so they were showing good antimicrobial activities. Then we have done the in vivo evaluation of these cream and gel preparations. We have taken the mouse which has been acclimatized for a week, then we have shaved the skin of the Vista rats, and we have applied our cytonemin based cream and gel. We have given UV exposure to these rats, and we have collected the samples after a week's treatment. The samples comprise of skin and blood. They have shown good antioxidant activity. The treatment by our cream and gel have raised the antioxidant status of the skin. This is the histological analysis of the primary skin interaction. Irritation study on the star rats. This is the control. This is UV plus control. This is the extract cream. This is the nano emulsion cream. And this is the nano emulsion gel. We can see that in the control and UV, there is lots of uh, the degradation in the skin tissues, whereas our nano emulsion cream and gel has not shown so much of deleterious effects. They have protected the skin from the harmful effects of UV. We have also performed the in silico analysis. The molecular docking studies was done, and then these autodock scores were obtained from for cytonemin. For cytonemin, it was 15.1. For the EHMC standard, it was 4.98. These are the inhibition constant, and for fucosterol, it was 34.08. So these figures shows the hydrophobic interactions of EHMC EGFR complex with the cytonemin and with fucosterol. So in the conclusion slide, I would like to say that cytonemin loaded lipid nanoparticles proved to have greater efficacy for drug loading, so could be used in pharmaceutical and cosmeceutical applications. Since in vitro evaluation suggested a promising role of cytonemin nanoemulsion in protection of human skin cells from UVB-induced DNA damage and apoptosis, hence it also acts as an effective chemopreventive agent against UVB-induced carcinogenesis. This study also demonstrated the feasibility of nanoemulsion systems for improved topical delivery. Further, in vivo evaluation of cytonemin nanoemulsion incorporated cream and gel exhibit good UVR protection as well as antioxidant effects. Hence, cytonemin nanoemulsion incorporated cream and gel have better UVB efficacy as compared to pure extract or cream. Thank you so much for the patient hearing. I would like to invite any questions or any query or any suggestions from the audience.
Thank you so much, ma'am. It was a wonderful presentation, and you have a lot of work done on this field, and we can see your outstanding publications also. It was a great work, ma'am. Now I would like to invite audience for the discussion.
Thank you so much, madam. If there is any query, I'll be happy to answer that.
Ma'am, actually, one query, I just not query, I just want to know that the cream that you have developed, will it work on already affected skin, or will it just protect the skin from for the like affecting, getting affected?
Ma'am, what we have proposed is that, in skin cancers, there are lots of damage to the skin cells.
Yes, ma'am.
So they are both preventive as well as curative. They will be acting both to prevent the cancers if there is, then since they are having UVB protective efficacy also. So they will be preventing the wounds also. Like I am proposing now in another project, I have proposing these creams and gels on a wound healing patches to develop a wound healing patch.
Yes.
So they will be acting on the wounds also. So they will be both preventive and curative.
Okay, so ma'am, are you planning of marketing these creams or
Yes, yes.
anything?
I'm just waiting to get patents. I have applied. I've published patents on these. So as soon as I will get patents, I will be commercializing these creams and gels. I'll be inviting some cosmeceutical industries like L'Oreal, so we can discuss. And I'm thinking to commercialize it.
Ma'am, it's really a great work you are doing.
Thank
And
you so much. Thank you, ma'am, for your appreciation. It means a lot. It means a lot to us, to our team. This appreciation this keeps us moving, keeps give us motivation, and encourages us to do better work.
thank you so much, ma'am.
Thank you, ma'am. Thank you.
Now I would like to invite Kanchan Patak, Naurozi Wadia College, Pune, Maharashtra. She will be presenting on in vivo validation of zinc nanoparticles as discolorizing agent in Drosophila. Kanchan ma'am, you are
Thank you,
most
ma'am.
welcome.
Yeah. Am I audible?
Yes, ma'am, you are audible.
Yeah. I'll just share my screen. Is the screen visible to all?
Yes, ma'am, it is visible and your voice is audible. You can continue.
Yeah, yeah. Thank you, ma'am. At the outset, I would first of all like to thank the organizers for giving me opportunity to present a piece of my work. The title of my work is In Vivo Validation of Zinc Nanoparticles as a Decolorizing Agent in Drosophila. Just to give you a background, as we know, the rapid growth of nanomaterials and their increasing demands in all walks of life have led to an incremental production and uncontrolled use of these, which have further raised a concern to the health of ecosystem. Now, synthetic metal and metal oxide NPs are among the primary massively produced nanomaterials. The present study aims to validate the potential of zinc nanoparticles, which are one of the non-conventional NPs. Non-conventional in a sense that when we talk about zinc, usually the oxide or sulfide form of a zinc is used in various aspects, but as such, the metallic part of it and its nanoparticles are one of the rarely used NPs. So zinc nanoparticles, which are one of the non-conventional NPs to modulate the body coloration in Drosophila. Just a minute, my slideshow is not working. Yeah. Although it's a natural component of a skin tissue, but a potential of zinc in its either form, either a nano or a bulk, to interfere in the skin melanization has not yet been assessed to a large extent. Our earlier studies on other metallic nanoparticles such as silver oxide, and a zinc oxide nanoparticles, and also their microparticles, that is a bulk form, they have shown a failure of any adverse effects on Drosophila melanization pathway. So zinc oxide, we have already worked and published data indicating that zinc oxide, when zinc is in oxide form, it does not have any adverse effect on the Drosophila melanization pathway. But when silver and silver oxide NPs were given, there was an adverse effect on melanization pathway. So we had a question that if zinc in its oxide form, it is not having any adverse effect, but can zinc, when it is present in the metallic form, can have any adverse effect on the Drosophila melanization pathway or not? So coming to the methodologies, commercial zinc nanoparticles were used from Eldridge with a size range less than or equal to 50 nanometers roughly. They were characterized by routine methods of various physicochemical methods such as UV visible spectroscopy, X-ray diffraction, SEM studies were done, FTIR and particle size was determined. Later on, these particles were treated to the Drosophila flies via oral route. So they were mixed in the food medium, and each larval stage was then exposed to a range of concentration. After the required time point of incubation, a percent mortality was calculated, and which was further analyzed statistically. Internalization was also quantified by using atomic absorption spectroscopy method by routine protocol. Morphological observation were done on various wild type Drosophila flies, as well as some of the body pigmentation mutants such as yellow and ebony flies were, again, they were also treated with NPs. They were allowed to grow and metamorphose in the same medium containing zinc nanoparticles. Observation of progeny flies was done to evaluate any change in the melanization. Potential of these zinc nanoparticles to cause any somatic mutation and recombination was evaluated by a smart assay using MWH and FLAIR mutant flies. Later on, the biochemical analysis of melanization pathway was done, in which the total body melanin of adult flies was performed, which was later on taken for analysis of phenol oxidase activity, quantification of a key amino acids of body pigmentation pathway, which is tyrosine and dopa, was done by HPLC. An interaction of these amino acids with that of zinc nanoparticles was also performed by UV visible spectroscopy and FTIR analysis to understand any new functional groups that were produced or not. This is the data of characterization showing typical 2 lambda max for zinc nanoparticles. XRD was done. Size range was found to be around 50 to 70 nanometers. FESEM was performed to understand the surface morphology as well as to get an idea of a rough size of these particles. The AS studies indicated that zinc was successfully internalized in all the life stages of Drosophila, including larva, pupa, and adult. Here, the naturally occurring zinc levels were deducted from all the treatment values in order to get the accurate data of our treatment. So as we can see that as we proceed from a larval to pupal stage, the amount of zinc was increasing, and in the adults we can see that there's a slight decrement in the amount of zinc in case of adults. This could be due to when the embryos, they emerge out, when the adult fly emerge out from the pupal case, some of the particles which are deposited in the pupal case, they will be not available. So this decrement in the levels could be because of a loss of zinc nanoparticles which were there in the pupal case. To our surprise, what we noticed was the flies that were emerged from zinc NP containing medium. As you can see, as we go from left to right, we can see that this is the control fly without any treatment of zinc nanoparticle. This is the control female fly. This is the zinc treated female fly. This is the control male fly, and this is the zinc NP treated male fly. So if we compare the color of the flies with that of a control, we will definitely agree that there was a reduction, there was a partial reduction of body pigment. So this is of wild type. When we treated a yellow body mutant, a similar results were observed. But to our surprise, ebony flies did not show any effect on the pigmentation. Of course, this reduction in pigmentation was not a complete, okay, and there was no effect on the eye pigmentation. So such a phenotype is called as a leucistic phenotype when there is a reduction in the body pigmentation without affecting the eye pigmentation. Okay, so leucism was seen, but it was not complete leucism, in a sense that we can still see some of the abdominal patches here, abdominal melanin bands here, and the typical dark tip of the male fly, it was there, but it was to a lesser extent. So that's why we call these flies as a partially leucistic flies. So in case of wild type and in case of a yellow body mutant, this partial leucism was observed in the flies, whereas the ebony flies, they failed to show any effect on the body melanization. So then the adult flies were evaluated for the total melanin content. This for our other study, we have also done the comparative study of zinc microparticles here, although I have not shown much of data of it, but here I would like to show you that when the flies, they were treated with zinc NP, there was a considerable reduction in the melanin content, and it was statistically significant when zinc was in nano form. Now, when we look at the pigmentation pathway, body pigmentation pathway, this is the pathway. This is the rate limiting step wherein conversion of tyrosine to DOPA takes place by tyrosine hydroxylase. And then from this DOPA, it's a multi-branched pathway, which one branch produces the dopamelanin, which is black in color, brown in color, then yellow in color, yellow pigments are also produced. So from DOPA onwards, there is a multi-branching of pathway, but this is an important step of the pathway where tyrosine is converted to a DOPA. Now, literature says that usually these metal nanoparticles, they have a tendency to bind with amine group. That's why we wanted to find out if this reduction in pigmentation is because of binding between these key amino acids or not. So for that purpose, we quantified the total levels of tyrosine and DOPA, and also there is a report indicating that these metal nanoparticles have an ability to bind non-covalently with an enzyme such as tyrosine hydroxylase and phenol oxidase. Phenol oxidase is the last step of catalysis where the actual melanin is produced. So we decided to target these key steps wherein we quantified the levels of tyrosine and DOPA, and we also evaluated the functionality of phenol oxidase enzyme in presence of zinc nanoparticles. So this is the data showing graph showing the effect of zinc nanoparticles on phenol oxidase enzyme activity. So the control and treated, if we see that no doubt the PO enzyme was active in case of ZNNP treatment, but its functionality was reduced as compared to that of a control. So this could be one aspect giving an explanation why we got those partially depigmented flies. And if we see here the levels of tyrosine and DOPA, then they were also reduced as compared to that of a control. So this is the control levels of tyrosine and DOPA, and these are the ZNNP treated levels. So it was a combinatorial effect of decrease in the level of tyrosine and DOPA and the reduced functionality of phenol oxidase enzyme, which was contributing to the lesser levels of melanin. So we decided to perform the spectrophotometric assay to understand that is there any binding or interaction between ZNNPs with that of tyrosine and DOPA. So here is the data showing the combinatorial effect of ZNNP plus tyrosine. In UV visible spectroscopy, we did not find a much of a difference, but what we could see in the FTIR analysis that when tyrosine and DOPA were mixed with ZNNPs, there was a formation of a new peaks in a region around 1200 to 1400, and these two peaks typically indicate the formation of ether-like linkage between the cyclic OH group of DOPA and tyrosine with that of ZNNPs. So we postulate or we predict that there was an interaction, although it was a weak interaction, but there was a direct interaction between DOPA and tyrosine with that of ZNNPs, which was reducing the availability of tyrosine and DOPA in the free circulating hemolymph. And since there were less amount of tyrosine and DOPA which were available for further reaction of melanization pathway, That's why the final product, which is melanin, was produced in a reduced amount, which resulted in the partial depigmentation. So the present study is a pioneering report of effect of ZNNPs on Drosophila pigmentation pathway, effects on functionality of phenol oxidase enzyme, and levels of circulating tyrosine and dopa indicate that these NPs may have pleiotropic effect on all over the entire physiology of organism, because this tyrosine and dopa, they not only participate in pigmentation pathway, but they have an important role to play in behavioral aspect and the nervous system of the flies also. So there could be a pleiotropic effect of these NPs on the overall physiology of these flies. Now, in lower invertebrates, such as in insects, the body pigmentation is one of the crucial traits required for survival. So needless to say that any alteration in pigmentation pathway will have a pleiotropic long-term effects in the body of insect, despite the fact that such a pigmentation may act as a camouflage or may enhance the chances of survival also. So I thank all my collaborators, Professor B.B. Nath, who is Emeritus Professor at Department of Zoology, Savitribai Phule Pune University, and Professor P.K. Khanna, Professor in Defense Institute of Advanced Technology. I would also like to thank all these institutions for providing me infrastructure and different facilities. Some of our data we have published in Metallomics, and recently we have also published zinc oxide data in Materials Today proceedings. So thank you. Thank you so much for your patient listening. And if you have any doubt, you can ask.
Thank you, ma'am. It was a wonderful presentation. And I would like the audience to participate in the discussion. So we can start with the next session.
Thank you.
For the next session, I would like to invite Tuhin Subrasantra, Department of Engineering Design, Indian Institute of Technology, Madras. He will be chairing the session for hybrid materials. Hello, Dr. Tuhin.
Yes, thank you, madam. Yeah. So there are another one chairperson, right? Hello.
And Kamla Khan Kailasam from Institute of Nanoscience and Technology, India. I don't know if it's present or not. Sir, will you share the...
So next presentation can start here. The presenter is that Fuladipa Patra, the Department of Chemistry, Indian Institute of Petroleum and Engineering, Visakhapatnam, India. The title is that hybrid composite of carbon nano anion and zinc oxide tetrapods for high performance supercapacitors. So is he presenting?
Sir, he is present. Dr. Fuladi.
Yeah, Dr. Fuladipa, you can start your presentation. Hello.
1 minute. Is my screen visible?
Yes, yes, go ahead. Yeah.
everyone. I am Kuladeva Patram. I am from Indian Institute of Petroleum and Energy. I am a first year PhD student here. My research work is on hybrid composite of carbon nanonium and zinc oxide tetra for high performance.
Excuse me, ma'am. Ma'am, your voice is not very clear.
Am I audible now? Hello?
Yes, ma'am, you are audible.
Now am I audible?
Yes, ma'am, you can proceed.
Yes. My topic is hybrid composite of carbon nanonium and zinc oxide tetrapods for high performance supercapacitor. First of all, as we know, the demand for long-term sustainable and durable energy storage devices has been increasing over global challenges and concerns associated with the energy and environment conservation. The main technological issue is to develop renewable resources based on highly efficient energy storage devices with good electrochemical performance. Now, my present study proposes an environment-friendly approach for facile large-scale synthesis of onion-like carbon nanoparticles and zinc oxide tetrapods for application in high-performance supercapacitors. This is the synthesis process of the carbon nanonions. We use the waste frying oil to synthesize carbon nanonions. We synthesize it, synthesize it 550 degrees. We synthesize it in waste frying oil and keep it in a furnace for 550 degrees centigrade to remove the amorphous carbon and unburned oil. And this is the same image of the carbon nanonions. You can see there is onion-like structure of the carbon particles. This is the synthesis of the zinc oxide tetrapods. Zinc oxide tetrapods are synthesized by flame transport synthetic technique. In this method, zinc particles and polyvinyl butyl powder was filled in a crucible and heated in a furnace for 30 minutes, 900 degrees centigrade, and then we collect the particles and these are the tetrapod-like structure. This is the same way, and you can see the structures. Then we synthesize the composite, the hybrid composite of zinc oxide tetrapod and carbon nanonium. We take carbon nanonium and zinc oxide tetrapod certain ratio in aqueous solution. Then we test it for 24 hours. Then resultant suspension was filtered and it was dried overnight with 50 degrees centigrade. You can see the carbon nanonium particles are arranged on the surface of the zinc tetrapod structure. This is the characterization part. This is the characterization part. The morphology of synthesized CNOs and the uh, zinc oxide and carbon anion tetrapod hybrid composite characterized during AM and HRTM analysis. Spherical and well dispersed carbon nanonions are observed in the low resolution low resolution TEM image. The size distribution pattern as evaluated statistically demonstrates that the carbon nanonions exhibit a really narrow size distribution in the range of 5 to 20 nanometer. Mostly the most of the particles are in 10 to 15 nanometer, 10 to 15 nanometer range. The 15, this is the high resolution TEM image of the zinc oxide tetraparticles showing the decoration of the carbon nanonions on the zinc oxide surface. The white surface there we can see the onion-like structure of the zinc surface. This is a structural characterization of zinc oxide and carbon nanonium hybrid composite. Here the FTI spectra of the carbon nanoniums, zinc oxide tetrapod and the composite are shown. The FTI spectrum of the carbon nanoniums exhibits the characteristics peaks of the graphitic carbon. We can see the doublet at 2,900 centimeter inverse, 2000 centimeter inverse, the CH stretching, C11C bending at 1600 centimeter inverse. Then we see the C single bond C stretching and CH bending vibrations in the spectra. And in the that zinc oxide tetrapod spectra is there. Zinc oxide at 500 centimeter inverse, and the figure C is the FTS spectra of the composite, and we can see there both the OH OH is for the which is the stretching vibration, always stretching vibration at 3500 centimeter inverse, and the XRT pattern. The XRT patterns were obtained to examine the composition and crystallinity of the PO zinc oxide tetrapod, carbon nanonions, and the hybrid composite. And this shows that both the carbon nanonion and the zinc oxide tetrapod exhibits a pure crystalline nature. The XRT pattern of the carbon nanonions present at the 002 pin and 100 1002 reflections of the carbon respectively. And then in the figure E, this is for the zinc oxide tetrapod XRD, and in the figure F we can see both carbon nanonium and zinc oxide tetrapod that depicted there. This is the XPS analysis where we can analyze to characterize the chemical composition of the synthesized material, and where we can synthesize material, where here we can see the zinc, carbon material, and the for oxygen. We did the XPS analysis. And the electrochemical, we make electrode with the zinc oxide supercap. We make the electrode for supercapacitor using this composite, and this work is going on. It is not completed, and we are still optimizing at which composition it is working best. Now I have done 1:5 and carbon nanonium and zinc oxide tetrapod ratio in 1:5 and 1:10 ratio, and this is the cyclic voltammetry data, and this is showing 8 millivolt current at 100 millivolt 8 milliampere current at 8 ampere current, 8 milliampere current at 100 millivolt scan rate, and I'm still working on this. Further optimization and modification, this hybrid composite can work as a very efficient supercapacitor with good electrochemical performance. Thank you.
Okay, thank you very much, Fuladipa, for your nice presentations. So, anybody have any questions?
Hello.
Yes, yeah, please go ahead.
What is the capacitance of your material?
This is the capacitance of the this is not the proper value. We are still working on it.
So till you are optimizing, right?
Yes, sir.
It's not experimentally till well proof, right?
Yes, and now we are working on it.
Okay, thank you. Any other question? Okay, so if no question, thanks to Fuladipa for your presentation. So we'll go to that next speaker. So the next speaker is Dr. Salini Raghunath, Department of Chemistry, CHRIST, CHRIST, deemed to be University of Bangalore. Title of the talk is bismuth ferrite nanoparticles decorated on graphitic carbon nitride sheets, a highly efficient electrolyte for hydrogen evolution reaction. So Dr. Salini, you can start your presentation.
Yes, sir. Thank you. Sir, is my slides are visible?
Yes, yes. Just make hide.
Sorry?
In your full presentation in bottom, you can see hide, stop sharing. So press in hide.
Oh, okay, sir.
Yes. Yeah, please.
Thank you, sir.
Yeah.
Good morning, one and all. The title of my work is Bismuth ferrite nanoparticles decorated on graphite carbon nitrate sheets, a highly efficient electrocatalyst for hydrogen evolution reaction.
Excuse me,
Another
ma'am. Can you speak a little louder because your voice is very low?
Hello, am I audible? Hello.
Yeah, ma'am, you are audible, but just speak little bit louder because we are not clearly hearing you.
Hello.
Yes,
Hello.
ma'am. Yes, ma'am.
Now you can hear me.
Yes, ma'am.
Yeah, okay, thank you. These are the contents of my presentation: introduction, methodology, characterization, and application. And as we all know, the perovskite form of bismuth ferrite is well-known multiferrite material with numerous applications like memory storage, sensors, photovoltaics, etc. But there have been very few reports on the bismuth ferrite electrodes for hydrogen evolution due to some of its drawbacks, and also graphite carbon nitride. It is a very well-known photo catalyst, and with its band gap of 2.9 electron volt, and due to their graphitic microstructures and high nitrogen functional group loading, can be efficiently used in several energy applications, which will enhance the electrochemical properties of the other materials also, so that we can modify other materials using graphite carbon nitride sheets. So here we have prepared one binary composite with bismuth ferrite and graphite carbon nitride to check their electrocatalytic activity towards hydrogen evolution reaction. The steps of the present work is first we have prepared the bismuth ferrite from the from the precursors, and we have modified the prepared bismuth ferrite using graphite carbon nitride, and we have analyzed the samples using different physicochemical methods to check their phase analysis and their purity, and finally we have checked their electrocatalytic activity towards hydrogen evolution reaction. Moving on to the methodology, this is the synthesis method that we have adopted for the preparation of bismuth ferrite. Here we have used hydrothermal technique for the preparation, and the precursors were bismuth nitride and ferric nitride, and the solution, the mixed solution, was kept in the Teflon lined autoclave for 6 hours at 200 degrees Celsius, and obtained resultant solution was filtered and dried to get the pure bismuth ferrite sample. And next is the preparation of graphite carbon nitride. For that we have used melamine as a precursor, and it was calcined at 550 degrees Celsius for 4 hours, and we got a product yellow colored powder, that is a graphite carbon nitride. And for the preparation of binary composite, we have used a calculated amount of these both components, that is bismuth ferrite and graphite carbon nitride, and it was mixed thoroughly for 15 to 30 minutes using hot ramp vessel, and we have calcined it for 400 degrees Celsius for 4 hours to get a final product, that is a BG, that is bismuth ferrite graphite carbon nitride binary composite. And characterization. These are the XRD, IR, and IR spectra and EG analysis done for the bismuth ferrite and the binary composite. From the XRD pattern, we can see the characteristic XRD peaks for the bismuth ferrite, which accords with the JCP 200169, and the preferential growth was the most intense peak is at 31.2, and for the binary composite also we can see the same XRD pattern, but the intense peak of the XRD pattern, the characteristic peak for GCN was not visible. It may be due to the lesser amount of the GCN that we have used for the binary composite. We have used lesser amount of GCN for modifying the bismuth ferrite. And from the FTR spectra, we can see the characteristic peak of the ferrite, that is at 520 and 438 for both the samples. And for the binary composite, the FTR spectra of pure GCN shows the broad band in the range of 1200 to 1700, which is ascribed to the stretching vibration mode of carbon nitrogen and carbon double bond nitrogen heterocycles, while the band at 810 centimeter inverse may correspond to the vibration estrizing structures in the GCN. And from the analysis, TG analysis, we can see the bismuth ferrite is stable till 50 degrees Celsius, and for the binary composite here, that is which includes the GCN, sudden weight losses there after 550 degrees Celsius, which can be attributed to the degradation of GCN. It can be oxidation of GCN to nitrogen or some other compounds. And this is the SEM and EDS analysis of bismuth ferrite and the binary composite. Figure A shows the SEM image of the bismuth ferrite, which can see the wafer-like structures of the bismuth ferrite, and the corresponding EDS shows the presence of bismuth, iron, and oxygen elements without any other impurities. And the figure B shows the composite and the 1 micrometer range, and the layer-like structures can be seen in between. And EDS, corresponding EDS shows the presence of carbon and nitrogen besides the bismuth, iron, and oxygen elements. And the table shows the elemental composition of both the samples, I mean bismuth and binary composite, without any other elements, impurities present in the sample. The application that we have done here is electrocatalytic vortex splitting, where the working electrode can act as both cathode and anode based on the applied potential. And we have used platinum electrode as a counter electrode, a reference calomel as the reference electrode, and the catalyst coated on glassy carbon electrode as a working electrode. And to the right, we can see the working electrode preparation. We have used nephene, ethanol, and distilled water with our catalyst for the good dispersion and the binding of the material. And we have sonicated it for 30 minutes, and the sonicated catalyst ink that we have drop casted on the glassy carbon electrode and used for the further electrochemical studies. These are the results that we obtained from the hydrogen evolution reaction. From the LSV curve, we can calculate the overpotential at which the reaction is happening. Then the overpotential for the binary composite is 148 millivolt at 10 milliampere per centimeter square. So it is better that, so we can say that where the second image shows that for bismuth it is about 570 millivolts. So we can say that our catalyst is binary catalyst is a good electrocatalyst.
Excuse me, ma'am. Ma'am, you have only 1 minute to conclude.
Okay, I will. Then the Duffel slope confirms the mechanism of the reaction followed, and from the slope of the binary composite, we can confirm that the mechanism formed Volmer mechanism. And from the AC impedance, we can see that the binary composite is having lower solution resistance and the charge transfer resistance. So we can say that the electrical conductivity is more for the electrocatalyst. We have achieved the overall water splitting by using the two electrode system, and from the graph you can see that only 1.9 volt cell potential is required to reach to 10 milliampere per centimeter square, and we have used the same potential for long-term durability test, and after 2 hours it is showing a good stability. And we have calculated the electrochemical surface area using CV technique in the non-Faraday region, and we have calculated the double layer capacitance and plotted against scan rate, and more slope is obtained for the binary composite, which confirms a better electrocatalytic activity of the composite. So we can conclude that we have efficiently prepared and binary composite via calcination method and characterized using different discrete methods. And the electrocatalytic activity towards hydrogen evolution reaction was done, and over potential of 148 millivolt at 10 milliampere per centimeter is obtained. And we are again trying to prepare some ternary composite using this material, so that we can get a better electrocatalyst which can be used for the further work. These are some of the references that I have used for my work. Thank you.
Okay. Thank you very much, Dr. Salini, for your nice presentation.
Thank you.
Now, question from audience. Any questions? Okay, so we have it. We'll go.
Can I stop?
Thank you, Dr. Salini.
Thank you, sir.
Nice presentation. Audience can maybe communicate with Dr. Salini for if you have further query. Okay, so the next presentation is Dr. Prithu is from SRMIST, Tamil Nadu. The talk title is Exploring the Growth and Properties of Van der Waals Graphenes or MOS2 heterostructure for Photodetector application. Please go ahead for presentation, Dr. Prithu.
Okay, thank you, sir. Can I share the screen now?
Yes, go ahead.
So is it visible, sir?
Yes, yes.
Okay, so myself, Preeti Satish, and I'm working as a junior research fellow under the guidance of Dr. S. Chandramohan, SRM Institute of Science and Technology, and my proposed work is on exploring the growth and properties of van der Waals graphene MOH2 heterostructures for the photodetector application. So the outline of my presentation will be, I will start with the introduction about the 2D materials, and we'll move on to the heterostructures, and we will talk about the current status of the topic. So basically, I will start with the 2D materials, and it's basically nothing but an atomically thin materials which consisting of one or more layer of atoms with a strong in-plane covalent bonding and a weak out-of-plane van der Waals forces. So actually, the discovery of the first 2D material, that graphene, by Andrej Jim and K.S. Navaslev in 2004 by means of the mechanical exfoliation has stimulated the quest for other layered van der Waals structures also. So that has resulted in the experimental synthesis as well as the theoretical prediction of other layered structures with the diverse properties. So this picture actually represents some of the currently discussed 2D materials. So as I mentioned, what are the properties that makes the graphene, which is a star material of the 21st century, is that of it's only having a single atomic layer thickness, having a zero band gap material, and it is having high electronic mobility of about 2 lakh centimeters per volt per second, and having high electrical conductivity as well as one of the strongest material ever known. So as I discussed, among this class of the 2D materials, we are particularly interested in the transition metal dichalcogenates, which is having a general
Okay, I will start. Hello, hello, Dr. Preeti.
Yes, ma'am.
Your voice was stuck in between.
Okay.
Present. Yes, yes, you
Is it
can.
audible, ma'am? Ah. Okay, so instead of going with a single material, we know that if we take a particular material, each material is having some unique properties. So the question is, what about combining all those properties in one unique material? So that idea led to the formation of heterostructures. So we can either make a vertical van der Waals heterostructures, or we can also go with the horizontal one. So here we are interested in the vertical van der Waals heterostructures, which is made of stacking different 2D crystals on top of each other, which is held together by means of a van der Waals forces. So here we are interested in the graphene MOH2 vertical heterostructures. So these heterostructures can be either formed by means of a top-down approaches like a mechanical exfoliation or like a CVD. Because even though the sample which has been prepared by the mechanical exfoliation will give you a good quality, in the practical application sense, when we are going to the industrial level, it may not be that much applicable. So we will go with the chemical vapor deposition, which will provide you even an approximately greater grain size as well as a high controllability. So the question is why we insist heterostructures for photodetectors. Photodetectors is nothing but a device which can actually convert a light energy to that of electrical energies. Even though the photodetectors based on the customary semiconductors like silicon or a gallium arsenide has also been investigated, but in their case, the spectral bandwidth limited by their band gap actually demands photodetectors for different spectral regions. So, and in addition to that, the stiffness in the bulk semiconductors also hinders the development of a flexible photodetectors. So, even if we in the graph we can see that comparing to the conventional photodetectors, the photodetectors made of the heterostructures can even provide you high responsivity within a very short response time. And on the other hand, for the graphene, the wavelength independent light absorption that enabled by this gapless energy dispersion in graphene can actually make it as a great potential application in the case of broad range photodetectors. But even though still this graphene has some limitations, like it's definitely having a zero band gap, and also it is having a short photo carrier lifetime. So in order to what to say, make it use in the case of photodetectors. Several other methods have also been investigated, like integration of quantum dots with graphene structures, etc. But as I have mentioned, the discovery of this wafer scale growth of this transition metal dichorcogenates has actually opened up so many opportunities to integrate with graphene, so that we can increase the responsivity as well as the photo response of these types of photodetectors. So in our case, we will focus on this graphene MOS2 photodetectors, in which the MOS2 can displace a strong light matter interaction, whereas the graphene will act as a tunable work function electrode. So we are going to work on this particular topic, and we have to know what are the outputs that we are getting from this, and we are expecting that we will get a better outcome than that of the existing photodetectors now. So that's all about. Thank you.
Okay, thank you, Prithu Satish, for your nice presentation. So now question from audience. Okay, so if no question, thanks, Prithu. So we'll move to that next presenter.
Okay, thank you, sir.
Yeah, thank you. So next presenter is Dr. P. Naga Maleswari, Department of SNH, VFSTR, deemed to be University, India. Uh, Title of the talk is Double Dope GD3 plus Y2 plus rare earth metal ions effect on ZNO nanopowder, heat treated at different temperature and its multifunctional properties.
Good morning, sir. Shall I start my
Yes,
presentation?
yeah, please start it.
Is it visible, sir?
Yes, do the full screen and start.
Okay, sir. Is it okay, sir, now?
Till not its full screen mode. In right side bottom, you have a full screen mode option.
Full screen.
Yes, you can see that there you can increase that size of your screen and then just left side. Just bottom corner, right side. We cannot see your cursor also. Yes, yes. Go to that right bottom. Yes, yes.
It is okay, sir?
Ma'am, actually, if you will click on share entire screen, then only we can see your whole screen. When you are clicking on share, that time you click on share entire screen, then you
Okay.
present.
Yes, that
Okay, okay.
you need to do that. Yeah. Maybe you can close and again share entire screen.
Okay, sir.
You can close your presentation and again open with share entire screen.
The directory is not in. Now it is okay, sir?
Yes, yes. Go ahead. Yeah.
Good morning, one and all. Myself, T. Nagamallishwari, research scholar, Division of Physics, Department of SNH, Vignan's Foundation for Science, Technology and Research, deemed to be University of Vadlamudi Guntur, Andhra Pradesh, India. On behalf of ICN 2022, now I want to present my research work on double doped gadolinium and yttrium direct metal ions effect on zinc oxide nanopowders heat treated at different temperatures and its multifunctional properties. These are the contents of my presentation: introduction, synthesis of the samples, results and discussion, and conclusions. Basically, zinc oxide material has multifaceted applications in the fields of optronics and electronics, basing on the special structural, ferroelectric, and electronic properties due to its large energy band gap of 3.34 electron volts and the excitation wavelength of 60 milli electron volt. And there are many possible methods are there to prepare the zinc oxide nanoparticles. Among them, some are solvent method, hydrothermal method, and chemical synthesis methods. Among them, solvent process is a versatile solution process for making advanced materials and the most promising production technique to prepare the zinc oxide nanoparticles in nanotechnology. In our present study, gadolinium and yttrium double-doped zinc oxide nanoparticles are presented from Sol-Gel method using PVA as chelating agent and annealed at 500 degrees centigrade to 1000 degrees centigrade with a step size of 100 degrees centigrade to study its physical properties in few of the device applications. These are the flowchart for the preparation of double-doped zinc oxide nanoparticles. First, we took zinc nitrate and gadolinium nitrate and yttrium nitrate separately in 3 beakers and dissolved them in a deionized water. And after that, the cationic solution was steeped for 2 hours, added PVA as chelating agent, and dehydrated it around 100 degrees centigrade with a constant and continuous stirring rate of 700 rpm till the gel is formed. After that, the gel is placed in a hotter oven at 170 degrees centigrade for 10 hours. We'll get a dry powder, and we grind that dry powder a minimum a time of half an hour. Finally, we'll get the double-doped zinc oxide nanopowders, which we labeled as ZgYO nanoparticles. For this, we'll go for results and discussion. These are some characterization techniques which we done for my research samples: X-ray reflection, scanning electron microscopy, energy dispersive spectroscopy, transmission electron microscopy, FTIR, DRS, photoluminescence, magnetic and mechanical studies. Firstly, I'll start with the X-ray diffraction pattern. The figure A shows the XRD patterns of the annealed double-doped zinc oxide nanopowders from 500 degrees centigrade to 1000 degrees centigrade, and figure B shows the prominent peaks of 100, 002, and 101. From figure B, we can clearly identify the crystallinity has been increased with increasing the annealing temperature. From these figures, and the figure showed broad intensity peaks corresponding to the hexagonal Lugite phase at 100, 002, 101, etc. respectively. So the crystallite size has been found using Debye-Scarrer formula. It is found to increase with increasing annealing temperature. So the line broadening of the diffraction peaks confirmed that the synthesized materials are in nano resin. By using of this XRD data, we can calculate crystallite size, lattice parameters, distortion factor, value, U parameter, and bond length. And here we observe that the lattice constant, value, U parameter, bond length, and distortion factor has a little change will be takes place. And at crystallite size, from 500 degrees centigrade to 1000 degrees centigrade, a random variation of increase of crystallite size has been observed. It is from 14 nanometers to 46 nanometers. And this is the same micrographs of the prepared double-doped zinc oxide nanopowders from 500 degree annealing temperature to 1000 degree annealing temperature. These images will show at low magnification, which will show the spherical geometry of the prepared nanopowders. And the crystallite size has been found to increase with increasing annealing temperature. By using this, we can calculate the porosity and the porosity incongruence with that of the density of the samples. And also we are calculate the density of the samples by using Archimedes water displacement method. And this tabular form will give the complete information about experimental density, theoretical density, relative density, and porosity. And we found that at 500 degree annealing temperature, the relative density will be 99%, and at 700 degrees centigrade, it will be 92%, and the porosity will be incongruous with that of the relative density of the prepared double-doped zinc oxide nanopowders. And these are the EDS profile of the prepared double-doped zinc oxide nanopowders. Basically, EDS is used to find the chemical composition of the prepared material, and it will clearly shows the presence of zinc, oxygen, gadolinium, and yttrium ions, the synthesized ZgYO nanopowders. And below tabular form will give the atomic percentage and weight percentage of the prepared double-doped zinc oxide nanopowders. And here we observe that the 100% purity samples will be prepared by the using Sol-Gel method. And these are the 10 pictures of the prepared double-doped zinc oxide nanopowders. And here we show the figures from A to F And figure A will show the annealing temperature of 500 degree sample, and figure D and E shows the annealing temperature of the 900 degree sample powder. So basically, TEM is used to find the accurate particle size of the nanoparticles. And here we observe the better clarity on the microstructures of the samples was obtained from transmission electron microscopy, and which shows the spherical shaped particles. And the computed size of nanoparticles at 100 nanometer and 10 nanometers range resolution from TEM at the annealing temperatures of 500 and 900 degrees centigrade has been found to be 14 nanometers and 44 nanometers for the prepared ZgY1 nanoparticles. And this will be exactly matched with the study of the XRD in the previous results. And this is the FTIR profile for the prepared double doped zinc oxide nanopowders. And this will be studied at room temperature in the range of 400 centimeter inverse to 4000 centimeter inverse. From the figures, a very strong and broad absorption peak will be occurred at 3000 centimeter inverse. It was attributed to OH structuring vibration in the hydroxyl group was seen in all the double doped zinc oxide nanopowders. And the peak had 1376 to 1395 centimeter inverse and 1439 to 1514 centimeter inverse was assigned due to the presence of carboxyl group. The symmetric and asymmetric C double bond was stretching mode of vibration was takes place in all the prepared zinc oxide nanopowders. And it is exactly matched with the literature. And due to the double doped rare earth ions in the zinc oxide lattice, a defect is arised at 861 to 879 centimeter inverse. And this is a diffuse deflectance spectroscopy study of the prepared samples at room temperature. And here, the absorption peaks located at nanometers by increasing 500 degrees centigrade to 1000 degrees centigrade. And by using of this, we can calculate the energy band gap of the prepared materials. And the energy band gaps will be 3.32 electron volts, 3.29, 3.18, 3.12, 3.07, and 3.0 electron volts respectively for annealing temperatures of 500 degrees centigrade to 1000 degrees centigrade. And here we observe that a slight decrease in the optical band gap from 3.32 electron volts to 3 electron volts in the studied materials with the increasing annealing temperature from 500 degrees centigrade to 1000 degrees centigrade was observed. It is because of the inducing of the highest ionic amount of ionic radius of the materials of gadolinium and yttrium will be substituted in the host zinc oxide lattice. Maybe due to this reason, the energy band gap will be decreased from increasing the annealing temperature from 500 degrees centigrade to 1000 degrees centigrade. And this is the photoluminescence spectrum for the prepared double doped zinc oxide nanopowders at an excitation wavelength of 272 nanometer, 320 nanometer, and 620 nanometers. The figure A shows the excitation wavelength of 272 nanometer, and this is for 320 nanometers, and this is for 620 nanometers excitation wavelength. At 272 nanometer, we identified two emission peaks at 544 nanometer and 670 nanometer range. And the peak at 544 nanometer is associated with the enhancement of green emission, which is owing to the oxygen vacancies formed at the surface of the material and due to the zinc interstitials. And the peak at 670 nanometer led to orange and red emission. And at the wavelength of 320 nanometers, we identified only one major peak located at 679 nanometers from all the annealing temperatures from 500 degrees centigrade to 1000 degrees centigrade. It is due to red emission. And figure C shows the excitation wavelength of 620 nanometers, and it will show four major peaks, which is located at 272, 310, and 367 to 379, and 514 to 524 nanometers. So the peaks at 272 is due to the electronic transitions of the rare earth metal ions, which is substituted on the zinc oxide host lattice. And the 310 nanometers is due to the emission of gadolinium transition. And so if the peak at 310 nanometers is due to the emission of gadolinium 3+ ion transition. So the type of materials which are used in luminescent materials due to its excellent chemical stability. And the next peaks are located at the position of UV emission for various annealing temperatures of double doped zinc oxide nanomaterials. And the peak at 514 nanometers to 524 nanometers is due to green emission. It is due to the oxygen vacancies located at the surface of the zinc interstitials. Due to the photoluminescence results, these type of material, prepared materials, are used in luminescent materials, and due to the
Excuse me, ma'am, can you please conclude?
Okay. From this type of materials will be used in the white LED applications, and these are the magnetic studies. These images will give the complete information about the magnetic properties of the prepared double doped zinc oxide nanoparticles from 500 degrees centigrade to 1000 degrees centigrade, which will shows the room temperature ferromagnetic property. And these are the retentivity, coercivity, squareness factor for the prepared double doped zinc oxide nanopowders. And lastly, we'll go for mechanical studies of wear resistance and friction coefficient. And the wear resistance and friction coefficient will be increased with increasing annealing temperature by the values of coefficient of wear and coefficient of friction. The coefficient of wear and coefficient of friction will be increased with increasing annealing temperature, and the coefficient of friction will be decreased with increasing the annealing temperature. So by using of this type of magnetic properties, these type of prepared nanoparticles may be used for the self-lubricating materials. Now I'm going to concluding my work. The prepared gadolinium and yttrium doped zinc oxide nanoparticles have been synthesized from Sol-Gel method using PVA accelerating agent, and the nano size of the particles was confirmed by XRD and TEM, and the XRD peaks confirmed the hexagonal Urgite structure, and semi-micrographs indicates the spherical geometry of the particle. The crystallite size was increased with increasing annealing temperature, and the EDS results confirms that there is no presence of impurity in the prepared nanoparticles, and the FTIR study for the studied nanoparticles established the presence of absorption peaks of the zinc oxide nanopowders, and 10 pictures have revealed the particle size similar to that of XRD study. And the above studies discuss the influence of annealing temperature on the structure, morphology, and composition. Room temperature ferromagnetism was observed for the prepared samples. So the prepared materials are subjected to mechanical studies of wear resistance and frictional coefficient to understand the effect of annealing temperature. So by using of the magnetic and mechanical studies, the prepared double doped zinc oxide nanoparticles may have a good potential to be used in spintronics as well as self-lubricating materials. Thank you, one and all.
Yeah, thank you, Dr. Manesuli, for your nice presentation. So any question? Just maybe one question. Okay, so if no question, we are going to close this session because we have time limit. So thank you very much to all audience to attend this session. Okay, thank you very much.
Thank you, sir.
I would like to thank Dr. Tuhin Subra for patiently chairing the session. So thank you for giving your valuable time.
Yeah, thank you very much.
So for the next session on hybrid nanostructures, I would like to invite Sushmita Das, Department of Chemistry, MIT Institute of Applied Sciences, MIT University, West Bengal, and Kanchan Pathak, Daisy Wadia, College, Pune, Maharashtra, India.
Yes, thank you, ma'am. This is Dr. Kanchan Phatak. Is the other chairperson there?
No, ma'am. Ma'am, please, can you chair the session?
Yeah, okay, thank you. So this session is on hybrid nanostructures. There are going to be 5 short talks on it. So I welcome our first speaker of this session, Dr. Naveen Goyal from Materials Research Center, Indian Institute of Science, Bangalore. His topic of presentation is ion exchange reaction mechanism to engineer hybrid nanostructures. So Dr. Naveen Goyal.
Excuse me, ma'am. Ma'am, till now I can't see Naveen Goyal has joined. We can start with the next presenter. Meanwhile, if he will join, then we can ask him to present.
Okay, so is Dr. Bindya Basani Mishra is here?
Yes, ma'am.
Okay, so I welcome Dr. Mishra. She is from Center for Nanoscience and Nanotechnology, ITER, deemed to be University, BBSR, Odisha, India. And her topic of presentation is optical and magnetic study of Mg substituted zinc magnite nanoparticles. Ma'am, you will have 10 minutes. You can please start with your presentation. Thank you.
Yes,
Please share your slides. Yeah.
yes, ma'am. Ma'am, I think it is visible.
Yeah. You can just slideshow. Yes. Yeah.
Ma'am, now it's okay?
Yeah. Thank you. You can start.
Yes, ma'am. Okay. First of all, I would like to thank to the organizer for giving me such an opportunity to deliver my talk on this big platform. And myself, Bindhyavasini Misra, PhD research scholar from SOA, deemed to be university. And today my topic is on structural and optical study on magnesium substituted zinc manganate nanoparticles. So these are my plan of talk where I would like to introduce about spinel structure and zinc manganate, then some of the application and properties of zinc manganate, then the synthesis procedure we have adopted for prepare the zinc manganate, and some of the result and discussion, final the conclusion. So I would like to start with the spinel oxide structure, and this crystal structure is first described by Brax and Nishikawa, and the general formula of spinel oxide structure is AV2O4. Okay, where the A is basically divalent cation. Some of the examples are magnesium, chromium, manganese, cobalt, nickel, and so on. And B is trivalent cation in nature, such as aluminum, gallium, indium, titanium, and so on. And here this structure contain tetrahedral and octahedral holes. That means a single oxygen atom is surrounded by 4 cation, that is called tetrahedral hole. When the single oxygen atom is occupied by 6 cations, it is called octahedral holes. And basically the A cation is occupied at the tetrahedral holes and B cation is occupied at the octahedral holes. So depending on the type of metal atom occupied at these sites, this can be classified into 2 types, this spinel oxides. One is normal spinel structure and another one is inverse spinel structure. So in case of normal spinel structure, the A cation is occupied at the tetrahedral side, B cation is occupied at the octahedral side, and oxygen is occupied in FCC lattices. And some of the examples is zinc ferrite, cadmium ferrite. But in case of inverse spinel structure, the A cation is occupied at the octahedral position and B cation is occupied in both tetrahedral and octahedral position. And example of inverse spinel is nickel ferrite and cobalt ferrite. Now come to the zinc manganate, which is our base material. Basically, zinc manganate has gained attention in nowadays due to its unique structural, electrical, and mechanical properties, and it is normal spinel structure. And it is tetragonal structure with 1:1 AMD space group, where the zinc is occupied at the tetrahedral position, manganese is occupied at the octahedral position, and oxygen is occupied at the FCC lattice. And in a single unit cell, there are 8 tetrahedral sites, 16 octahedral sites, and 32 oxygen atoms are there. Different approaches are have been made to prepare the zinc manganate nanoparticle, like salt gel autocombustion, co-precipitation, hydrothermal, polymer pyrolysis method, and so on. And some of the application of zinc manganate, it can be used in lithium-ion batteries, sensors, supercapacitors, in catalysis, memory devices, and electrodes. And the basic, if we call the basic properties of zinc manganate, it has high theoretical specific capacities, excellent heat resistance, good chemical stability, and it is also low price and environmental friendly. So to overcome the recombination process as well as to improve the structural, optical, and magnetic behavior, doping is always an excellent method to be adopted. So in our work, we have taken magnesium as a doping material, and we have doped magnesium in place of zinc, and we have prepared this material using salt gel autocombustion method. So this is my synthesis procedure, where we have taken 100 ml DI water in which the acetate precursor is added. Then the citric acid is used as a chelating agent, and the solution is stirred continuously at 120 degrees Celsius under continuous stirring till the milky white solution. Then the autocombustion is taken place at 220 degrees Celsius for 3 hours. After grinding that sample, we calcine that sample at 500 degrees Celsius for 4 hours. Finally, the zinc manganate nano powder is obtained. So we have prepared 6 series of samples where we have changed the concentration of magnesium from 10% to 50%. And for our convenience, we have naming the material as ZMO, MZMO 1, 2, like this. So for the confirmation part, we have first taken, these are my result and discussion. For the confirmation, we have first taken the structural analysis through XRD, where the pure phase zinc manganate is obtained, and we have also match with it with the JCPDS file using the foolproof software. And as we can see, there is no extra impurity peak is obtained for any of the doping materials. So we can say that pure phase zinc manganate and magnesium doped zinc manganate nanopowder is obtained successfully. And the 211 is the characteristic peak of the material, and we have observed that there is a rate shift in the main characteristic peak, and this may be due to the doping of magnesium in place of zinc. And here we have calculated the crystallite size using the device error formula, and we have found that the with increase of doping of magnesium, there is an increase in the crystallite size from 21 nanometer to 25 nanometer. Okay, so the next one is our Raman analysis, where in case of zinc manganate, there are total 10 active Raman modes are present, but in our case, we have obtained only 3 modes. Okay, A1G, EG, and B2G. Okay, here the A1G mode is due to the symmetric breathing of the AO4 tetrahedron, and the B2G mode, this is the lowest mode, lowest frequency mode, and this is due to the BO6 octahedron. Similarly, the EG mode is due to the symmetric bending motion of oxygen within the AO4 lattice. As you can see here, the table, we can see that the Raman modes are slightly blue shifted in case of doping materials. So we can conclude that magnesium is replacing zinc successfully in case of our material. And next one is our optical studies, where we can see that the magnesium 10% doping of zinc manganate have the highest observance in case of UV region, and all other materials have lowest observance from the pristine zinc manganate material. And when we calculated the band gap from the Tau-C relation, we have found that the band gap is decreases from 1.76 electron volt to 1.68 electron volt when we doping magnesium in place of zinc. Okay. And this is my magnetic study, where the room temperature VSM is take place, and we can see that there is paramagnetic material with a very slight change in magnetic susceptibility and magnetization. And these are my conclusion, where the pure phase magnesium substituted zinc manganate is obtained successfully with average particle size of 25 nanometer. Out of 10 Raman active mode, we have find 3 modes were present in our case, and the shifting of Raman modes confirm the substitution of magnesium over zinc. And the observance graph also proposed that magnesium 10% doping having the highest observance, where there is a decrease in band gap with an increase in magnesium doping, and the room temperature magnetization study revealed the paramagnetic nature with no hysteresis loop. And these are some of my references. Thank you.
Thank you. Any questions? We can take one question. Okay, so if there are no questions, I thank Dr. Mishra for her nice presentation. Moving
Thank you,
on,
ma'am.
the next speaker that we have is Dr. Gaurav Gupta from Department of Physics and Astrophysics, University of Delhi, India. And topic of his presentation is correlation of electron density defects with magnetic behavior of Z and MGU nanoparticles. Dr. Gupta? You're on mute.
Okay, so is my screen is visible?
Yes.
Okay. Thank you. So, hi, good morning to all of you. Myself, Gaurav Gupta. I'm pursuing PhD in physics from University of Delhi, and my title of presentation is Correlation of Electron Density and Defects with Magnetic Behavior of Zinc Magnesium Oxide Nanoparticles. So, the outline of my presentation, I will give an introduction of zinc magnesium oxide nanoparticles, and which will be followed by the nanoparticle synthesis and the characterization techniques, and followed by the summary. So the objective of my research work on zinc magnesium oxide is to analyze the microstructural properties through rate-world refinement of XRD data and Raman spectroscopy technique, and also see the effect of Mg incorporation on the phonon mode behavior of the host lattice zinc oxide, and to see how the defects will be incorporated with respect to the Mg dopant, and which will be investigated using the rate-world refinement technique, Raman, and photoluminescence. Also, the effect of Mg composition will be seen on the room temperature ferromagnetism. So there are some advantages versus and issues with the zinc magnesium oxide material. First one, the here the zinc oxide is the host lattice which is having a woodside structure, and while the magnesium oxide, which is my alloying lattice, or I can say the dopant lattice, which is having a cubic structure. So the zinc oxide has strong radiation hardness and high stability due to its high binding energy, and also, as we can see in the left hand side figure, the zinc oxide is having a band gap of around 3.3 electron volt, while magnesium oxide is having a band gap of the order of 7.8 electron volt. So with the alloying of magnesium oxide into the zinc oxide, so its band gap can be changed from zinc 3.3 to 7.8 electron volt, which is high application in UV photodetector application. And the issues with this material is the thermodynamic solubility of magnesium and zinc oxide is around 4%, and also due to the different crystal structure, the wide miscibility gap exists, and also the high UV to visible rejection ratio. So I have used the solid state reaction route method to prepare my samples. First, the solid state reaction method is a shake and bake technique in which, firstly, the high quality standard samples are taken and they are weighed in a stoichiometric amount, and they are mixed using either the agate mortar pistol method, or I can say the ball milling method. And after mixing, they are giving the heat treatment that is called the calcination. So solid state reaction includes two methods. First one is the agate mortar pistol method, and second is the ball milling. So I have chosen the ball milling over agate mortar due to that in ball milling the uniformity in the particle size is very high as compared to agate mortar. And ball milling is a top to down approach. It is easily handleable. It includes three stages. For the first stage, the elementary constituents, that is the precursor, are taken, and in the transitory process, or in the mediocre stage, somewhere in the fracturing process is occurring, and somewhere in the fusing process is occurring, and in the final stage the particles formed in the nano crystalline stage. Ball milling depends upon some parameters, the temperature, the milling media, the presence of the ball to powder ratio, and what is the incident frequency or the kinetic energy is giving to the balls. So I have chosen this solid state reaction route since it is a reproducible technique, it is an inexpensive technique, and the large quantity of the powder can be easily obtained. Here, the zinc oxide and magnesium oxide powder purchased from the Sigma Eldritch are taken, and they are weighed in the stoichiometric amount, and they are transferred into the jar along with the ball to powder ratio, which is around 10:1, and distilled water is chosen as media, as I can see in the right hand side figure, in which the balls and balls are present in the jar and with the powder. So the mixing is done at 18 Hz frequency using NQM 0.4 liter ball mill, and this mixed powder is oven dried for 12 hours at 100 degrees Celsius, and this amorphous zinc magnesium oxide nano powder is converted into a crystalline nanoparticles by giving the calcium heat treatment at 1000 degrees Celsius for 12 hours. The phase analysis was studied using the X-ray diffraction, in which in the left hand side figure, which is the XRD pattern, and the woodside structure is still maintained up to the 20% composition of magnesium, but for 15 and 20%, the phase segregation occur. As I can see, the magnesium oxide secondary phase peak is coming around 43.5 and marked as a star, which indicates the maximum solubility of magnesium and zinc oxide around 10%. I have used the rate-world refinement process to obtain the microstructural information, which uses a more peak shape function to calculate the Y calculated intensity, and the difference between the Y calculated and the Y observed is minimized using the least square algorithm. I have used the foolproof software which uses the Gauss-Newton algorithm to do the minimization, and then the crystal structure is refined, and the following information can be obtained. The quantitative phase analysis can be done. The latest parameter, the atomic occupancies, and especially the bond length, bond angle, and oxidation state can be calculated using that. I have used the pseudo-Voigt peak shape function, which is a mixture of Gaussian and Lorentzian peak shape function. In this, the eta represents the fraction, and there are two factors on which the fitting depends. Fitting of this X-ray diffraction reticle refinement process depends, which is the one is RWP and another is the R experimental. RWP defines the quality of data, and R experimental defines the convergence of data, and the ratio of these together defines the goodness of it. The obtained parameters are listed in this table, where the goodness of it is around observed to be around 2 and 3, which indicates the best fitting, and also the estimated bond length decreases shows a decreasing behavior with the composition X, and the G naught represents the change the oxygen site occupancy, and delta G naught represents the change in the oxygen site occupancy, and the value is found to be high or positive for the 5% magnesium composition, which indicates the formation of defect oxygen vacancy concentration in high amount, and also the lower value of a cation oxidation state for supports V naught. So the effect of Mg composition is seen on the structure lattice parameter. First one is the C. So change in C parameter is very high as compared to the A parameter, which is around 0.4%, and as I can see, the variation between 15 and 20% is very less. So which describes or which demonstrates the phase segregation, and this behavior is fitted using the second order polynomial, which is written by this equation y equals to 5.20913. So this equation can be further used to determine the composition X. Simultaneously, the C by A parameter deviates from the ideal value for all starting from the pure zinc oxide and also for the magnesium incorporated sample, which indicates the increase of ionicity in the sample, since C by A ratio is directly proportional to the difference in the electronegativity of cation and anion. And also the U parameter, which is the position parameter in the ZnO4 tetrahedra in the Z axis, so that the standard value is around 0.375. So the deviation is higher for 10% sample, so which indicates maximum distortion in the bond, since the tetrahedra will flatten in the basal plane. As I can see, the distortion value is high for 10%, and also the bond angle is very high. So the morphology, this is the morphology of the zinc oxide, magnesium oxide nanoparticle. So the X-ray density is observed to be very high for 15%, as we can see from the SEM images. So the Raman spectra, it includes two type of modes. There are two type of Raman modes. One is the polar mode, and other is the non-polar mode. The non-polar mode is the E2 low and E2 high mode. In E2 low mode, the atoms vibrate in the opposite direction. In E2 high mode, the atoms vibrate in the same direction. E2 low mode represents the zinc sublattice, and E2 high mode represents the oxygen sublattice. The presence of zinc, I am replacing zinc by magnesium, so which is confirmed through the formation of this local vibrational mode, which is occurring in the Raman spectra around 510 centimeter inverse. So the variation in E2 high and E2 Raman modes are represented in this figure. So the change in peak position of E2 low and E2 high mode, as in the D figure, up to 15%, it is a linear variation, but between 15 and 20%, the variation is very less, so which indicates the phase segregation, and the broadening E2 high mode is very high, so which indicates the random substitution of magnesium and zinc oxide. And there is also a FWHM variation in E2 low mode, which indicates which confirms the substitution of magnesium atom on zinc site. So I have used the spatial correlation model, which is used to probe the microstructural disorder. So in which so this is my formula of the spatial correlation model, and due to this disorder, a redshift in the phonon frequency can occur, and also an asymmetric broadening in the phonon peak can also occur. So I have fitted the E2 high mode, which represents the oxygen sublattice. So I have estimated the oxygen vacancy concentration using this spatial correlation model. So the correlation length L describe the distance between the defects, and which is observed to be very lower for 5% composition, and the oxygen vacancy is calculated using this n equals to 3 by 4 pi L cube, so which is the inverse of correlation length. And
Excuse me,
in the right,
sir, can you conclude in next 1 minute or 2 minutes?
okay ma'am, so the oxygen vacancy concentration is observed to be very higher for this. So this is my pair distribution function. So the estimated bond length is observed to be very in similar as compared to the Ritwell refinement process. So the variation in first peak width is observed to be higher for 10% sample, which indicate the zinc vacancy formation in very high amount. So this is my room temperature ferromagnetism. In the high magnetic field region, it actually shows a mixed behavior. In the high magnetic field region, it shows a diamagnetic behavior. In the low magnetic field region, it shows a ferromagnetic behavior at the room temperature, as we can see in the right hand side figure. So I have correlated the hysteresis loop area with the electron density values. So the hysteresis loop area is very high for 10% composition, and the electron density value for zinc and oxygen is very lower. Since the lower electron density values means the overlapping between the orbitals is very less, so which contributes to the formation of unpaired electrons, and which indicates the formation of some net magnetic moment. Actually, zinc oxide is a diamagnetic material, but with respect to incorporation of magnesium and zinc oxide, it shows some ferromagnetism behavior, and this all correlates with the zinc vacancy formation. And I have confirmed the zinc vacancy formation through the PL spectra, which is having a violet emission peak. And this is my summary. So zinc magnesium oxide particles are synthesized using solid state reaction technique, and maximum solubility is achieved and confirmed through XRD pattern refined analysis and phonon mode behavior. Oxygen vacancy information is obtained through change in oxygen site occupancy, and zinc vacancy information is obtained through Ritwell refinement, analysis of first week of pair distribution function, and PL spectra. Room temperature ferromagnetism is correlated with the low electron density values of cation and anion. Thank you for all. Hello. 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 Hello.
Yes, sir. Yes, sir.
Yes, I have finished my presentation.
Okay. Okay. Audience, can you? Is there any questions? Excuse me, Dr. Kanchan.
Our talk as usual is full.
The chair, Dr. Kanchan, is there. We can't hear you. Dr. Kanchan, we can't hear you.
We can start
At present, can you hear that?
And Dr. Gaurav, can you hear Dr. Kanchan, ma'am, who is the chair of the session?
She's speaking something.
Ma'am, I can't hear Kanchan,
Yeah,
ma'am.
we also can't hear. She is speaking something, but we are unable to hear.
Type in the chat box.
Okay, on behalf of the chair, I would like audience to ask some questions if they have any discussions. Thank you, sir. There are no more questions, it seems. So we will move on to the next presentation. I would like to invite Princey Francis, Department of Physics and Center for Research, St. Teresa College, Ernakulam. She will be presenting on a comparative study of the thermal diffusibility of hybrid nanofluid of AuSiO2.
Yes, ma'am, I'm here.
Ma'am, can you please make it to full screen?
Yes, I'm trying. Are you able to see it now?
Yes, ma'am.
Are you able to see
Continue.
now?
Yes, ma'am.
Okay. Good afternoon, and I present before the committee my work on a thermal comparative study of the thermal diffusivity of hybrid nanofluids of gold silica and gold borax. In my presentation, I would like to give you an introduction to nanofluids, the significance of nanofluids in current research and various applications, and also an idea on the thermal diffusivity measurement of gold silica and gold borax hybrid nanofluids using photothermal lensing technique. Now, it was in the year 1995 that Choi et al. Reported enhancing thermal conductivity of fluids with nanoparticles. He proposed that nanometer sized metallic nanoparticles can be suspended in industrial heat transfer fluids such as water, ethylene glycol, or engine oil, etc., which can function as a new class of engineered fluids with enhanced thermal conductivity, and he termed those fluids as nanofluids. It was in the year 2001 that Choi et al. Again reported the anomalously increased effective thermal conductivities of ethylene glycol based nanofluids containing copper nanoparticles in the Applied Physics letters.
Hello.
Hello.
Yes, ma'am, you continue.
Am I audible? Hello.
Yes, ma'am. Yes, ma'am. You
Oh,
are.
oh, yeah. Okay. Yeah. Please continue. Ma'am. Yeah.
Now, it was in the year 2006 that Turkey et al. Came up with an innovative idea of mixing two dissimilar nanoparticles in the same base fluid. For example, metal oxide like nanoparticles like Al2O3 exhibit good chemical inertness and stability but possess lower thermal conductivity, whereas metallic nanoparticles like aluminum, copper, silver, etc. possess higher thermal conductivities, but they are chemically reactive and unstable. So, if it is possible to mix these nanoparticles in an appropriate proportion, we can create the hybrid nanofluids and we can use the unique properties of each for various applications. So, the idea of hybridizing or by hybridizing the appropriate combination of nanoparticles, one can get the desired heat transfer effect even at low particle concentrations. And the primary idea of hybrid nanofluid is to achieve a promising improvement in thermophysical, hydrodynamic, and heat transfer properties compared to mono nanofluids. This opens a new arena of hybrid nanofluid to use them for different heat transfer applications. Now, let me tell you about the significance of thermal diffusivity measurement of nanofluids. The thermal studies were mainly focused on thermal conductivity measurements, and there are a lot of theoretical models on thermal conductivity, like unit cell model, Hamilton crossover model, etc. But there are many discrepancies that are existing between these theoretical models and experimental values, which led the research community to identify other thermo-optic parameters influencing thermal properties. Now, if you look into equation 1, it can be observed that the thermal conductivity K is related to the thermal diffusivity of the fluid. So, the researchers identified that the main parameter could be thermal diffusivity. So, there is a need for having a better understanding of thermal diffusivity to understand about the discrepancies that are existing between the theoretical models and the experimental values. Now, the synthesis of nanofluids can be done in two different ways. That is a single-step method or the two-step method when it comes to the nanofluids. That is, you can go for a CVD or LCVD method, or in the case of two-step method, it is more better because you can create the nanoparticles using the top-down or the bottom-up method, and you can disperse them into the required base fluid. Now, there are n number of applications for nanofluids, varying from solar energy, heat exchangers, electronic cooling, generator cooling, nuclear system cooling, biomedical, spaceships, and defense. So, there are a lot of applications when it comes to nanofluids. Now, if you look at the number of articles published in Scopus from 2006 to 2016, it can be seen that with the keywords nanofluid and hybrid nanofluid, there is a tremendous increase in the number of publications in nanofluids. And from the year 2015-2016, you can see that there is an increase in the publication in hybrid nanofluids. So what I would like to bring your attention is that this area of hybrid nanofluid is yet to be explored, and there are a lot more applications to be found out. Now, let me bring your attention to the comparative study of the thermal diffusivity of hybrid nanofluids of gold silica and gold boric. Now, we have chosen two additives, silica and boric acid, because silica has high surface area, hydrophilic behavior, good thermal stability. Is that it has extensive application in energy, microelectronics, heat transfer application, and random lasing. Boric acid also shows excellent stability and it has good thermal stability too. And in nuclear power plant reactors, in order to control the rate of reactivity, proper stability and safety of the nuclear reactor, borated water is used. And other than that, antiviral, antifungal, and antibacterial behavior is also shown by boric acid. Now, the synthesis of gold nanoparticles is done using the Turkovish method, where we have used the precursors gold chloride and trisodium citrate. And this is the method in which we have prepared, and it is a very common method. And in the case of preparation for the hybrid nanofluid, we have taken the gold nanosol and we have added the additive of silica and boric, and we have ultrasonicated for 1 to 2 hours and to obtain a good stable nanofluid. Now, these are the HRTM images of gold nanoparticles, which reveals a particle size of 18 nanometer, and the FSM images of silica and boric acid shows a particle size of 1.68 and 400 nanometer. Now, there are different methods to determine thermal diffusivity, like steady state thermal comparator, laser flash method, thermographic method. But we have used thermal lens technique because it is a highly sensitive technique which can be used to measure very small refractive index changes across the beam width, resulting from a temperature variation of 10 raised to minus 5 degrees Celsius. Now, this is the experimental setup as done in the lab. Now, here you can see that there is a pump and a probe. We have used a pump of 532 nanometer and a probe of 632 nanometer. Both the pump and the probe are made to be collinear and passes through the convex lens. We have used necessary neutral density filters to reduce the power so that there are no spherical aberrations. And from the lens, it passes through the sample. And we have placed a filter to remove the pump, and only the probe falls on the photo detector DSO system. So in the case of this experiment, when we have the pump and the probe, there are excitations that are happening inside the sample, and because of the de-excitation or the non-radiative relaxations, there is heat that is developed inside the sample, and because of which the molecules are forced to move from the center to the periphery, or there is a change or variation in the refractive index due to the variation in the temperature gradient, and there is an optical thermal lens that is formed inside the sample. And along with the probe, along with the pump, we send the probe. So any variation that is happening inside the sample causes a variation in the intensity of the probe beam, which is falling at the DSO. Now, this is the laser spot size before passing through the sample, and this is after passing through the sample. There is a divergence that is happening because of the formation of a concave lens inside the sample. It's an optical thermal lens, and there is thermal blooming. Now, equation 1 gives you the equation for the photo detector, and there are two fit parameters, theta and Tc. So, by experimentally fitting the experimental data to the theoretical equation, we get the theta and Tc, and once we get the Tc, which is a characteristic time constant, we can determine the thermal diffusivity. Now, in order to reduce the error due to the measurement of the beam base size, we have taken a ratio as shown in equation 6. So, we standardized the experiment for water, and then we found out the thermal diffusivity of the sample. Now, these are the decay curve as obtained in the DSO, and figure 12 shows the thermal lens signal recorded for water. Now we have calculated the value for water and gold. It is in close, agreement with that in the literature. So we have experimentally standardized for water and gold, and keeping all the parameters constant, we have determined the thermal diffusivity for gold boric and gold silica, and it can be observed that there is an enhanced thermal diffusivity at a very low volume fraction of 0.16 in the case of boric in gold nanosol. And in the case of silica in gold nanosol, again there is enhanced thermal diffusivity at a volume fraction of 0.65. Now, this enhancement in thermal diffusivity can be explained based on the excitation of gold nanoparticles, resulting in surface enhanced plasmon resonance. For an isolated metal nanostructure such as gold, under illumination, excitation of surface plasmon results in light oscillation from an area larger than its geometrical cross-section area. The electrons from the occupied energy levels get excited above the Fermi energy, reaching a very high kinetic energy, and these electrons are termed as hot electrons, will quickly transfer their energy to low energy electrons via the electron-electron scattering process. Apart from this, there are interactions between the hot electrons and phonons of the inclusions, such as silica and boric acid, which result in the formation of a quasi-equilibrium state between electron system and the phonon system, thereby increasing the lattice temperature. Finally, heat is transferred to the surrounding medium, that is the gold nanosol. The optimal volume fraction could be because of the fact that when the volume fraction increases, the Brownian motion decreases, also the near field interaction also decreases. So it can be compared, or the conclusion of this experiment is that from the dual beam thermal lens setup, we have determined the thermal diffusivity of hybrid nanofluids, and it is observed that when compared to water or the single phase gold nanosol, there is an enhanced thermal diffusivity in the hybrid nanofluid gold silica and gold boric. So, and that too, it happens at a very low volume fraction when compared to the conventional base fluid and the single phase nanofluid of gold nanosol. Hence, it can be concluded that these novel hybrid nanofluids are promising candidates in the development of thermo-optic tools, heat transfer, and biomedical applications. Thank you.
Thank you, ma'am. Any question from audience? Okay, so if there are no questions, I welcome the next speaker of this session, Akanksha Mohan from Department of Chemical Engineering, Birla Institute of Technology and Science, Pilani, Goa, India. And the topic of her presentation is a study on the effect of collector properties on the fabrication of magnetic polystyrene fibers using electrospinning techniques. You will have 10 minutes.
Okay, thank you, ma'am. Is it visible?
Yes.
Okay. So the title of my study is a study on the effect of the collector properties on the fabrication of magnetic polystyrene fibers using the electrospinning technique. So these are the contents. To introduce my topic, I'll first start with the magnetoresponsive materials. So we have all heard of magnetic nanoparticles and its vast research in biomedical applications such as targeted delivery or for hypothermia. The advantage of having magnetoresponsive materials or magnetic nanoparticle in general is that it offers an untethered control, especially because of its super paramagnetic property. So, but we cannot use bare magnetic nanoparticles, MNPs less than 100 nanometer, because of the cytotoxic effects of because of its cytotoxic effects on the biological cells or tissues. So it is known that MNPs less than 50 nanometer will diffuse across the biological membranes, leading to various consequences such as generation of reactive oxygen species, inflammation, impaired DNA function, etc. So having a polymer encapsulation will overcome these limitations and provide a safe way to explore the application. So the polymer I'm using here is polystyrene. So we'll discuss about it later. So there can be different ways of encapsulating it. So here my objective is producing a fiber, and the best way to produce a nanofiber or a microfiber is electrospinning technique, because most materials can be spinnable using this technique. So the basic mechanism is there is a syringe pump where you carry your polymer solution, in this case a magnetic polymer composite solution, and at a constant flow rate, the spinneret, the pump, the syringe pump pumps the liquid out of the spinneret, and due to the electric field, the jet stretches itself and micro or nano fibers are formed. So the main parameters affecting the fiber morphology is the polymer molecular weight, the viscosity of the solution, voltage, working distance, humidity, choice of solvent, etc. So various morphological structures, hybrid structures have been spun using electrospinning fabrication technique, hollow fibers, core sheath fibers, etc. So electrospinning technique is compatible because it can be used with most materials, and it offers continuous production of fibers, hence it can be scalable. So my aim here is to produce microhelical fibers of polystyrene magnetic composite solution, and to in particularly to study the effect of collector properties on the fiber helicity. So what's a collector? So the major function of the collector is the charge dissipation of the deposited fibers. So there are two types of collectors, static collector or rotatory collector. Our focus is here on static collector. So various collector designs have been reported previously. There are again two types of collectors in static collectors, solid collector designs and liquid collector designs. I'll be using liquid collector designs, and my aim is to produce helical fibers, and it has already been produced using co-electrospinning mechanism or mechanical buckling mechanism, which I'll be discussing in detail now. So mechanical buckling is it basically looks like this, which you all have come across while I don't know, like when you just use honey on any pancake or something, you must have seen this mechanism. It's also called liquid rope coiling. It happens when a jet impinges on a solid surface, liquid jet basically impinges on a solid surface, and there is an axial compression. It forms coiling. And the co-electrospinning again uses this particular mechanism, which you can see here. It uses two different types of polymer solution, which is spun side by side. And again, like these different polymers will have a different elasticity. So when it is spun together, there is a difference in shrinking level and hence twisting forms. That is one more way of producing co-electrospinning. So the way which I am more interested in is bending instability, which naturally occurs in an electrospinning setup. So because of the disturbance in electric field or the improportionate surface charge density that is present on the jet. So I'll be exploiting this bending instability to produce helical fibers. So firstly, we need magnetic nanoparticles. So the synthesis is basically using co-precipitation technique. I'm using ferric chloride and ammonium ferrous sulfate in 2:1 ratio as my precursor, and forming an aqueous solution. I try to maintain the pH by adding ammonia, and when it reaches pH 10, I introduce the citric acid functionalization. So when it is heated for 90 degrees Celsius, heated at 90 degrees Celsius for 90 minutes, we will obtain magnetic nanoparticle precipitation. So this magnetic nanoparticles will be dried and then dispersed in polystyrene solution, and hence we will get a polystyrene MNP composite. So these are the physical characterization results. So we can see both MNP and PSN MNP characterizations here. So the major focus is to identify the composition of magnetic nanoparticle in polystyrene. So we can see that the major peak, it already says the crystalline structure. Polystyrene is an amorphous material, non-crystalline material, and we can see that it almost shows the crystalline peaks of magnetic nanoparticle in the composite. And again, in the Raman spectra, we can see that this peak at 666, which actually tells the magnetite phase present in the composite, again in the red color. So again, in the FTIR, we acknowledge the presence of magnetic nanoparticle and polystyrene, and the citric acid functionalization of the magnetic nanoparticle. And we also have the VSM data, which tells the magnetization properties of the magnetic nanoparticle and the composite fiber. So the magnetization value, saturation magnetization value I obtained from this particular characterization is 24.07 for the bare magnetic nanoparticle, and for composite fibers I obtained 13.38, and we can also observe that it is exhibiting no almost negligible hysteresis, which is basically superparamagnetic material. So when the composite solution is spun using electrospinning, these are my collector variations. So I will be using liquid collectors, and I'm particularly interested in the variation in the morphology when surface tension of the collectors are varied. And we can clearly see that for the lowest surface tension ethanol, we have obtained maximum helicity, very fine helical fibers are obtained using and also more number of helical fibers were produced when ethanol was used as a liquid collector. And then I have used ethanol DI water mixture in 1:1 concentration. Surface tension of all the liquid collectors are taken from literature. And again, the helicity is the rate of helicity has decreased a little bit in when compared with ethanol, but again the helical fibers are still present. And again, I have used two surfactant solutions as collectors, and the concentration is above their CMC level, and the surface tension is also mentioned. So we can again see there are helical fibers present. Also in different pictures, we have noticed that various other non-helical structures were also present, like coiled or zigzag structures were also present when surfactants were used as collectors. And for deionized water or sodium chloride aqueous solution, which is conductive and has a higher surface tension than DI water, gives mostly straight fibers. There is no helical fibers present. So with this, we have concluded that helical morphology is pretty much directly related to surface tension of the collector. So to confirm this, we have also used solid collectors, where I have used the conventional aluminum foil for spinning the electrospun like polystyrene fibers. So I have obtained straight fibers like as usual. And I have also used dielectric collector, which is ice. Again, all the liquid collectors and the ice is not exploited much in the literature. This is ice is particularly ice and surfactants are exploited for the first time here. And I have obtained very good helicity using ice. So discussion is firstly in this plot, we try to see like it is pretty much clear that how helicity is dependent on the surface tension. For the lowest surface tension, we obtain highest helicity, and it gradually decreases with the increase in surface tension. Here again, we can see that fiber diameter and coil diameter are again dependent on the collector. So TX100 and SDS, the surfactant baths, again had particle dispersion in that. So that is pretty much causing the coil diameter and fiber diameter to increase a little bit. So why helicity is present at first, and how surface tension of the collector is affecting the fiber morphology. So in a general electrospinning setup, these forces are dominantly present, and it manipulates the jet dynamics. So elastic force of the polymer solution, which is dependent on the polymer solution. Yes.
Ma'am, please can you conclude?
Yes, yes. Okay, so electric force again, it depends on the voltage you are giving. Air drag force is present, surface tension of the liquid collector, and Coulombic force present on the surface charge. So helicity is basically observed when the electric force is greater than elastic force of the jet and the air drag force of the jet, and also when the Coulombic force is greater than the elastic force. So pretty much when you apply a higher voltage and you have a higher charge density, you will be getting a helical fiber. So concluding this talk, magnetic doping, we have seen that it increases the charge density of the jet, thereby increasing the instability. and lower surface tension of the coagulation bath is directly proportional to the amount of helical fibers you receive, as it allows to retain the structure. The instability is formed in the air, but the lower surface tension of the bath allows you to retain the structure of the fiber. Surfactant baths resulted in various fiber morphologies and can replace flammable baths like ethanol. Solid dielectric collectors such as ice or glass. Glass also has been used previously for continuous helical fiber production through mechanical buckling of the jet. So these are the references. Thank you.
Thank you, Akansha. It was a wonderful presentation. Now the session is open for the discussion.
Yes, let me ask one question. Can you hear me? Akansha, can you prepare these fibers in water by using some kind of surfactants?
Yes, sir. I have actually prepared it. I have used sodium dodecyl sulfate as a surfactant, also Triton X100 as a surfactant, both in concentration which is above CMC level. I have used it, and in both the cases, I have got really good helical fibers.
Thank you.
Thank you.
So the next session is on nano energy generator, and for that I would like to invite Pramila V, Department of Sensor and Biomedical Technology, School of Electronics Engineering, Vellore Institute of Technology, Tamil Nadu. She will be presenting on printed carbon electrodes for flexible triboelectric nano generator as a self-powered tactile sensor. Dr. Pramila.
Yes, ma'am.
Yeah, you can present.
Sure. Good afternoon to all. Can you see my screen? Hello?
Yes, yes, we can see. Yeah.
Okay. Before going to present, let me introduce myself. I'm Pramila from VIT University, Vellore. I'm doing research under Dr. Arun Kumar Chandrasekhar in the domain of nanosensor and nano energy generators. Now I'm going to present the paper on printed carbon electrodes for flexible triboelectric nano generator as self-powered tactile sensor. It's basically a tactile sensor as well as it is self-powered device. This is my overview. I'm going to give a general talk on global power requirement and energy crisis, and then I'm going to start with my work, like nano basics of nano generator and how it will be useful in self-powered applications. Then I'm going to start with the working modes, material selection, as well as the device fabrication, working mechanism, and the analysis like electrical analysis, real-time analysis, and all. Here, first, yeah, this global is indeed of power. We need more energy to sustain in day-to-day life. Actually, the energy requirement in traditional sources from fossil fuels, and it might be exhausted someday, and we will be exhausted someday, and that vital important of human society is to be sustainable, and to increase the electricity requirement and other energy requirements lead us to think about the alternative solution for this power requirements. Usually the large scale flexible and low cost energy harvesting devices are very minimum in current situation. Actually, we are using the batteries have some disadvantages like recycling, disposing issues, and environmental issues. Frequently we need to recharge that, and it will be have a thermal runaway, and the energy harvesters, some other energy harvesters like factory or a windmill, that also pollute our environment. So it will cause us pollution to planet, as well as it is harmful to our health also. And I have to mention that our United Nations adopted 17 sustainable global goals to provide a shared blueprint for peace and prosperity for all people and the planet, to the planet and the future by 2030. In that you can see that seventh goal depicts that affordable clean energy, which ensure access to affordable, reliable and sustainable modern energy for everyone. Our proposed work is intended to do support that goal and to fulfill their goal by 2030. The best solution for these all crises is self-power systems. Our nano generator also a self-powered system. Usually, I'm going to talk about TENG in the sense triboelectric nano generator. Triboelectric nano generator is applicable in all kind of applications, specifically for self-powered applications. In that, you can see that sensor and actuator applications. Here, I highlighted that touch sensor. That only I'm going to present now. Nano generators. We need to know what is nano generator. Then only we can understand what is the work going on nano generator. The nano generators simply converts the mechanical energy into electricity. Actually, I have three approaches, mainly piezoelectric nano generator approach and triboelectric approach and pyroelectric approach. In that, piezoelectric and triboelectric nano generators convert mechanical energy into electricity. Meanwhile, pyroelectric nanogenerators can harvest electrical energy from the time-dependent temperature fluctuations. I chose an triboelectric nanogenerator because it has more and more advantages than other two nanogenerators. Piezoelectric nanogenerators need a dedicated material, but triboelectric nanogenerators doesn't need any special materials because we can harvest mechanical energy and convert them into electrical energy by our day-to-day life activities like human motion, walking, vibration, mechanical triggering, as well as flowing of water. The main advantages of triboelectric nanogenerator is material availability, and it has excellent robustness and reliability, and it has a very good for environment because we don't pollute our environment by our device, and it has high efficiency and low operating frequency. And you can use that triboelectric nanogenerator as wearable also because it is very easy to fabricate and it needs very low cost to manufacture, and it has a very light in weight, and it is flexible, highly portable to carry wherever we want. We can use it in jacket as well as for a smartwatch, anything. And the main principle of triboelectric nanogenerator is triboelectric effect and electrostatic induction. These are the modes of triboelectric nanogenerator. Triboelectric nanogenerator works under 4 different modes. First mode is vertical contact separation mode, and second one is lateral sliding mode. Third one is single electrode mode, and fourth one is freestanding mode. Basically, the working mechanism of triboelectric nanogenerator can be described as the periodic change in the potential difference induced by the cycle of contact and separation. Contact and separation. When a mechanical agitation is applied onto the device to bend or press it, the inner surface of the two sheets, like you can see that here we have two sheets. These two are the triboelectric layers, and first and last one is the electrodes. We apply the force on any one of the electrode, and the inner surface of the two sheets will get one side of the surface both just a triboelectric effect. When the deformation release, when we release that device from pressing that, we will get the electrostatic induction. So these opposite triboelectric charges will generate the electric field in between, thus induce a potential difference across top and bottom electrons. In order to screen this potential difference, the electrons will be driven to flow from one electrode to another through the external load I connected here, or as external load. The electricity generated in the process will continue until the potential of the two electrodes get back to even again. Subsequently, when the two sheets are pressed towards each other again, and the triboelectric charge induced potential difference will begin to decrease to zero, so that the transfer charges will flow back through the external load to generate another current pulse in the opposite direction. When this periodic mechanical deformation lasts, the alternating current signals will be continuously generated. This is the basic mechanism of triboelectric nano generator. These are all the materials available economically in triboelectric nano generator design. This is the working mechanism of my device. This is the tactile sensor, which I fabricated with the help of activated carbon electrode and flex friction layer, and here you can see that in initial state, when the human skin and the friction layer in the sense, it's a ecoflex layer. Friction layer and human skin when contact, it will be in this equal rate of charges. When it starts releasing, it electrostatically transfer the opposite charge to the electrode, because here ecoflex has negative charge. When it electrostatically changing the opposite charges the electric potential, which means the electron transfer will occur. Again, it will comes to equilibrium state. When we press it again, this operation will repeats. This is the main fabrication of tactile sensor. Here you can see that first figure depicts that the printed carbon electrode using stencil printing technique. For this stencil printing technique, I used laser cutting technology to make that stencil. Stencil in the sense, it's a simple mask. I used PET sheet as a stencil, and I prepared activated carbon slurry with ready available activated carbon and mixed it together with PVA, polyvinyl alcohol. I taken polyvinyl alcohol as 10 gram of polyvinyl alcohol with 100 ml of distilled water, and I mixed together. After taking that, I took only 10 ml of that PVC binder, and I mixed my activated carbon with it with the help of probe sonication. I probe sonicated for 1 minute. Then I poured on my mask. Before pouring on it, I prepared my mask on the substrate of PET substrate. Then I get my activated carbon, which is coated on PET substrate. You can see that in this image, the schematic illustration of my overall image. For that, I fabricated activated carbon electrode. Then I need one friction layer to fabricate my tactile sensor. For that, I use EcoFlex friction layer. EcoFlex has many advantages, because EcoFlex is completely biodegradable and biocompatible. So we will not pollute our nation, because activated carbon also biocompatible and biodegradable, as well as EcoFlex also biocompatible and biodegradable. EcoFlex silicone rubber has many advantages over PDMS. Like usually people using a PDMS. PDMS only have a stretchability about 30%, but EcoFlex can stretch up to 3 times of its own original size. So I chosen EcoFlex, and EcoFlex alone give good friction, but I would like to improve its friction level. So I did surface modification. I took one emery sheet and prepared my mold, and I put my EcoFlex monomer in the sense precursor and curing agent in the ratio of 1:1, mixed it together and pour it on my mold, and I peeled off from that. I got that Eco. And second one is magnification, and final my data sensor. And these are all my electrical analysis. For electrical analysis, I want to know the how this friction layer works and how we accumulate charges. Further, I did my experiment in 3 different frequencies. In first frequency, I did with 1.2 Hz, and second one 2.2, and finally I did with 5.2. By comparing this, I can find is that when tapping of frequency, I get 10 to 12 voltage. Meanwhile, when my tapping time increases, my voltage also decreases. Here I mentioned the short circuit current value I attained from this device. Actually, the maximum short circuit current I obtained is 0.8 microamps. Actually, the trivoltaic nano generator have the simple drawback of minimal level of current, but we are now doing that mainly focusing on how to improve the current value and power density value. One of my team members particularly working on that domain. And in first image, you can see that our device have the capability to power up a 1 microfarad capacitor. In the zoomed image, you can see that the charging and discharging level of capacitor. This is the real-time analysis. When I connected multiple LEDs with my tactile sensor and tapping over it, I'll get glowing. And this is the video. You can see it. And this is also a real-time analysis. My device can energize that LCD display. It doesn't need any battery power or anything because it's a completely self-powered. It's very portable and reliable. And coming to conclusion, we reported a single electrode tank-based tactile sensor, which comprises an eco-friendly EcoFlex silicon rubber as a friction layer and printed carbon electron as a electrode level. The fabricated tactile sensor have a high sensitivity as well as it is flexible. We checked with various ratios. When I mixed PVA with 5 gram of activated carbon, it is brittle in nature. When I tried with 3.5 gram, it is also good. But I chosen 1 gram because it has more flexibility, bendability, and my device has durable. And this device possesses a short circuit current as 0.8 microamps, and the maximum open circuit voltage we obtained is 10 volt. This tactile sensor has the capability to charge storage, and that has been examined by using that 1 microfarad capacitor charging and discharging operation. And our future work is focused on integrating an array of this tactile sensor. Here I used only one tactile sensor. We plan to do with the array of flexible tactile sensor and miniaturizing the device with good performance. Why we doing this in the sense we need to do it as a compatible device which will help to assist people with visual impacts with the help of haptic sensor. And I would like to acknowledge Dr. Arun Kumar Chandrasekhar for his great guidance. He is my guide. And this research work was supported by our VIT University's VIT Seed Grant 2021. And also I would like to thank Mr. Harish and Uday Surin sir for their lab support. These are all my references. And thank you. Hello, sir. Hello.
Thank you, ma'am. Thank you for the wonderful presentation. Audience, if you have any question, you can discuss. From the audience, any questions? If there is no question, we can move on to next session.
I think someone raised their
but they have not question.
Hello, am I audible?
Yeah,
Yes, sir.
Yeah, I had one quick question. That you showed the demonstration of that LCD panel, self-powering that LCD panel, right?
Yes, sir.
For how long it can keep it on? I mean, the time of duration.
Actually, it's a self-powered device. We didn't store the energy. We directly power up that LCD. We
Yeah.
can also store it, use a storage device and retain it.
Means, does it work as a battery or something else? I mean,
Not a battery. It's
yeah.
just a supporting device. We can't replace it completely with a battery.
Yeah. Okay.
Yeah, it is somewhat supporting.
Fine. Thank you.
Thank you, sir.
Thank you so much, ma'am.
Thank you.
Next session is on foams. For that, I will like to invite T. Bhuminathan, Department of Chemistry, School of Advanced Sciences, VIT Vellore, Tamil Nadu. He will be presenting on catalysis of nano-sized lead-loaded modified chitosan polyurethane foams for carbon-carbon and carbon-nitrogen coupling reactions. Dr. Bhuminathan, you are most welcome for the presentation. Hello, Dr. Bhuminathan. Yes.
Are you able to see my slide, ma'am?
Yes. Your slides are visible. You can continue.
Okay. Good afternoon, everyone present here. And this is Bhuminathan. I'm going to give a talk on synthesis of nano-sized palladium-loaded modified chitosan polyurethane foam application in cross-coupling reactions. So we know that most of the numerous metal-based heterogeneous catalysts are well known for the CC and CN coupling reaction, but the main problem is metal leaching from the heterogeneous surface, and thereby it reduces the efficiency of the catalyst after a few cycles. So there is a constant demand for a recyclable, non-leachable, high-efficient and eco-friendly catalytic system of industrial significance. And the present work described the designing, fabrication, and characterization of the heterogeneous material loaded with a nano-sized palladium for the carbon-carbon and the carbon-nitrogen coupling reaction. In this work, the synthesis of selective derivative of chitosan-based polyurethane foam and their corresponding nano-sized palladium-loaded polymeric foam, and the heterogeneous palladium catalyst was utilized in CC and CN coupling reaction in high yield. And some of the literature for the palladium based material for the catalytic applications.
So the figure 1, polymethoxylic acid has support for the palladium preparation, and they have done a reduction of para-nitrofenol to para-aminophenols. And then second one is modified chitosan used as support for the preparation of palladium catalyst, and then coated with titanium dioxide. Then they have done a CC coupling reaction and high temperature, less yield, high metal loaded, and without titanium coated palladium leaching from the surface of the catalyst. And then what are the main components involved in this polyurethane foam? And mainly polyol, isocyanates, catalyst, blowing agent, and surfactants. And the objective of this present work is to perform carbon-carbon and carbon-nitrogen coupling reaction. A small amount of metal is loaded onto the chitosan based polyurethane foam, and to achieve a high conversion rate, carry out carbon-carbon and carbon-nitrogen coupling reaction at a room temperature to avoid the metal leaching from the catalyst surface. Then we have done the chitosan paste based material, their different application, adsorption, dye removal, support for the catalyst reaction, bioactivity, and miscellaneous application. Then we have published in topic in current chemistry. Then we have selected some of the precursor in order to improve the foam, surface area and porosity and thermal stabilities. And this the precursor should be non-toxic, and the foam material need to be biocompatible, and the facile synthesis and reproducible, and the possibility of the structure modifications. And this is the way the polymeric foam were synthesized. And we have made a different foam materials, and gallic acid foam, citric acid foam, tartaric acid foam, and chitosan foam, and polyethylene glycol foams. And then the structure of the chitosan foam materials, and the carboxylic acid based which we selected the precursors, the structure of the foam materials. And this is coming to the synthetic procedure for the nano-sized palladium foam catalyst. And then we first we have loaded palladium chloride, then we have reduced sodium borohydride into make it palladium zero. Then we want to check the structure of the foam material as well as palladium loaded foam materials. Then the urethane linkage of carbonyl carbon appeared at 1700, and the NH group appeared at 3300. And coming to the XRD, and before loaded, after loaded, the palladium peak were confirmed through the JCPDS files. Then we want to check the stability of the catalyst, and then the slightly increased after palladium loaded, the stability somewhat increased. And we want to check the catalyst oxidation state of the oxidation state. We have taken XPS analysis, and there are two binding site which is indicate the one is 0 oxidation state, another one is 2 oxidation state, and this 335 and 340 is which is indicate the 0 oxidation state, and the another one is 377 and the 343.1 is which is indicated the palladium is 2 oxidation state. And all the 4 catalysts majorly palladium 0 is contributed. And we have taken SEM analysis to check the morphology of the foam materials, all the foam having more surface area. And then we want to check the particle size of the palladium, and we have taken HR time analysis, and all the foam 4 catalyst, the particle size around 3 to 10 nanometers. And we have checked ICP OES for the metal leaching studies, and up to all the 4 different catalysts, combination of chitosan and citric acid foam material having better catalytic efficiency, and compared with the other catalyst. So it is up to there is no metal leaching up to 10 cycles. And this 2 application we have done, and Suzuki cross coupling reaction, and synthesis of benzimidazole. And we'll see the one of the CC coupling derivatives, and the methyl proton appear at 2.6, and the other aromatic protons appeared 7 to 8. And coming to the C13 spectrum, and the methyl carbon appeared at 27, and the carbonyl carbon appeared at 197.94, and the other aromatic carbon appeared at 120 to 140. And coming to the chromatogram which is indicate the compound CC compound having no other impurities. And the expected mass for this CC product and 196.09. The observed mass is 196.40. And coming to the another application, benzimidazole derivatives, and the three aliphatic methyl proton appeared as a singlet in the range 1.5 and 1.6 and 2.2, sorry 2.1. These two CH2 group appeared multiplet in the range 2.1 around. And then this proton appeared as a triplet, which is appeared at 5, and this proton appeared as a singlet, which is appeared at 6.1. Then all the rest of the aromatic proton appeared at 7 to 8. Then we have taken C13 NMR. All the aliphatic methyl and CH2 group appeared at 20 to 40, and the rest of the other aromatic carbon appeared at 110 to 150. And coming to the chromatogram of benzimidazole derivatives, and here which is indicate the chromatogram which is indicate there is no other impurities involved. And the expected mass of this compound is 274.124. Observed mass is 274.379. And coming to the conclusion, we have successfully developed a new heterogeneous catalyst system containing nano palladium based polymeric foam material using carboxylic acid. The prepared catalyst was characterized by the various spectroscopic and analytic technique. This catalyst demonstrates CC and CN coupling reaction, yielding the product with high conversion at room temperature. This method is simple, reusable, and eco-friendly and cost-effective. This is the abstract. And coming to the acknowledgement, I'm thankful to my research guide, Dr. Agila Sivaramakrishna, for his constant guidance and encouragement. I'm grateful to VIT Vellore for the research fellowship and all the facilities. I would like to thank the organizer of the ICN 2022 for the providing me an opportunity to present my work here. Thank you all.
Thank you, sir, for the great presentation. Sir, actually, I want to ask that you have mentioned that this process is reusable. So, can you explain how it can be reusable?
Yes, ma'am. Yes. Actually, we have done a CC coupling reaction. So, what we have to take a small, RB. We will take RB and we will put our catalyst for 10 mg. So this catalyst can after reaction over, we will take it back simple filtration. Then again the same catalyst used for 8 times to 10 times. Then we have to check it their efficiency, whether it is working 100% or it is less. We have to check it.
Sir, the efficiency will reduce after multiple use of the catalyst if we are reusing it.
Yes, ma'am. But the my case, I observed according to the ICBO's result, there is no metal leaching, ma'am.
Okay. Thank you, sir.
Okay. Okay. Thank you, ma'am.
Thank you. Now for the next session. Next session is on environmental application, and I would like to invite Deepak Panchal. He is from Wastewater Technology Division, CSIR, National Environmental Engineering Research Institute, India, and he will be presenting on inorganic nanomaterials for multifunctional environmental application. Dr. Deepak Panchal, you are most welcome for the presentation.
Hi, just wait a minute, I'm sharing my slide.
Okay.
Is it visible?
No, sir.
Yeah. Is it visible now?
It is loading. Yes, sir. Can you make it to full screen mode?
Yeah.
Yes, sir. Yes, sir. You can continue. Yeah.
Hi, I'm Deepak Panchal, and the topic for today's talk is engineered inorganic nanomaterials for multifunction environmental applications. So, directly jumping to the application of nanoparticle in water treatment, we have seen various applications such as photocatalysis of nanoparticles, where different modalities for oxidation of organic particles and transformation of heavy metals. Also, we have seen the disinfections, oxidations through the different nanoparticles and dehaloginations of higher organic compounds. We have seen the application of iron-based nanoparticles for photofentone reactions, and we have seen the adsorption of different organic compounds and high metals in the water treatment. So, however, still we have various research gap, which is when the physicochemical characteristics of any pollutant changes, your application get limited. This is how we achieve this is how we see the restricted application of nanoparticles. And when there are multiple contaminants, you are not able to remove all the contaminants at the same time, because your nanoparticles are very specific toward the targeted nanoparticles, and somehow we lose the intrinsic characteristics, because when they are in environmental complex environmental sample, they tend to agglomerate, and a big compound can be formed, and this is how they lose their nano size and their activities which are generated from the nanoparticles can compromise. So we thought of synthesizing the multifunction nanoparticles, such as we have this new type of phone in our hands. We can use interfaces like social media and entertain ourselves. We can talk to people which are not even around you. So we also wanted to synthesize such a materials which will be able to have so many application at the same time. So how can we induce these multifunction applications? We can synthesize multi-metallic based nanoparticles, or we can couple the different applications such as adsorption and photocatalysis together. In our first research activity, we targeted the biometric system based on the silver and iron. So in literature, we found that people were using different methods, where they were using either the pre-synthesized silver-based nanoparticles, or they were using this iron-based nanoparticles. Also, the synthesis was very sophisticated, and there were 2-3 steps in a synthesis. However, in this activity, we synthesized the AGFE biometric system in one reactions, where this plus two say ferrous iron was converted into the ferric under the light irradiation, and in the same system we reduced the silver ion to the silver nanoparticles, and we converted to the coral-like hierarchical AGFE biometric system. So this is how we achieved this. We added the silver and iron together in a system, and we irradiated the system, and we found there is a change in a color within 5 minutes, and we characterized this, and we found the formation of coral-like nanostructures. However, we kept the same situation in the dark also, but we found no changes. We also checked whether the silver can form nanoparticle itself, but no, there was no change. Even the iron was not able to change it. However, there was some slight change in the iron solution, but after 24 hours, which is very kinetically slow. So this reaction was pretty fast, and we didn't use any reducing agent, no surfactants. So just by irradiating the system, we were able to find such type of structures. We did this experiment at different molar ratio also, and we found at higher concentration of iron, the precipitation was occurring so fast, and we were not able to see any type of coral-like structures. When the concentration of iron was reduced down to 1 millimolar, here it was 20 millimolar. When it was reduced down to 1 millimolar, we were able to find this type of prominent coral-like nanostructures. So we can say the synthesis can only happen in light and at a some millimolar range of iron ferrous concentration. And this is the TEM images. You can see there are small dots which are indicating the presence of the silver nanoparticle in the iron matrix. And in HRTM, we find the monocrystalline nature of the silver nanoparticles because the plane was very consistent, and the d-spacing was coming around 0.236 nanometers. And this is the elemental mapping, where you can see the iron matrix as a pink color, and the yellow color is indicating the occurrence of the silver nanoparticle. And in the superimposed image, you can see the silver ion are pretty fixed in the iron matrix. And this is XRD image, XRD pattern. You can see the where various prominent peak are there, which can be assigned to the ferroferric oxide of irons and presence of metallic silver. In order to just check what is the oxidation state, we checked the XPS, and we found two prominent peak in the AG3D region, and which was coming around 368 and 374.2, which was the separation was around 6 electron volts, so giving the indication of the successful reduction of silver to the metallic nanoparticles. And this is the XPS of the ferroferric oxide. You can see the peaks which were deconvoluted into different peaks, giving the indication of occurrence of +2 and +3 ions and oxidation state. And this is the EDS, which is giving the occurrence of which is showing the occurrence of iron also and silver also. This is the particle size distribution, where you can see the silver particle can be narrowed down to 2 to 4 nanometers. However, the particle size was how the particle grow to the 16 to 20 nanometer also. And we gave a plausible mechanism for the synthesis. We started with ferrous, and which get photo oxidized to the ferric, and then because of the continuous irradiation, they might have converted into the aqua complexes of irons, and because of the continuous irradiation, they dissociate back into the ferrous. So this is how we achieved a photo oscillating system of the iron, +2 to +3, +3 to aqua, and then again back to the +3. And in the same time, we added the silver precursor, which get reduced to the metallic silver together. So in the same reaction, we were able to achieve the formation of the metallic silver nanoparticles, and some of the portion of the +2 and +3 species of iron get transformed into the stable iron oxide, and and we found the formation of the silver and iron oxide together. We gave the six to seven stages for the formation of this photo-induced synthesis. And talking about the stabilization, there can be two type of interaction between the silver nanoparticle and iron nanoparticles. However, the heteroaggregation was more prominent because the iron was characterized to be positively charged, where the silver were negatively charged. So because of the difference in the surface charges, the chances of formation of biometallic system was high. And because of this heteroaggregation and interaction, the dissolution of the AGNP can also be reduced back into the solution. So we can say the interaction will reduce the leaching of silver into the aqueous solution back. And this is the environmental application we explored from the synthesized nanomaterials. We removed the arsenite ions to 100% from 500 ppb of the concentration, and with increasing the dose of the AGFE biometallic system, we were able to achieve 93% of the removal from 1 ppm of the arsenite. And we have also checked the antibacterial activity of the system against the gram-negative and the gram-positive bacteria, where E. coli was completely removed around 32 milligram per liter of the dose, and the M. arborescens was removed completely around 64 milligram per liter of the dose. And we hypothesized that this happened because of the synergistic action of the silver and iron together in the biometallic system, because iron is known for their metal capturing capacity. So we synthesize the coral-like structure. So this is how the surface area might have increased, and we have achieved enhanced removal of the arsenic ion. However, silver can also form bond with the arsenic oxides and precipitate as a yellow precipitate. And in terms of antibacterial action, the silver are known for their contact healing. However, iron can also play their role. They can stabilize the silver nanoparticles because the zeta was coming very high, very positive. So silver nanoparticle can adsorb on the surface of iron nanostructures, and they can also adhere the negatively charged nanoparticle on the surface of the nanostructure, where silver can play their role for the contact healing. And in conclusion, we have achieved a coral-like hierarchical nanostructure within one pot reaction based on the photooscillating system of iron. We eliminated the use of any precursor, and we can say the process was environment friendly. We changed the morphology just by changing the concentration of ferrous in the system, and we removed the arsenic by 99% from 100 to 500 ppb, which is well below the US EPA drinking water standards. And the absorption capacity was coming around 125.64 milligram per gram. And we have also checked the KD value, which was coming around the 10 to power 6, which is indicating the AGFE was quite great adsorbent. And we have also achieved the biometric. We also achieved the antibacterial activity of the biometric system. In the second activity, we thought of synthesizing a material which would be able to perform two function at the same time, that how to kill two birds at the same time. So we thought of synthesizing a heterolayer system, where we targeted the synthesis of Ti2 decorated magnesium layer outside, which is positively charged, and MS2, which was negatively charged. Because of the difference in their surface charge, we were able to achieve a heterolayer system based on the electrostatic self assembly. And this is how we got their structures. The tier 2 decorated our LDH layer. This is hexagonal layer of LDH. Tier 2 is decorated over the surface of it, and this is defect rich MS2. You can see wavelet like structures of MS2, and because of the difference in surface, we achieve the final structures here. Yeah, this is the 7-10 images of the MS2. You can see the corrugated structure of MS2. We have also additionally created some defects into it. So the interlayer spacing was increased to 0.692 nanometer, and we additionally created some defects which helped inducing the some additional binding sites, so that we can capture more number of heavy metals or the other pollutant over the surface of MS2. And this is LDH. You can see prominent hexagonal shape, and this is after the decoration of the Ti2 nanoparticles, where the LDH is pretty preserved. And this is the final structures of TLM, titanium at the LDH and MS2. And you can see the occurrence of Ti2 nanoparticles.
Hello.
Hello.
Sir, can you conclude?
Oh, okay. This is the XPS of MS2. This is the environmental application where we achieve the cationic dye removal and anionic dye removal by using the single type of nanomaterial. And this is the reusability test, where we achieved the 92% of removal even after the 5 cycle. This is the hypothesis, where we show the formation of semiconductor type 2 semiconductor between the MS2 and Ti2. This is the removal of different type of metal ions from the same solution, and very high adsorption capacity of 425 milligram per liter. And in conclusion, that we achieved the defect rich MS system, where we have achieved different type removal of different type of pollutants in a single treatment. Thank you. Yes, please, any question?
Thank you, sir, for the wonderful presentation. Audience, if you have any question, you can discuss. Okay, we will move on to next session. Next session is on membranes, and for that, I would like to invite Dr. Vibhu Prasad Sahu to chair the
Yes, ma'am.
session.
Actually, I joined late. Sorry, it's raining like anything. I was outside of my office. Okay. Anyways, it is just a glimpse only I have seen. So, may I know what information you got from XPS study?
What information I got from XPS study?
I thought XPS you have presented, right?
Yes, yes.
Okay. May I please explain that XPS? What? I mean, just a query. This is not a question. What result? What analysis? What thing you interpreted after getting XPS result?
Okay, okay. I'm just sharing the XPS slide.
Just go. Yes, go to that slide, please.
This slide?
Yeah. Yes, yes. Yes.
So this is the MS2, the X-phase of MS2. Here we are saying the successful formation of MS2, and this is for the S2P region where we are saying the disulfide bridging between the MS2 layers. So S, MO, and S. So this is the successful indication of the formation of MS2, and these are the different peaks in the M2P region of Mg, and this is, we are just indicating yes, we have successfully synthesized the nanoparticles layer of LDH, and this is for Ti2 nanoparticles.
Okay. Okay. Thank you. Actually, because I very much curious to know about XPS. Thank you a lot. Means it gives
No,
us the
I can
information
explain
whether
it. I can
really it
explain
is
it.
formed or not. Yes. Hello.
Yeah. What you want to know? Just ask your
Means
question.
it gives the information about the really it is really formed or not. What you want? Okay. Right.
Yes. And
Yeah.
also there
Thank
are
you.
some shift in the peaks. When we checked it with the available data, there are some shift which is showing the electronic bond between the nanostructure formation.
Okay. Thank you. Very nice. Okay. Thank you for your nice presentation. I don't have any question.
Next session is on membranes. For that, I would like to invite Dr. Bihu Prasad Sahu from School of Applied Sciences, KIIT, deemed to be University, Bhubaneswar. Sir, I would like to welcome you for the session. Sir, you can share the session.
Thank you, ma'am. Thank you for your warm welcome. Yes, ma'am. I'm here only. Next presentation, who is presenting? Please share your screen.
Sir, do you have schedule of the presenters?
Yeah, I actually it was with me, but right now I am in a place to access all those things. So kindly you help me and you call the participants on another.
Okay, I will invite. For the next session, I want to invite Harsh Patel. He is from Membrane Technology and Gas Separation Laboratory, Department of Applied Physics, the Maharaja Sayaraj Rao University of Baroda. He will be presenting on energy band gap and thermal analysis of polymer PC and GEO nanocomposite membranes films.
Okay, am I audible, ma'am?
Yes, sir, you are audible.
My screen is visible. Hello, my screen
Sir,
is
can
visible.
you make it to full screen mode?
Yes, it is visible.
Yes, it is visible now.
Yes, continue.
Good afternoon, everyone. Myself, Harsh Patel, and today I am going to present my paper in the International Conference on the Nano Materials, ICN 2022. And the title of my paper is Energy Band Gap in the Thermal Analysis of Polymer Polycarbonate with Graphene Oxide Nanocomposite Membrane Films. So the outline of my work is the introduction, methodology, synthesis, and the characterization, and the resultant discussion. So my main focus is to make the membrane for the hydrogen purification. So nowadays there are the many application of the membrane. In the real world, there are the many two types of the membrane, polymeric and the non-polymeric. And the basic application of the membrane is the industrial water purification, fuel beverage. And the region when the types of the membrane is very much used is the North America, Europe, and etc. So the basic process of the membrane is when we feed the mixture of the gases, the membrane filter the particular gas and retrain or pass some of the gases. And there are
Your
the two.
screen actually is not. Are you moving the screen? It is not moving. Only we are getting your fast screen. Actually, share the complete screen. Then only it will come.
Yeah. Okay, sir.
Share your complete screen. Actually, we are getting only your first slide, title slide.
Okay. And now it is visible.
But go to presentation mode. Yes, now it's okay. Yeah, it's moving right now. Continue.
It's moving now. Okay, sir.
Yes.
Okay, so yeah, okay, so there are basically two type of the process, porous membranes and tensor membrane. I just use the solution diffusion mechanism for my experimental work. So my aim and my goal is to purify the hydrogen gases and to hydrogen purification. So nowadays the hydrogen is generated from the renewable energy like wind and the solar cell. Here the membrane play a very key role to purification of the hydrogen, and it's converted into the green hydrogen. And the application of the green hydrogen is the aviation, chemical manufacturing and shipping also. And these are the picture where the membrane process is actually used. So the synthesis process of my membrane is I just use the solution casting technique to synthesize my membrane. And these are the polycarbonate membrane. And when I added the graphene oxide nanofillers in this solution, the membranes look like this. And these are the real material when I used to found out the gas permeability. So the experimental setup, which is known as the constant volume variable pressure method, in that I just use the permeation cell, which is the inside of the image of the cell, which is looks like that. In that middle of the part, I just put my membrane, and from the upper side, I just feed the mixture of the gases, and by using this membrane, the particular gas like hydrogen gases to pass from this membrane, and I just found the permeability and the selectivity of the particular gas. So these are the result of the permeability analysis with the different gases. I just use the hydrogen, carbon dioxide, and the oxygen in my experimental work. So here it is easily observed that when I increase the graphene oxide nanofiller, increase the weight percentage of the graphene oxide nanofiller, the permeability of the oxygen and carbon dioxide is reduced very much in comparatively the hydrogen gases. And the selectivity data shows that when we have the mixture of the hydrogen and the carbon dioxide, then it is very much easy to separate the hydrogen from the carbon dioxide, and very much hard to separate the hydrogen from the oxygen gases. These are the result of the selectivity. And by using this result, I just plot the Robinson plot. So it is gives the result which is below the Robinson 2008 upper line and 2091 upper line bound, which is so there's this material very much used in the recent novel of my work. And by using the thermal analysis, I just found the glass transition temperature with a different heating rate, like 5%, 10 heating temperature, 15 heating temperature, and 20 heating temperature. And by editing the graphene oxide, I just found that when we added the graphene nanofiller in the polycarbonate, the glass transition temperature will be increasing as we add it, and that means that shows that the thermal stability of the polycarbonate will be increases as we added the graphene oxide. And by using the DSC analysis, I just found the activation energy by using the four different method, like OSWA method, King's-Fisher method, and two another method. These are the table of the activation energy. As we show that as we added the graphene oxide nanofiber, as we increase the weight of the graphene oxide nanofiber, then the activation energy is decreasing. And I also found the energy bandgap. So here the values of the energy bandgap. As we increase the rate of the graphene oxide nanofiller, the energy bandgap is drastically decreasing. As if you have the polycarbonate energy bandgap which is around 3.10, and as we add the graphene oxide nanofiller, the energy bandgap which is found around 2.09 in the case of the 15% of the graphene oxide. These are the another result of the energy band gaps. These are the FTIR spectra. In this spectra, I just confirm the presence of the graphene oxide by confirming this bond. Here the XRD analysis. By using the XRD analysis, my polymer, which is the crystallized material, and when we added the graphene oxide, the FWHM will increasing. That show that it is converted into the amorphous. By using the SIME analysis, I also just confirm the presence of the graphene oxide in the polycarbonate, and I successfully synthesize my polycarbonate with the graphene oxide membranes. So the conclusion of my work is that the aim of my work is to purify the hydrogen gases and the transporter by using the polycarbonate and the geo nanofiller, the better transportation mechanism of the hydrogen gases. It's improve the hydrogen gas molecular as compared to the another gases like O2 and CO2, and the PC and GO shows the higher permeability for the hydrogen gases, and the same result, same analysis confirmed the presence of the GO in the polymer. Uh, and the main thing is that the novel of my work is the separation factor tends toward the Robinson 2008 upper bound limit, which is the novel of my work. And these are the references that I just use, and I acknowledge to the UGC for providing me JRF and SRF scheme. Thank you.
Okay, thank you for your nice presentation. So may I know, I'm having a query. So why you have selected polycaprolactam, not other polymer?
Sir, because sir, the bonding with the polycarbonate, and we got the fraction-free volume for to find the permeability, which is the highest in the case of the polycarbonate and not in the other polymers. So polycarbonate is the glassy polymers, and we have also option for the rubbery polymers like PDMS. But in the case of the PDMS, we to make the membrane, which is quite difficult, and the permeability of the hydrogen, which is very high. It is uh, very much difficult to control the permeability of the other gases also. So that's why I selected the polycarbonate with the graphene oxide.
Okay. Then what is the means after adding GO graphene
Yes, sir.
oxide? What is the increase in permeability or what improvement of your
Sir,
material you observe?
yes, sir. After editing the GO, the permeability of hydrogen it is increasing by drastically, and the permeability of the oxygen and the carbon dioxide which is decreases. That means if we have the mixture of the gases, if we have the impurity in the gases of the hydrogen, then it is very much useful to purify the hydrogen from the other gases like carbon dioxide, oxygen, nitrogen.
So if we will go for any metal oxide nanoparticle, then have you thought what will happen? It will work better than GO or not like GO?
Yes, sir. If we
Suppose I am
use
saying zinc
the
oxide, titanium
yes,
oxide,
sir.
if I will say.
Yes, sir. Yes, sir. They also increase the permeability of hydrogen, but GO shows the more higher permeability than the another nanofillers like CNT, ZnO2, TiO2, silica.
Okay.
I
And
also
in
did.
the scheme, in the image, you have shown a cylinder. That cylinder is full of hydrogen gas or mixture of gases.
No, sir. It is particular for the hydrogen gases. We have the different cylinders also, like
Okay. So
carbon
your
dioxide,
job is
oxygen.
in not cell. If you want, if I am not wrong, so you have taken the polycaprolactam and geo nanocomposite film, and through this film you are allowing the hydrogen gas and you are measuring the extent of permeability, right?
Yes, sir. Yes. Yes.
Okay. In this way, the
That
hydrogen
is
is getting purified, right?
yes, sir. Yes, of course.
And it allows us only the film allows us only H2 gas to pass over it, and other gas will not pass, right?
Yes, sir. No, they are also passed, but the rate of the permeation is very low as compared to the hydrogen gas.
Yes, yes. Okay. That means in this way you are purifying the hydrogen, right?
Yes, sir.
Okay.
Yes, sir.
And you
Because
have
of the
also mentioned the solvent casting as well as means you are polymerize caprolactam to polycaprolactam, or you are using commercial grade of polycaprolactam.
sir, commercial grade of the polycarbonate.
Okay. Okay. Thank you. Very nice
Okay, okay,
topic.
sir.
And
So basically, my aim
again,
is the
another thing you have
yes,
shown some wind image. That
yes,
means
sir.
the what
Yes, sir.
wind energy image. So what is the
Yes, sir.
means how you are linking the wind energy image with your topic?
Sir, actually, by using the wind energy and by solar cells, they generated a hydrogen. But the
Okay.
generation of the hydrogen is not purified. So by using my membranes, means this type of the membranes, they converted into the green hydrogen. And the application of the green hydrogen is the hydrogen fuel cell very much useful, the green hydrogens.
Okay. Thank you. Thank you for your presentation. It's really indeed a good presentation. Thank you. All the very best.
Thank you. Thank you so much.
So may I have the next presentation?
Yes, sir. Thank you. Next, Rini K. Vishwakarma. And he's from Analytical Chemistry and Spectroscopy Division, Indira Gandhi Center for Atomic Research, Kalpakkam, Tamil Nadu. And he's going to present about effect of hydration on strontium absorption, performance of graphene oxide membranes.
Hello?
Yes, ma'am, you're audible.
Hello? Okay, ma'am, my
Yes,
slides
ma'am,
are
can you
completely
make
visible.
it full screen?
Full screen, 1 second.
Yes, ma'am. Yes.
Now it is? Okay. Good afternoon, everyone. My name is Rini. I'm fourth-year research scholar from IGCR, Indira Gandhi Center of Atomic Research Center, Kalpakkam, India. The work I'm going to present here, effect of hydration on strontium adsorption performance of graphene oxide membranes. So that upcoming slides will be containing objective of the work, synthesis and characterization of graphene oxide, hydration effect on graphene oxide membranes for strontium separation, results, conclusion and references. So let me start with introduction. What is graphene oxide? So basically graphene oxide is a two-dimensional material, a popular adsorbent widely used for separation of various metal ions, not only metal ions, pollutants, dyes, etc. Large surface area and diverse oxygen functional groups which are being protruded on the sp2 carbon matrix, which is facilitating adsorption process. As we know, in adsorption is a surface phenomenon. And if I'll speak about the mechanism between metal ion interaction and graphene oxide, so the oxygen functional groups which is making polar, that graphene, which is the skeleton of the graphene oxide, can form metal ion complexes, and the sp2 carbon domain, especially these interact with non-covalent interactions, and here it will be cation pi interactions. So aims and scope will be, objective of the present work is to study behavior of graphene oxide upon hydration and its effect on strontium separation from aqueous solution. Strontium 90 basically is a radioactive radionuclide, which is a biological and environmental concern, since it is a strong beta emitter and poses carcinogenic characteristic. And one best part with this work is that we have chosen one method, chemical-free approach for surface modification of graphene oxide as compared to conventional methods which are being adopted from long time. That is either some chemicals like ozone, sodium borohydride, polymers, or metal organic framework. Now graphene oxide and its characterization. For preparing graphene oxide membranes, we have used graphene oxide dispersion, and for reaching to final graphene oxide dispersion, we have prepared graphene oxide using Hammer-Hoffman method. For that precursor, we have used graphite powder followed by reagents, that is KMnO4, sodium nitrate and H2O2 for consumptions of these metal ions, so that it should not affect graphene oxide, and ultimately we are getting graphene oxide. Here next, characterization of graphene oxide with spectroscopy. We will start. U visible spectroscopy, that absorption spectrum on the right hand side of graphene oxide, and one FTIS spectrum of graphene oxide sheets I have presented here. So with UV spectroscopy, a peak at 228 nanometer is due to pi-pi strike transition of carbon-carbon double bond group, and peak at 302 nanometer is due to in-2-pi strike transition of the carbonyl group. From FTIS spectroscopy, broadband in the region of 3800 to 2600 wave number is due to stretching vibrations of hydroxides, which are associated with carboxylic group and adsorbed and free water molecules, which are present on graphene oxide, and peak at 1733 nanometer, 1733 wave number and 1587 wave number are due to carbonyl stretchings associated with carboxylic group present in the graphene oxide, and 1587 is due to carbon-carbon double bond skeletal vibration or sp2 carbons of the graphene oxide. One peak which is very much intense in the overall window, that is 1151 wave number,
is due to the asymmetric and symmetric stretchings of the epoxides as well as ether, and one peak at 865 wave number are associated with deformation vibrations of the epoxide. Next, with morphological study with FEACM, we have studied that what graphene oxide we have synthesized are monolayers. These are the lateral dimension of graphene oxide. What we have prepared is of from 2 to 5 micrometer. In the inside of that SEM image, I just wanted to show that membranes what we have prepared, and followed by that graphene oxide membrane and surface modification by hydration. So basically, graphene oxide membranes we have prepared using vacuum filtration method, and in that we have taken MC membranes, mixed cellulose ester, which are polymeric membranes. On that we have taken a subsequent amount of water, and then we have dropped graphene oxide dispersants, and then we have prepared this graphene oxide membranes, and we have kept it for drying till it reaches constant weight. Then one schematic here I have represented that skeleton of graphene oxide and how water is approaching it, and restructuring, how that restructuring of graphene oxide will happen. Now, effect of hydration on graphene oxide membrane. Let's go with interaction studies, graphene oxide water interaction with FTIR study. So in FTIR spectra A, B and C, A corresponds to graphene FTIR spectrum of graphene oxide, B corresponds to graphene oxide treated with water vapor for 60 minutes, and C corresponds to graphene oxide intercalated in water for 60 minutes. Before concluding to these timing, already we have done set of experiment with minimum of 5 minutes and maximum of 72 hours experiment. So with water treatment, whether it is intercalation or water vapor, we have seen that large enhancement in the intensity of OH stretchings, and we have seen again that intensity in the sp2 carbon peak, that is 1587 carbon, which is corresponding to carbon-carbon double bond of the skeleton vibration, that has increased. And one blue shift of epoxide, it has shifted to from 1154 to 1217 wave number. It means that from symmetric to asymmetric stretching directly it is getting converted. And removal of epoxide deformation peak, that is in spectrum A, 867 peak we can see, that is deformation vibration of epoxide, but in C it is not there. And overall, with FTIR, it has been concluded that hydration of graphene oxide leads to restructuring of functional group, and relative ratio of functional groups has been changed. Now, this effect has been studied for strontium adsorption. So, strontium analysis, which has been done using flame AES. So from that initial and final quantification has been calculated, and then we have seen that optimum strontium adsorption capacity of graphene oxide membrane is 335 milligram per gram, which enhances directly to 515 milligram per gram at 0.1 milligram graphene oxide mass on the membrane. So hydration, which has been lead by the modification of graphene oxide, which has been lead by the hydration effect, which is ultimately changing the structure and diffusion properties of these ions, which are being percolated through these membranes. The confined and localized motion of water molecule makes stronger hydrogen bond between the graphene oxide layer. And finally, hydration amongst relative ratio of functional groups on the graphene oxide, which is facilitating more active sites for the superior strontium uptake. And if I'll count to the number, adsorption capacity for as prepared and water vapor exposed graphene oxide membranes. So at 0.1, we will see that only graphene oxide has shown 335 milligram per gram of strontium adsorption capacity, which has increased to 515 milligram per gram. And with increase in mass, we have seen that decrease in adsorption capacity, same has been followed by water intercalation. So as a conclusion, hydration is a chemical-free approach for surface modification of graphene oxide. Graphene oxide membrane shown enhanced strontium adsorption when subjected to water vapor, especially steam, and hydration amongst relative ratio of functional groups, especially sp2 carbon, epoxides and hydroxides. Strontium adsorption capacity, the best strontium adsorption capacity shown at the least minimum possible mass what we have achieved, that is 0.1 milligram of graphene oxide membrane. The next enhancement in strontium sorption capacity is attributed to amendments in relative ratio of function group of graphene oxide and the stronger hydrogen bonds forming between the oxygen and hydrogen function groups between the graphene oxide sheets. and then the overall interaction behavior of hydration graphene oxide, which is ultimately facilitating the more favorable or more reactive sites for strontium to obtain. These are my references. Thank you.
Okay, thank you. Very good, very nice work.
Thank you, sir.
So the water from particularly you are focusing which water
Water.
to be purified by your developed geo.
Yes.
That means particularly which area of water or what water source you are using
Okay.
that is strontium rich.
Okay, no. So basically, we have started that from aqueous solution. We have prepared a stock of strontium solution with different concentrations, and then we have done this all analysis, all batch of experiment. But that objective of mean work is to separate this strontium from HLLW, high level liquid waste. Since I'm working in IGCR, Indira Gandhi Center of Atomic Research, their work should be attributed towards nuclear industry. So during reprocessing, alkali group metal ions will be there in reprocessing, and so that's why in high level liquid waste we want to do that. But before doing that, we have to study that full strontium and graphene oxide interactions between at room temperature and with aqueous medium. So once we have established this system, now we are moving towards the radioactive things. So this is.
Okay, after purification, suppose you have taken strontium rich water and you have added that is GO, graphene oxide, whatever is synthesized, then strontium is getting absorbed on the surface and the
Yes.
strontium quantity getting less. Then how come you are separating the all the GO and strontium or GO covered with strontium from water? How? By which
Okay.
technique? By what type of filtration technique?
No, sir. If I'll show my method again, I would like to brief my method that graphene oxide membranes we are preparing. So these are solid state
Okay,
based
you are
membranes.
passing over, you are
Yes, sir.
passing.
So then this filter method, I just want to show this.
Yeah, okay, I got it. Okay.
So
Secondly, on the graphene oxide membrane, you have grown on what substrate, or it is self-sustaining membrane?
no, sir. Actually, we are parallelly working on freestanding membranes also. But since freestanding membranes are not stable in aqueous medium, so this for this work we have completely devoted for graphene oxide, uh, um, um, which is being deposited on MC membranes and mixed cellulose ester membranes we have taken. For membranes also as a supporting membrane. For membranes also we have done study for nylon membranes, other polymeric membranes, but we have seen that
Yes, yes.
MC membranes, that is the mixed cellulose ester membranes, that is having the maximum hydrophilicity with respect to graphene oxide. And then we have opted for this MCE membrane, that is mixed cellulose ester membranes, and then we are percolating graphene oxide dispersants on that. Then with vacuum filtration setup, we are taking this membrane which is already being deposited with graphene oxide dispersants. Once we will take it, and then we are keeping it inside desiccator till it reach constant weights. Twice or thrice we will weigh their weights. So once it will reach their its constant weight like zero point 0.1 milligram, 0.2 milligram, or whatever x milligrams, and then we will percolate again aqueous strontium solution. Sir, one more objective of using this vacuum. Objective of using this solid state based membranes. So once we will reach to active part, then in active part liquid waste itself is a big problem. So with this, it can be kept in a closed compact cell. So having this objective also, we have opted for solid state based membrane. And the question related to graphene oxide, how we are separating. So parallelly we have done graphene oxide and strontium centrifugation separation using centrifugation process. So strontium we will take it out from pipette with the help of pipette, and the residue left, that is graphene oxide, then we can separate it very well with the help of centrifugation process. That's it.
Thank you. So this was query I am having. It's a wonderful topic. Okay, thank you for your work and all the very best for the rest of the work. Thank you. So may I have the next presentation, or if the audience is having some questions, they may ask. So stop sharing, and who will be presenting next?
Thank you, ma'am. And next, I would like to call Amit Kumar Gantayat. And
Yes.
he's from Mechanical Engineering Department, Veer Surendra Sai University of Technology, Odisha, India. And his topic is analysis of a graphene X pattern reinforced axial functionally graded non-uniform polymer matrix non-composite beam.
Good afternoon, everyone. Is my slide visible and my tone is audible?
Yes, it is visible, but it is not in the presentation mode. Just maximize it.
Yes, sir. It is already in presentation mode. It is in full screen.
No, okay, you just move the slide. Move your slide. Just putting the down arrow. Just
Yeah,
pressing the
sir.
down arrow. It is
Yeah,
not moving.
it is not moving.
You just share your entire screen. Same problem. Share your entire. First, you just stop sharing. Share your entire screen. Then come to the. Actually, we are not getting the full screen. Yes. Do it again.
Okay, sir. Just a minute. Now it is visible, sir.
No, it has not come.
Hello.
Share your screen. Your screen is not at all shared.
So now it is visible.
No, not. Just share your entire screen. Hello.
Yes, sir. I am
Share your
clicking
entire.
share entire screen. Yes, sir.
No, no, no. I am not getting. At least whoever are they getting. I am not
No,
getting your screen.
we are unable to see that full screen.
What said Rini? Are you getting the
Sir, what you are facing,
slash?
same full screen, we are unable to see.
Now your screen is shared almost, and maximize your presentation.
Sir, it is in slide show mode. Now it is okay, sir.
No, I am getting your photo only. Your profile pic. I'm getting your profile pic only.
Sir, can convener can help?
Three dots are
Yes, sir.
there. If you click on
Yes, sir.
three
Yes.
dots, share your entire screen. One option will be coming. Then
Yes,
it will be
sir.
share. Yes, yes. And maximize your presentation. Maximize your presentation. Click on the hide button. Yes. Yes. Now it's okay. Continue. Yes, your presentation is opening. Yes, maximize it. And come to the presentation mode.
Yes, sir.
Yes, continue. Now it's okay. Okay, start speaking. Start presenting. Hello, Amit Kumar, are you? Your voice is not coming. Amit Kumar, are you there? Lot many network issue, I think.
I think he'll rejoin, so we can just wait for.
Okay, okay. So in the meantime, we'll accommodate the next speaker. Yeah, we'll wait for the Amit.
So there's Kavita Illathu from the Department of Engineering and Design, IIT Madras. So Ms. Kavita, are you ready for your presentation?
Yeah, I can present.
Okay,
So
please share your screen, entire screen, and maximize your
Yes,
presentation.
yes, yes, sir.
So Ms. Kavita Illathu is from Department of Engineering Design, IIT Madras, India, and she's gonna present her presentation on tunable synthesis of spiky gold nanostars using symmetric flow focusing microfluidic device.
Shall I start?
Yeah, start, continue.
Myself, Kavita Iyer. I'm doing PhD under the guidance of Dr. Toin Subrasandra of Engineering Design Department at IIT Madras. Today I am here to present my work on tunable synthesis of spiky gold nanostars using symmetric flow focusing microfluidic device. So this is the outline of my presentation. Coming to the nanomaterial synthesis. Generally, nanomaterials are synthesized in a conventional batch reactor method. That means in a conical flask, we add the reagents manually one by one, and here we can have the control over spinning as well as heat over a particular duration of time. On the other hand, in the microfluidic device, we have several inlets and outlets which are connected with micro channels. And from the outlet, we can collect the generated nanoparticles with the tubings, and through the inlet, we can supply the reagent solutions. And one of the important microfluidic platform is the droplet microfluidics. Here we have two immiscible phases. These are the three geometries which are used for achieving droplet microfluidics. One is axisymmetric, T-junction, and symmetric flow focusing. Here we use immiscible fluids, oil and aqueous normally. And at the junction of oil and aqueous phase, due to the interaction between shear force and surface tension, droplets are generated. Now for the nanomaterial synthesis, normally reagents will be in the aqueous solution form, and within the droplets, these reagents will be mixed. So for the controlled nanoparticle production, homogeneous droplet production is needed. So if we can achieve a droplet production prior to the particle synthesis by tuning the parameters, it will be advantageous. So normally we can use the computational fluid dynamics models for in order to achieve this. Level set is one of the such method, and in 2020, Kasper et al. Utilized the level set method in his microfluidic platform to synthesize the iron oxide nanoparticles. So in this work, I will be utilizing level set method for my nanostar synthesis optimization. So first this is the methodology which I follow. First CFD simulation, which is carried out in COMSOL multiphysics software. Level set is used, and here I varied a capillary number as well as a flow rate ratio, and the pressure oscillations were captured according to the time. And next I validated the simulated results. For that I fabricated symmetric flow focusing device PDMS based using the soft lithography procedures. And the droplets were evaluated under the microscope and compared the results with the simulation. Next, after optimizing the parameters here, I moved to the golden nanostar synthesis, and here I selected the reagents according to the nanostar formation, and in order to tune the plasmonic properties of a golden nanostar, I varied the flow rate as well as concentration of reagent. Now moving to the results. This is the 2D geometry of the symmetric flow focusing device I used. So the width of the channel is 80 micrometer till the flow focusing junction, and after the flow focusing junction width is 120 micrometer, and the silicon oil is used as the continuous phase, whereas the disperse phase is water, and the properties of the fluids are listed here, and the channel height is kept as 150 micrometer everywhere. the dependency on capillary number. So here two images are there. Left one corresponds to the capillary number, very low capillary, that is at a 0.001, and the right one is at a 0.01. And these are the stages involved in the droplet formation. Here we can see it is lagging, filling, spreading, necking, detachment, and droplet reshaping. Extra blocking stage is there compared to the right one. So at a very low capillary, we observe that complete blockage of water thread happens. So the droplet formation mainly depends on the surface tension dominated. Here, there is no blockage, and the droplet formation is mainly depend on the shear force dominance. And this is the quantified results. Now we will see the effective flow rate ratio. For that, we fixed our water flow rate at 900 microliter per hour and varied the flow rate. So this video shows the droplet formation at a flow rate ratio of 0.7. So here only water flow rate is fixed, and oil flow rate we were continuously decreasing. So this is the droplet size, quantification of a droplet size as well as production frequency. We can see that with the increase in flow rate ratio, droplet size is increasing. As the water flow rate is fixed, in order to maintain this constant mass flow rate of the water, the production frequency is decreased. And this is the droplet size graph only, but it is with respect to time. So here we have each cycle what is the size of the droplets. So with the increased flow rate ratio, we found a similar trend. Droplet size is increased, and also found that number of cycles are reduced. That means production frequency is reduced. Now we evaluated the pressure oscillations at the one particular point that we found at the 180 micrometer apart from the droplet tension. Here we observed that as flow rate ratio is increased, pressure oscillations are decreased. Hence, the number of droplets generated is decreased. That means the droplet production frequency is decreased. Also, we found that the maximum value of the pressure value is decreased drastically. Another important thing is there is a transient in all the flow rate ratio in the beginning. You can see for the first 3-4 droplets, it is completely different from the next. So for the stabilization, it takes some time. Now we move to the experimental validation. These are the microscopic images of droplets generated at various flow rate ratio. At Q equal to 0.1, the droplet size is comparable with the width of the channel. At extremely large flow rate ratio, we found the droplet size is very large, and this is the comparison with the droplet size obtained with the simulation results. Now moving to the golden nanostar synthesis. This is the schematic of the microfluidic device. So here you can see this is the droplet junction, symmetric flow focusing junction, and in order to form the golden nanostar, I introduced sinusoidal geometry, two sinusoidal geometry as well as one semi-spiral microchannel. And here we can see total 6 inlets. One inlet, this is corresponds to the silicon oil, and all the remaining 5 inlets are corresponding for the reagent solution in water. And this is the outlet through which I can collect the golden nanostar. And this is the final photographic image of the device. Now moving to the reagent mixing for the nanostar. So this is the result for the concentration distribution. In the first junction, we added gold seed, gold precursor as well as HCl, and after moving through the sinusoidal geometry, we found that mixing is really improved. And at the second junction, we added AgNO3 as well as ascorbic acid together. This is important for the nanostar formation. So for the complete reduction of the gold precursor, it has been found that silver nitrate as well as ascorbic acid has to be introduced together. So in a conventional batch reactor, this is very difficult. Technically, it is challenging and difficult to achieve. but in a microfluidic platform, it can be achieved easily. Now moving to the characterization of a golden nanostar. My aim is to tune the plasmonic properties of a golden nanostar. In order to tune that, I varied the flow rate of a silver nitrate from 180 microliter to 540 microliter per hour. So I found that as the flow rate is increasing, the graphs move to the red shift. And also I observed that at a particular 360 microliter per hour flow rate, after that monodispersity is monodispersity is decreased, or the spectrum became broader. And also the absorbance peak, if we evaluate, hello. Okay, after 360 microliter per hour, it is observed that there is a sudden jump in the absorbance peak as well. So, in order to confirm the morphology of the nanostar synthesized, we evaluated the 10 micrographs at a 180, 360 as well as a 540 microliter per hour. We found that at a very low flow rate, core diameter is very large, as well as branches are not so visible. And in the at 360 microliter per hour, core diameter became smaller and the branches are become uh, somewhat sharper and visible. And at 540 microliter per hour, branches again became more sharper compared to 360 microliter per hour. And there is a non-uniformity in the nanoparticles as well. Now we quantified the core diameter as well as tip-to-tip length of the nanoparticles obtained at these three flow rates. So the results show that as the flow rate increases, core diameter decreased as well as tip-to-tip length increased. And this in turn, tip-to-tip length increase means overall size of the nanostar is increasing. So this was confirmed with the DLS data also. Here you can see the size is increased, as well as surface theta potential. We found that it is decreased. It is increased in the negative direction. Now, similar to the flow rate of silver nitrate, we varied the silver nitrate concentration and observed the absorbance spectra and found that it is first initially it red shifted, and beyond the 0.3 millimolar it is blue shifted. So now we fixed our concentration at a 0.3 millimolar. As we if we want to use the golden nanostar for photothermal or any plasmonic related application, bio application, it is recommended the near infrared region is favorable for the bio application. So I fixed the here the plasmonic peak is maximum nearly around 900 nanometers. So I fixed my concentration at 0.3 millimolar. So concluding my works. So in order to obtain the homogeneous distribution of nanomaterials, homogeneous droplet production is demanded. And using our simulation results, by controlling our capillary number as well as flow rate ratio in for a specific dimension of a flow focusing droplet device, we achieved controlled droplet production. And in order to synthesize golden nanostar, extra sinusoidal channels as well as semi-spiral microchannels were introduced. For tuning the plasmonic properties of a golden nanostar, we tuned the flow rate of as well as a concentration of a shaping reagent, silver nitrate. Also, the negative value of surface theta potential also we tuned by changing the flow rate of the shaping reagent, silver nitrate. Now, overall, the work demonstrated that the nanostars with exceptionally good monodispersity along with the tunable plasmon resonance can be synthesized by our microfluidic platform, and this is a very promising candidate for photothermal and photodynamic therapy, which is in that we need to tune the plasmonic properties. These are the important references. Thank you.
Now this is open for a discussion.
Hello, sir.
Okay, anyway, I don't have any question on this topic. Um, so if somebody is having some question, you can ask. Otherwise, we'll move to the next presentation.
Okay, shall I stop sharing?
Yes, yes, you stop sharing.
Okay, thank you, sir.
Dr. Gabriela Virendra. Dr. Gabriela, I'm sorry. I think you have joined the wrong link. Can you please come to hall 1? I'm sorry, Chair. Can I inform? Yes, please join hall 1. We can't hear you. Can you please unmute?
I
Dr.
cannot
Gabriela?
connect to the whole one. I can
Okay, we
connect to
will.
the whole two, but I cannot connect to the whole one.
Okay, we will send you the link once more. You just sign out from this and then please join again.
Okay.
We have started the next talk, but we can have your talk after that, after the talk of Professor Ilaria. Yes, dear Chair, please continue.
Now the session is over. Now I would like to extend my sincere thanks and gratitude to Dr. Bibu Prasad Sahu for your nice and kind chairing.
Thank you, ma'am. Thank you a lot. This is a really wonderful session, and I would like to express my heartiest thanks to Team ICN 2022 for selecting me to chair this such a wonderful session. I will really all the talks are awesome, very nice, and the presentation was very good. The interaction is also very nice. I learned a lot, many things from these presentations. Okay, I wish all my good luck to the presenter and the youngsters. Okay, thank you.
Thank you so much. So now we are moving on to the next session, which is on nanocomposites, and we have Dr. Shivraj Paul from Department of Physics,
I'm not the
NIT
chairperson
Agartala.
of the coming session, ma'am. Sorry.
Sorry.
I am not the chairing. I will not chair the coming session. Right? I can leave.
Yeah, sure.
Okay, thank you, ma'am.
Thank you. So, Mr. Shivraj Paul is from Department of Physics, NIT Agartala, India. So he will be sharing on tuning of memory effect with magnetic field of Na and copper dot ferrite nanocomposites. Over to you, sir.
Okay. Good afternoon. Am I audible?
Yeah, you're audible.
Okay.
Not yet.
Does the
Sir.
screen visible, ma'am? Oh, okay. Just a minute. I have to share.
Perfect.
The screen is visible now? Okay. So good afternoon. I'm Shubharaj Pal. It's my proud privilege to give the deliberation in front of all the dignitaries. So I'm from a Department of Physics and IIT Agartala, and my work to this presentation is based on a tuning of memory effect with magnetic field of nickel and cobalt doped ferrite PZT and the composite. Okay, this is my plan of talk. I will introduce some basic things and sample preparation, resultant discussion, and conclusion. So we know the digital memory like magnetic memory, electrical memory, optical memory, and out of these three memory, magnetic electrical are very prominent because of permanent storage capability, first access, retrieval time, and large capacity. And in my work, I have focused on electrical bistability because the device exhibit two states of different conductivities at same applied value. I will elaborate this later. And for this reason, our material of interest are magnetic multiferric material, because this material can show the piezoelectric and piezomagnetic phase, and they have well magnetoelectric coupling response. So this is the route map, how I have prepared the sample. have taken aqueous solution of requisite amount of compounds and CFO in stoichiometric proportions. Then we have applied triethylamine HNO3 steering, then heated at 180 degrees C for 30 to 40 minutes, and precursor generates, then grind it, calcination, the nickel NCF particles are generated. We have mixed with PZT powder and 30:70 ratio, grinding time duration for 10 hours, then formation of pellet, and then sintering at temperature of 800 degrees C almost. This is the route map, and the process adapted here is pyrophoric chemical process and solid state reaction process. So this is the structural characterization. The structural characterization has been carried out using Bruker-Date Advanced XRD and high resolution scanning electron microscope. So XRD pattern reveals that the coexistence of two phases, that is piezoelectric phases and piezomagnetic phases only, and there is no presence of any secondary phases. And the diffraction peaks is well matched with the ICDD PDF2 curve mentioned here, number 000103225 for NCFO and cut 010732022 for PZT phases. This is well matched diffraction peaks, and it is gives a clear evidence that only two phases, piezoelectric phases for PZT, piezomagnetic phases for NCFO is present there. And the scanning electron microscope at 200 nanometer dimension indicates that there is no phase segregation and good chemical homogeneity is present. We have calculated the average crystallite size using Scherer formula that is mentioned here, phi equal to k lambda by beta effective cos theta. A is constant and lambda is 1.54 angstrom because we have used the copper K alpha radiation during the XRD process. And using this formula, we have calculated the NCFO size is 52 nanometer around and PZT is 54 nanometer around. That is all the particles in the nano region. Okay. Now we have studied the DC electrical property of the composite NCFO PZT nanocomposite. See here in DC electrical property, we have taken -20 to 0, 0 to +20, and then again come back 20 to 0 and 0 to -20. So out of the fourth segment from +20 to 0 and 0 to -20, the IV curve shows some non-linear behavior. And you can say the IV characteristic curve shows hysteretic behavior, which corroborates the electrical memory effect. And this, what is the reason behind the non-ohmic behavior? The reason behind the non-ohmic behavior is due to the oxygen vacancy and defect state of nanocomposite. Because we know oxygen vacancy and defect state of nanocomposite are situated at the grain boundary. What happens? The oxygen vacancy state accumulates charge carrier and defect state tunnel the charge carrier, and due to this, the conduction process enhanced. Okay. And then we have studied the variation of current with the magnetic field for two different voltage for +20 volt and -20 volt. We have show the variation for current with respect to magnetic field. And see, current is almost increasing with magnetic field, reveals the increasing conduction of charge carriers through grain and grain boundary. Why it is happening? Because when you apply the magnetic field, the magnetic particle tries to align along the direction of the magnetic field, and which deform the shape at the grain boundary, and due to the deformation of the shape of the grain boundary, it exerts pressure on the piezoelectric phase of the nanocomposite, which generates some charge carrier and conduction process is enhanced. And we have studied the variation of magnetocurrent versus H, MC percentage versus H, and we see that maximum MC percentage value of the composite is found to 28% at 3 kilo-ohm magnetic field, having a constant value of +20 volt. And from this, actually what happened, from this we can calculate the magnet resistance percentage. Yet we have to calculate, it will be calculated. This we have just showing the variations of MC percentage versus H. And later, very important thing is that we have fitted the IV curve in logarithmic scale using Child's law. This is I proportional to V to the power m. M is the fitting parameter, which varies from 1.0035 to 1.0088, and it is increasing with increase of H. Actually, M is the determining factor, because see why the IV characteristic curve is non-linear. there are several reasons. One may be due to defect state, oxygen vacancy, space charge polarization, space charge limited current, like this. So the value of M, if almost 2, then space charge limited current will dominate, and which is the responsible factor for the nonlinear behavior of IV characteristic curve. But in our case, the value of M well below 2, that is, it is C, defect 12008, it is well below 2, supports the facial polarization and space charge effect in the process of conduction mechanism. That is, the nonlinear behavior of IV characteristics is due to the interfacial polarization effect, because the value of M is well below 2. In a brief, we have successfully fabricated the ferrite PZTV composite sample. Structural characterization expresses the formation of both the phases and age-dependent diselectrical property, that is IV characteristics, shows history as a function of voltage. Maximum change of MC percentage is found to be almost 20 range. Value of M below of 2 supports the dominating of interfacial polarization in the process of conduction mechanism, because we can explain field. So these are some important references learned a lot and utilized. Thank you.
Thank you for the wonderful presentation, and now the session is open for discussion. If audience have any question, they can ask now.
Hello. Hello, ma'am.
Yes.
Okay. My presentation is over.
Yeah. We are asking for the audience to ask questions. Sir, I have a question.
Hello.
Can you hear me?
Yes.
So, to which area do you think we can extend the tuning of memory effect with immediate effect?
Actually, the voice is breaking, madam.
To which area can we extend the tuning of memory effect with the immediate effect? Application part.
Sorry, I'm not getting, madam. Maybe some due to network issue, the voice is breaking.
Okay, so thank you so much for your presentation, Dr. Shubraj Paul. Now we can move on to the next speaker. Let me invite Dr. Anjali TR. She's from a Department of Physics in Center for Research, Central Research College, Ernakulam. And she's going to present on GeoAG nanocomposites as an efficient source substrate for the detection of chemicals.
Hello.
Yeah. You're audible, ma'am.
Okay. Hello. Can you see the slide?
Yeah.
Hi everyone, I'm Anjali Tiyar from St. Teresa's College, doing my project under the guidance of Dr. Priya Parvati Amina Jose. First of all, I would like to acknowledge the organizing committee for providing me an opportunity in participating in this international conference. And today I'm going to discuss a part of my MPhil project done under the topic reduced graphene oxide silver nanocomposite, which can be used as a Ceres substrate so that it can have certain applications including the sensing or detection of some chemicals. So here I explore the technique Ceres, that is surface enhanced Raman scattering or surface enhanced Raman spectroscopy, which can be applicable on metal nanostructures with some surface plasmodes. Since this technique can enhance the Raman scattering by the targeted molecule and can give a fingerprint of the targeted molecule. So here, why I choose this graphene oxide nanocomposite? This is mainly because some of the properties of graphene oxide have already discussed by Rini Vishwakarma. So I'm not going to so much deep, but I would like to say one thing, that the graphene oxide is considered as the hydrophilic oxygenated functional group. So it is actually a two-dimensional mesh which contains the hydrogen, carbon, and oxygen in different ratios. So because of that reason, it shows a variable stoichiometry. So this open up a way for the sensing capability of some targeted molecule. And the synthesis part of this graphene oxide include both the oxidation as well as reduction process. So here, the structure of the graphene oxide itself is shown that it consisting of oxygenated functional groups like hydroxyl, epoxy, carboxy, carbonyl, and so on. So here, the synthesis part of the graphene oxide is actually done by a simple, faster, and an efficient method put forward by the Hammer and Ockman, which is called as modified Hammer's method. It's a bottom-up method where the nanostructures are constructed from the atoms. And here I use the graphite plates, potassium permanganate, sodium nitrate, and sulfuric acid. So here, actually, the oxidation and exfoliation of the graphite flakes is happening, and oxidizing agent is sulfuric acid. So here comes the importance of the silver nanoparticles. Since most of the researchers have already reported the Ceres property of the silver nanoparticle, since these metal nanostructures are usually consisting of surface plasmodes, which can add up the Ceres or the enhanced Raman spectroscopy when deals with some chemicals, and hence it can show some antibacterial activities as well as some other properties also. So this silver nanoparticle excellent Ceres property has already determined. So while when you add this silver nanoparticle or when you integrate this Ag plus ions on the graphene oxide sheet, it can enhance the Ceres property. It is mainly because of the strong pi-pi interactions in the graphene, as well as their enhanced properties including mechanical, optical, or electrical, thermal, etc. In addition to that, the electromagnetic field enhancement is also adds up some additional properties for this application level. So here the synthesis of the reduced graphene oxide silver nanocomposite was done by using a simple low-cost method called a solvothermal method. And the characterization of the reduced graphene oxide by silver nanocomposite is shown here. The first figure will shows that the X-ray diffraction pattern of the as prepared sample, and it reveals that the major peaks of these different crystalline planes of silver nanoparticle. And in addition to that, you can see an inset picture which simply indicates that the unoxidized part of the graphene oxide. And the second figure indicates the UV visible analysis. And here also you can see a bump near the visible region, which is mainly because of the carbon oxygen groups, that is n-pi transition of this carbon oxygen group. And in the figure 3, you can see a Raman spectra of the reduced graphene oxide silver nanocomposite. And here the two peaks corresponds to the D band and the G band, that is the defect band and the grain band. And the SEM images are also shown here. And from the SEM images, you can see that the morphology of this as prepared sample is spherical in shape. And the calculated value or the measured value is also in nanometer range, and it is approximately 50 nanometer. And the TEM image is the last image you can see here, is also determined. It can also reveals the diameter is in the nanometer range. And the last is the selected area electron diffraction pattern, that is the seed image of the as prepared sample. And here comes the applications. Because of the enhanced Serres property or enhanced Serres application, it can be act as an excellent sensor or dye sensitization, biomedical activities, photocatalytic activities, and so on. So here I am used this prepared sample as a sensor or a detection for some kinds of dye. Usually several dyes are used by today's industries as well as all the factories, including the crystal violet, methylene blue, rhodamine 6G, etc., are really harmful for the human life. So it is high time to think about the detection even at the very low concentration. So here it is possible by using this reduced graphene oxide silver nanocomposite. And here comes the Raman spectra or the Serres application of this as prepared sample. The first figure indicates the Raman spectra of the clear or the bulk crystal violet, and in the second figure you can see its detection even at very low concentration, because this graph represents the crystal violet with the different concentrations ranging from 10 raised to minus 5 to 10 raised to minus 11. And here you can see the peaks are represents the corresponding crystal violet itself, but their intensity is decreases by decreasing the concentration, but even at a very low concentration it is able to detect on this Serres substrate. So one of the application is detection of this dye, and the other application, it can be used as a sensor for the pesticide detection also. Not all pesticides, but the pesticides which contain some certain functional groups like thiol, amine, etc., can be determined by using this Serres substrate. And here I used to check the detection of the pesticide thiram. And here also, this figure first, you can see the Raman spectra of the Preston thiram, and the second figure is indicating the Raman spectra or the surface enhanced Raman spectra of this thiram for different concentrations ranging from 10 raised to minus 5 to 10 raised to minus 9 molar. Here also you can see that the detection even at a very low concentration is made possible on this reduced graphene oxide silver nanocomposite. So I can say that it is a better substrate for detecting such kinds of chemicals, both dye as well as the pesticides on this Serres substrate. So here comes the future hopes as well as the conclusion. Since certain chemicals that containing the thiol or amine or some dyes can be detected by using this Serres substrate, that is the silver reduced graphene oxide silver nanocomposite Serres substrate. So thereby it comes to the application. And here is the important references that I followed. So thank you. Hello.
Yes, ma'am. Thank you, ma'am. Now the
Thank you
session.
for the nice presentation.
Thank you for the nice presentation. And now the session is for open discussion.
Okay.
Anyone have any question? Can ask. Any questions from the delegates, audience? So thank
Madam, hello.
Dr. Amit.
Yeah, madam. Actually, my participation code is SIL14. During presentation, my connection has been lost, madam. Actually, I could not able to know during presentation.
Okay, so do you want to do the presentation once more?
Yeah, madam, definitely.
Okay, just 1 minute. I will confirm now.
Yeah.
Okay, so I request you to do your presentation right now.
Yeah, madam.
Okay, can I stop my presentation?
Yeah, just any questions from the audience?
So if not, thank you, Dr. Anjani, for your nice presentation.
Okay,
Now we
thank
will
you.
go to the next presentation by Dr. Amit Kumar, Mechanical Engineering Department, Veer Surendra Sai, University of Technology, Odisha, India.
Yes,
Dr.
madam.
Amit, please.
Yeah, madam. Just a bit. Is my voice is clear, madam?
Yes, your voice is clear and your presentation is coming.
Just.
Yes,
Is my
yes,
presentation
it's
is
full
visible,
screen
madam?
now. Please start your presentation now.
Okay. First of all, thank you, madam, that you are giving me opportunity to present again. My good name is Amit Kumar Panchayat from Veer Surendra of Technology, and I am a research scholar. My presentation is analysis of graphene X pattern reinforced axial functionally graded non-uniform polymer matrix nanocomposite beam. Am I audible, madam?
Yes, you are audible.
Hello?
Please continue.
Yeah. So in this topic, we will see that how the in structural aspect we see that how the nano composite beam is behaves to the dynamic behavior, that is the natural frequency. And before that we go to the topic, we our outline is this that. And the topic importance is that before as pure material we consider that in trading not that economical loss, as well as the thing is getting heavy as where conventional metals are used. Then we go for the alloys. Alloys is somehow extent it has to modify material. Due to some drawback like thermal inequilibrium, the alloy is also some having disadvantages or not optimum as the engineer is not optimum as we require property at every point. Then we the proceeding become the material, which is far extent towards economy as well as the desired properties as well as lightweight and stiffness ratio. And then the least drawback is the delamination effect. And overcome the functionally graded. And in functionally graded metals, you can apply the material what is the material that manipulating our reinforcement in functional manner. How we implement is Hello.
Your sound is not clear that much. Yes, now it's better.
The go through many stages, and the advantage become better and getting into properties, the mechanical thermal properties are far better than the conventional material. And
Yeah, Dr. Amit's connection, there is some problem with the connection of Dr. Amit. So I think we will give him a chance after this if we have time. We will end this session. And now we have the next session on biomedical application. Since both chairs are not present till now, Dr. Kashya Gandhi, can you please share the session? Dr. Kashyar, are you there? Dr. Kashyar Gandhi, are you there? Dr. Kashyar Gandhi? So if not, I request Dr. Hiran to chair the session.
Hello. Hello.
Dr. Amit, we will.
Yeah.
I think there is some connectivity issue. I request you to
Yeah.
check your internet connection and please come again. We will give you another chance.
Yeah, madam.
But
Hello.
now we have started the next. We are going to start the next session. So we will give you after this session one more chance. So please make sure that your internet is okay. Can you please check your internet connection and please come again, okay?
Yeah, my presentation is visible now, madam.
Dr. Amit, we are not able to see your presentation, and there was some connectivity issue, and your voice also was not clear. So we will now go to the next session, and we will come back to you after this.
At what time I will present?
You can present after this session. We are going to start the next session, Dr. Amit. Okay.
Okay, madam. Okay, madam. I am waiting. Okay.
Yeah. So I request Dr. Hiran to chair the session.
Starting. So the next session is on biomedical applications, and so I first invite SIL 19 Bonnie K. John, School of Chemical Science, Mahatma Gandhi University, Kottayam, India, to give his presentation on microwave-assisted synthesis of nitrogen-doped carbon quantum dots as a fluorescent sensor for amoxicillin. Bonnie, are you here?
Yes, sir, I am here.
Okay, you can make it full screen and start your presentation. Okay.
Okay, am I audible, sir?
Yes, you are audible.
Yeah, screen is visible?
Yes.
Yes. Okay. Good afternoon to all. Hello? Hello, sir?
Yes, please continue. We can, your presentation is very clear and your voice is good.
Okay. Thank you, sir. Good afternoon to all. Welcome to my presentation entitled Microwave Assisted Synthesis of Nitrogen-Doped Carbon Quantum Dots as a Fluorescent Sensor for Amoxicillin. Presentation outline introduction, synthesis and characterization of nitrogen-doped carbon quantum dots, NCQDs as a fluorescent sensor for amoxicillin molecules, and conclusions. Introduction. The quantum dots are zero-dimensional semiconductor nanomaterials having a particle size of less than 10 nanometer. Carbon quantum dots, also called CQDs, are zero-dimensional semiconductor nanomaterials composed of sp2 hybridized graphitic carbon atoms. During the last few years, several facile and inexpensive synthetic methodologies have been developed from chemical and green precursors for making CQDs with desired physical and chemical properties. Doping the CQDs with heteroatoms is an interesting and efficient technique to enhance the quantum yield of carbon quantum dots. Among the various elements, the size similarity between nitrogen and carbon atoms allows effective doping. In our work, we have synthesized nitrogen-doped carbon quantum dots from a mixture of beta-cycloadduction and ethylene diamine through a microwave irradiation method. Initially, we have mixed beta-cycloadduction and EDTA with 2 molar sulfuric acid and distilled water in a conical flask, followed by a microwave irradiation for 12 minutes at 450 watt. After 12 minutes, we got a brown-colored brownish yellow NCQD solution, which were filtered using a nylon 6s membrane. We get a clear brownish yellow NCQDs, which is brown in color under visible light and exhibit a blue luminescence under UV radiation. Optical properties. UV visual spectra of the fabricated NCQDs exhibited 2 characteristic peaks at 213 nanometer and 282 nanometer, corresponding to pi to pi star and n to pi star transition. The fabricated NCQDs exhibit PL emission at an maximum PL emission at an excitation of 360 nanometer, corresponding to the emission at 445 nanometer. Okay. in order to optimize the wavelength at which the NCQDs exhibit maximum PL emission, we have optimized the PL emission properties of the NCQDs by recording the PL spectra by exciting the sample from 300 nanometer to 400 nanometer. From the graph, it is clear that on exciting the NCQDs at an excitation wavelength of 360 nanometer, we get maximum PL emission at 445 nanometer. Structure properties. TEM EDX analysis shows that the fabricated NCQD is composed of the elements nitrogen, oxygen, and carbon. The Raman analysis shows two characteristic peaks at 1356 and 1591 corresponding to graphitic carbon D and G band. This band confirms the existence of well-graphitized carbon atom in the fabricated NCQDs. FTR shows exhibited several peaks corresponding to OH, NH2, sp3 hybridized CH3, C double bond O, C double bond C, C single bond O bonds, which confirms the presence of several functional groups on the surface of the NCQDs. XRD analysis shows that the fabricated NCQDs are amorphous in nature with an 2 theta of 26.04 corresponding to graphitic 002 plane. The TEM images shows that the fabricated NCQDs have a particle size of well below 10 nanometer. SID pattern further confirms that the fabricated NCQDs are amorphous in nature. The particle size distribution shows that the size of the average particle size of the NCQDs are around 6 nanometer. Optimization. Further, we have developed the fabricated NCQDs as a fluorescent sensor for the detection of drug molecule amoxicillin. For that, initially, we have optimized the pH and interaction time of the amoxicillin molecule with the NCQD solution by recording the fluorescent spectra at a different pH and interaction time. From the pH diagram, we can say that by changing the pH from 3 to 9, the maximum fluorescence quenching was observed when the pH of the system is 4. Furthermore, after mixing NCQDs with the amoxicillin molecule, an interaction time of 2 minutes is more than sufficient for the successful interaction of amoxicillin with the surface functional group of the NCQDs. So we have optimized pH 3 and interaction time of pH 4 and interaction time of 2 minutes for the further analysis. Study on interaction with the drug molecule. Initially, we have analyzed the sensitivity of the fabricated sensor towards different drug molecule. From the graph, we can see that only in the presence of amoxicillin molecule, a successful and well observed fluorescence quenching was observed. Further, move on to the concentration studies, we can say that on increasing the concentration of amoxicillin from 0 to 100 micromolar, there is a gradual decrease in the fluorescence intensity of the NCQDs. From the concentration studies, we have plotted a linear, we have plotted F0 by F and the concentration of amoxicillin graph. From the graph, we got a linear range of 0 to 25 micromolar with an LOD of 80 nanomolar. From the zeta potential analysis, we can see that the surface of the NCQDs are negatively charged and the fluorescence quenching may be arised from the successful interaction of positively charged functional group on the amoxicillin molecule with the negatively charged NCQD surface. Furthermore, indifferent studies shows that on mixing NCQD's amoxicillin mixture with the other drug molecule, in that case also, the fabricated NCQD system can effectively detect amoxicillin molecule. So there is no much interference from other drug molecule was observed. Mechanism of PL emission. In order to explore the mechanism, initially we have recorded PL decay curve of the NCQDs before and after adding amoxicillin. From the table, we can see that there is no much difference in the PL lifetime of the NCQDs before and after adding amoxicillin. Thus, it confirms that a static quenching is acting between NCQDs and amoxicillin. And also, amoxicillin on further exploring the mechanism, we can say that the amoxicillin molecule do not emit any fluorescence when exposed to UV light. So the possibility of a fluorescence resonance energy transfer can be neglected. Furthermore, there is no much difference in the lifetime of NCQDs and NCQDs amoxicillin system. So there is no chance for PET mechanism. Furthermore, comparison of UV visible and PL spectra of NCQDs, amoxicillin, NCQD plus amoxicillin and NCQDs excitation spectra shows that there is a considerable overlap between the absorption band of the amoxicillin and the excitation band of the NCQD solution. Hence, there is a possibility of inner filter effect mechanism was arise. Thus, we can conclude that a combination of static quenching and the IFI mechanism arised is responsible for the fluorescence quenching of amoxicillin, fluorescence quenching of NCQDs by the amoxicillin. And further, we have successfully applied the fabricated fluorescent probe to the determination of amoxicillin in real food samples such as milk and honey. In that case also, we got excellent recovery rate ranging from 90% to 101%. Conclusion. We have successfully established a simple and environmental friendly approach for synthesizing NCQs with a quantum yield of 15% from a mixture of beta cycloreduction and EDTA following a micro irradiation method. They exhibit a spherical shape and an average particle size of about 6 nanometer. As a PL sensor, they are very selective, and the extent of quenching is determined by the extent of amoxicillin ion coordination with the amine and hydroxyl group on the NCQD surface. The sensing process involves a static quenching associated with the IFE mechanism. This method exhibits an excellent linear range from 0 to 25 micromolar with an LOD of 80 nanomolar. The probe also demonstrated excellent precision without interferences and was successfully used to detect amoxicillin concentration in real food samples. Thank you.
It was a nice presentation, Bonnie. Now the session is open for discussion. If you have some questions, you can ask it down.
Question.
Hello.
Yeah, Suji, you are audible. You can ask question now.
Okay, my question is that have you tried any other applications rather than this detection, like some my shielding application? Because the material which we have synthesized in the green root is an excellent material for EMI shielding. So, have you checked it?
We have done further studies such as antimicrobial activity, bioimaging activity, cytotoxicity, etc. That are not included in this work, in this presentation.
So, my opinion regarding your presentation was excellent. So, my opinion, just my opinion, your material, which you have synthesized, is an excellent filler material, which you can incorporate in any polymer. You'll get good shielding. Radiation, you can fabricate shielding materials.
Okay. That's okay. Okay, thank you, man. That I also I will try.
Okay, that will be a very good point.
Okay. Thank you for your comment.
So if we don't have further questions, we can just conclude the session. Presentation.
Okay, thank you so much. Okay.
Thank you so much. Now we have Asta Gupta, School of Basic Sciences, Indian Institute of Technology, Mumbai. And the presentation is going to be on the topic disulfide cross-linked hydrosan stearic acid nanoparticles for gear drug delivery for colorectal cancer medical application.
Hello?
Yeah.
Yeah.
Can you share your presentation now?
Yeah, actually I'm trying, but my screen is stuck. Okay. Hello?
Yes, ma'am.
Yeah, I'm trying actually, but my screen is stuck. Actually, my laptop is hanged. Can I rejoin?
Yes, ma'am.
I'll try. I'm sorry, but my screen is stuck actually.
Okay, so
I'll
please
rejoin in a few
rejoin.
minutes. Yeah, I'll try.
Okay, please rejoin. By that time, we will go to the next speaker and we'll come back. Okay?
Okay.
Okay, thank you. So I request Dr. Mohan Dos. Are you there? Yeah.
Yes. Please share your screen.
Okay.
So the next speaker is Dr. Mohandos, Department of Botany, Sri Pushpam College, Tanjavur. Dr. Mohandos.
Yeah, I'm trying to share my
Okay,
screen.
okay. Do you have any difficulty? Yes.
Is my
Yes, it's
PPT visible?
visible. Please start your presentation.
Okay. Myself, Nilav Karisi Mohandas, research scholar. I am doing my PhD under the guidance of Dr. S. Vijay Kumar, PG and Research Department of Botany, AVVM Sri Pushpam College, Tanjavur, Tamil Nadu. My title is Investigation on Biofabricated Ion Axon Nanoparticles for Antimicrobial and Anti-Cancer Efficiencies. Introduction. Nanotechnology has developed a name in nanoscience during the past 20 years. The most significant transition metals for biological purpose is iron oxide. Hematite is the most stable polymer of iron oxide and its ideal biomedical applications. It is biomedical application due to its adaptable magnetic and optical characteristic, great chemical stability and biocompatibility. In the current work, ferric chloride hexahydride was converted into ionoxide nanoparticles using an extract of Capparis zeylanica leaves and were examined for antimicrobial and anti-cancer activity. Objective of this study: to synthesize ionoxide nanoparticles using aqueous leaf extract of Capparis zeylanica, to characterize the biofabricated nanoparticles using UV visible spectroscopy, XRD, FTIR, FSM with EDAX respectively, and to evaluate the antimicrobial activity of biofabricated ionoxide nanoparticles against human lung cancer, disease-causing pathogenic microorganisms such as Streptococcus pyogenes, Staphylococcus aureus, E. coli, Pseudomonas aeruginosa, Candida albicans, and Aspergillus niger, and to investigate its anti-cancer activity. Methodology: preparation of plant extract. Capparis zeylanica leaves were collected, dried, and to make it fine powder, followed by 20 grams of Capparis zeylanica leaf powder was added into 100 ml of distilled water, and then it was stirred continuously with the use of a magnet stirrer for 30 minutes. And the leaf extract was filtered with the Wattman #1 filter paper. The extract was stored and used for further process. This is the overall methodology of biofabrication of ionoxide nanoparticles. The Capparis zeylanica leaf extract was added into 50 ml of 0.1 molar ferric chloride hexahydrate. In the addition of plant extract, in the addition of plant extract, the color was changed into orange to brownish black color, and then the black color precipitate was formed. It was centrifuged for 30 minutes continuously, and it was filtered, dried in muffle furnace. The biofabricated ionoxide nanoparticles was used to analyze the characterizations such as UV, XRD, FTR, FSM with IDAX, and it was used to the applications like antimicrobial activity and anti-cancer activity. Results. Figure 1 shows the UV spectrum of biofabricated ionoxide nanoparticles. The prominent absorption peak at 354 nanometer correspond to ionoxide nanoparticles. The figure 2 shows the XRD pattern of biofabricated ionoxide nanoparticles. It shows the 2 theta degrees such as 24.716 at 012, followed by 33.52 at 104, 35.12 at 1110, 41.67 at 113, 49.79 at 024, 54.02 at 116, 57.22 at 018, 62.52 at 214,
63.82 at 300. Figure 3 shows the FTR spectrum of biofabricated iron oxide nanoparticles. The peak was observed in the range of 548.67 to 67 centimeter power minus 1 to 3407.63 centimeter power minus 1. Figure 4a shows the epistome image of biofabricated iron oxide nanoparticles. The spherical shape of iron oxide was seen. Figure B shows the histogram distribution of biofabricated iron oxide nanoparticles. The size distribution at 28.7 nanometer was observed. And then the 4C figure shows the hexagonal pattern of biofabricated iron oxide nanoparticles. The purified form of Fe iron and O oxygen can be seen in the ADAX. Figure 5 shows the antimicrobial activity of biofabricated iron oxide nanoparticles. The substance was tested for its antimicrobial effectiveness against harmful organisms such as Staphylococcus pyogenes exhibit the largest incubation, followed by Staphylococcus aureus, E. coli, Pseudomonas aeruginosa, Candida albicans, Aspergillus niger. With the use of agar-well diffusion method, the results of our synthesized nanoparticles antimicrobial efficacy against chosen microorganisms showed that they exhibit strong microbial activity. Figure 6 shows the entity assay and anti-cancer activity of biofabricated iron oxide nanoparticles. The substance has concentrated dependent cytotoxicity effect on lung cancer cell at a 15.6 mg per ml concentration, which is recorded as IC50 value. Iron oxide nanoparticle demonstrated. It shows that 50% of cells were killed. The human lung cancer cells were tested for cytotoxicity of iron oxide nanoparticles at a range of doses 1 to 100 mg per ml. A phase contrast inverted microbe was used to look at the cell growth. After receiving treatment with iron oxide nanoparticles, the lung cancer cells were shrank and their nuclei become fractured and compacted as shown in the figure 6b. Summary and conclusion. The present study focused on the productive and economical green production of iron oxide nanoparticles and an analysis of their microbial and anti-cancer property. The production of nanoparticles with a spherical shape and a crystal size of 28.17 nanometer was verified by the XRD and FSM measurements. It has also been demonstrated that the nanoparticles antimicrobial effectiveness was against the both gram-positive and gram-negative bacteria. The lung cancer cells were cytotoxically affected by the produce of iron oxide nanoparticles in the concentration-dependent manner. The synthetic iron oxide nanoparticles bioefficacy may make them suitable for use in biomedical and environmental domains. Thank you.
Thank you, Dr. Mohandos, for your nice presentation. So the session is open for discussion. Any questions? Yes, there is one question.
Ma'am, is there any cytotoxic effect?
Can you please comment on the cytotoxicological effect on the prepared material?
Dr. Mohandos, are you there? I think there is some connectivity issue. So I request Dr. Ashta Gupta is there. Dr. Asta Gupta.
Hello, ma'am. I'm trying to connect from another laptop, so
Yes.
I'll join in few minutes. Actually, my
Okay,
laptop
so
is.
we will go to the next presenter then. Okay. Okay, so now we will, I will call Dr. Hima Manoj, Department of Engineering Design, Indian Institute of Technology, Madras, to do your presentation. Are you there?
Yes, ma'am. Thank you, ma'am. Good afternoon, all.
Yes, thank you.
Good afternoon, all. Is it visible, ma'am?
Yes, it's visible.
Good afternoon, all. Myself, Hima. I am here. Myself, Hima, PhD scholar from IIT Madras. I am working under the guide of Dr. Tuhin Subrasandra. I am here to present my research work about infrared laser pulse mediated intracellular delivery using gold nanorod mixed PDMS pyramidal microtip device. So here introduction, objectives, and I'm going to present about microtip device design and their results and also the experimental results. So regarding the introduction, intracellular delivery is one of the most efficient technique which enables more efficient drug delivery, and the transfer of delivery will be internally only, not from the bloodstream. So here I am doing the intracellular delivery using pyramidal microtips, which are a micro scale device which are used to administer various biomolecules and therapeutic agents into the cell with help of micrometer structure molecules, about like 200 to 1 millimeter structures. So regarding the intracellular delivery, there are two types, that physical method and also chemical method. The electroporation, optoporation, microinjections are some of the examples for the physical methods. Electroporation is one of the method of physical method for the intracellular delivery, which use electrical pulse to create temporary pores that allow payloads to cross the cell membrane. But it has the disadvantages of high voltage, which results in field distortion, variation in pH, sample contamination, and toxicity effect. So when coming to mechanoporation, it is the rapid deformation of cell which will occur, and when it passes through a microfluidic deconstructions which generate transient poles. But it has also some disadvantages, like it can only deliver small molecules. Also it's non-uniform delivery. Regarding the microinjection, it is a mechanism which deals with the insertion of microneedle into a cell molecule with the help of microneedle. So, but it can't deliver the different big sizes of biomolecule, and also it needs skilled persons. So photoporation, it is a high, here we are applying a high intensity laser to the cell membrane to create permeable pores that can deliver the biomolecules. So when we apply the laser into the biomolecules, what will happen is it will happen a photothermal effect, which refers to temperature increase the following absorption of the photons by the molecules, and then because of this there will be a thermoelectric stress will be happening, that is cavitational bubbles, which contribute a pore in the membrane. So it has the advantages of non-contact, contamination free, targeted delivery for the different permeable molecules, and also it will help to create the pores which can be which can close a very nanosecond time. So the objectives of my study is most of the techniques of the intracellular delivery are facing the problems such as low throughput, specific cell delivery, small cargo delivery, non-uniform delivery with high transfection efficiency and cell viability. So in order to overcome this limitation, I fabricated a device in such a way that the efficient intracellular delivery can be provided, and also small to large biomolecules can be delivered with the help of my device. So this is the fabrication step. First, I have to tell about my device. My micro tips will be in the distance between the pattern will be 100 micrometer with an opening width of 106 micrometer and the depth of the micrometer will be 75. This is the AutoCAD model, and this is the fabrication step. The Pinana cleaned wafer will be coated with the photoresist, positive photoresist of AEZ 5214E, and I will do the UV exposure, and then BOE and KOH etching will be done for the wafer, and final silicon mold I will pour the PDMS in such a way that in the tip will be AU mixed PDMS will be there. So and I will incubate for it for 40 at 45 degree for 24 hours, and then I will peel off the microtip device. And these are the semi images for AU nanorod mixed PDMS microtips with a distance between pattern of 100 micrometer, opening width of 106 micrometer, and depth of 75 micrometer. And this is the application for my device. The device is flipped into the monolayer cell culture, and I will pour biomolecules, and then I will put the laser. When I apply the laser, what will happen is the tip containing AU nanorods. So it will heat up and it will make a cavitational bubbles, and because of these cavitational bubbles, there will be a pressure will apply on the cell membranes, and it will create pores. And because of the diffusion, the outside environmental cell will the particles will be going into the cell, so that the biomolecules can enter into the cell. And this is the experimental studies. I did microtip AU mixed my PDMS microtip flipped into the LN2N cells with and put the laser of 900 nanometer at an energy of 0.8 millijoule at the time of 5 seconds. And here I did the PA delivery, and this is a dye, but it won't be giving the fluorescence outside the cell. So once it enters into the cell, it will give red fluorescence. So this is the PA dye images, and this is the calcium images for getting the living to know about the living cells. And this is the delivery. We can see that about the orangish reddish color shows that it is live. So about 78 to 80% of cells are living. And this is the dextran delivery results. Dextran also another biomolecules with 3K molecular weight, and it also will give red fluorescence when it enters into the cells. So we can see the patterns of the small dot structures, and the particular dot that where the tips, actually the gap between the two tips is 100 micrometer, and the cell diameter is 15 micrometer. So wherever the tip in contact with the cell, the molecules will be delivered. So here also we can see that the cell viability of 78 to 80%. I am trying to optimize for more viability now. And coming to the advantages and application, we can deliver more types of molecules. Also, size-based molecular delivery is applicable, and large cargo delivery, high throughput delivery, high transfer efficiency, high cell viability can be achieved. And also different cell type like L9, RON, C, whatever cells can be delivered with the help of intracellular delivery. Coming to the summary, this work actually demonstrates the microtip device design and fabrication with the help of the biocompatible polymer PDMS. So the major highlights of the research is I am using UV lithography process with a combination of BOE and KOH etching, so that I can get the high accuracy and reproducible microtip arrays without any material loss and with less use of high cost equipment. So this study demonstrates the microtip mediated intracellular delivery for cancer treatments using optoporation technique with the help of nanosecond pulse laser source. And also in this device won't disrupt any cellular function, so that we can study or we can investigate the change in the cellular phenotype as a consequence of drug delivery. Overall, this microtip design can be a new method or efficient method for intracellular delivery for various biomolecules. We can use the negotiate the major biological barrier constructed by the cell membrane without altering the cell behavior. Thank you so much for giving a platform for the presentation. Thank you so much.
Thank you, ma'am. Thank you. And now session is for open discussion.
I have a question. Madam, can you please comment on the high cell viability? Isn't it dangerous for a living cell to have the remaining concentration of these microchips?
I didn't get you, sir.
Can you comment what do you mean by high cell viability?
Yes, sir.
Isn't it dangerous for a living cell to have this concentration of nanoparticles inside after that?
No, sir. Actually, there is no we are not adding the nanoparticle to the medium. Actually, the nanoparticles are in the tip of the device. So, where are the tips are touching the cells which are in contact with the tip only will it be delivered. All other won't be delivered because for the nanosecond player, when we are applying a laser, we need some nano rods or nanoparticle to heat up the medium. So here we are not adding the nanoparticle to the medium. The nano rods are in the tip of the device.
Okay, thank you.
So that the tip, where are the tip is in contact with the cell, that cell only will be delivered.
Thank you.
Thank you, ma'am.
Thank you. Thank you, sir.
Any more questions? No? Okay, let's move on to the next session. Thank you, ma'am. Thank you. Next, I would like to call Asta Gupta. Yes, ma'am. Are you ready?
Yeah, ma'am. Wait a minute. I'm sharing my screen.
Okay, ma'am.
Is my screen visible?
Yes, ma'am. Loading. Yes. Yes, we can see.
Yeah. Now is it full screen?
Yes, ma'am. Yes.
Yeah. Okay. A very good afternoon, everyone. My name is Astha Gupta, and I am a PhD student at IIT Mandi. The title of my presentation is Biodegradable Disulfide Cross-Linked Chitosan Stearic Acid Nanoparticles for Dual Drug Delivery for Colorectal Cancer. The presentation will involve a brief introduction, then the challenges in the field of work, followed by fabrication of the CSSA nanoparticles, then its characterization, and lastly, conclusion. Cancer, as we all know, is one of the world's most scourging diseases and is defined as a group of diseases involving the abnormal growth of the cells with the potential to invade to different parts of the body. According to the World Health Organization, cancer is the second leading cause of death globally, accounting for about 9.6 million deaths. There are many current cancer treatment techniques that are being used, which mainly involve surgery, radiotherapy, chemotherapy, and photodynamic therapy. All of these techniques, on one hand, have shown remarkable success in the effective treatment of cancer to some extent, but on the other hand, they are associated with some pitfalls like surgical complications, high radiation doses, pain, damage to the healthy cells, etc. Apart from all these things, the challenges such as non-target specificity, low drug bioavailability, multi-drug resistance, insufficient renal clearance, and image-guided therapy of the cancer cells still needs to be explored, whereby nanotechnology have paved its way and different type of the nanoparticles are being synthesized and are being used for the controlled and target-specific drug delivery via passive and active targeting. So based on all these things, our system has been designed where we have used stearic acid as the hydrophobic moiety and chitosan as the hydrophilic moiety. And then using L-cysteine, we have thylated the stearic acid and we have made thylated stearic acid. And using mercaptopropanoic acid, we made thylated chitosan. So from using this TSA and TCS, we have synthesized these CSSA nanoparticles via the disulfide cross-linking through air oxidation, leading to the formation of the disulfide links between the thiol groups of TSA and TCS. Then we have loaded the dual drugs, doxorubicin and curcumin into the system. And then we have formed the dual drug loaded disulfide cross-linked CSSA nanoparticles. Now, this system will take advantage of the enhanced GSH level in case of the cancerous cells, whereby this GSH will break down the disulfide links and the nanoparticle will degrade, leading to the release of both the drugs at the cancerous microenvironment. So for the optimization of the CSSA nanoparticles, 5 different formulations were synthesized based on the free thiol content of the TCS and TSA. Then we checked the hydrodynamic size, PDI, and free thiol content of all the 5 formulations, and our objective was to optimize that particular ratio which is having the lowest hydrodynamic size, lowest PDI, and lowest free thiol content. Based on which CSSA nanoparticles 4 they were optimized for further characterization. So first of all, the FTIR was done. At the bottom, we see the FTIR spectra of TCS, where the carbonyl stretching frequency and NH bending frequency were found, from where we confirmed the amide bond formation between the carbonyl group of mercaptopropanoic acid and the amine group of chitosan. Then the peaks at 2564 and 1240 centimeter inverse corresponds to the thiol group, thus confirming the presence of mercaptans, and hence the thiolation of chitosan was justified from this spectra. Similarly, from the spectra of this TSA, we found again the carbonyl peak and the NH bending, confirming the formation of the amide bond between the carbonyl group of stearic acid and the NH2 group of the L-cysteine. Again, the presence of peak at 2563 centimeter inverse confirms the thiolation of stearic acid. Then moving on to the FTI spectra of CSSA nanoparticles, the peak of thiol was absent, and also we found the peak for disulfide links at 717 centimeter inverse, confirming the formation of disulfide bonds between TCS and TSA. Then we did the TEM for the nanoparticles, and we found that the nanoparticles were having spherical morphology, and on plotting the histogram, we found that the nanoparticles were having an average size of around 87.55 nanometers. Then for a system to be a good carrier for drug delivery purpose, its stability is an important aspect, for which we check the stability of the nanoparticles in PBS pH 7.4 and PBS 7.4 supplemented with 0.2 molar NaCl at 0R and 48R. And then we check the hydrodynamic size of the nanoparticles by DLS, where we found that with time and with the increase in the ionic strength of the solvent, the size was almost the same, from where we speculate that the nanoparticles are stable in these media. And then we check the zeta potential of the nanoparticles in the same media at 0R and 48R, where we found that with the increase in the ionic strength of the solvent, the zeta potential decreased from minus 35 to minus 12.5 to minus 14.5 to minus 12.5 millivolt, from where we speculate that there is a compression of the electrical double layer, which led to the aggregation of the nanoparticle. But since the size was almost the same in the DLS, so from all these data, we conclude that some part of the some fraction of the nanoparticles they were showing the Brownian motion in DLS, and hence the size was almost the same. Then apart from stability, the degradation of the nanoparticles is also an important aspect, where the figure C is the SEM image of the nanoparticles after their incubation in PBS 7.4 for 48 hours. So here we can see the particles were clearly visible. Then figure C is the SEM image of the nanoparticles after their 48-hour incubation in 10 millimolar GSH, where we cannot see the nanoparticles. Thus, from where we conclude that the particles will get degrade in the redox microenvironment of the cancerous cells. Then we performed the in vitro studies. First of all, we checked the drug release of both curcumin and doxorubicin from the nanoparticles in two media, that is PBS pH 7.4 and in 10 millimolar GSH. Both the drugs were showing a good encapsulation efficiency. And it was found that for 10 millimolar GSH, the release of both the drugs was enhanced as compared to the physiological pH, confirming the fact that our system is capable of releasing the entire drug payload at the cancerous microenvironment only. Then we performed the cytotoxicity analysis through MTT assay on the HCT116 colorectal cancer cell line, where we found that the bare CSSA nanoparticles, they were showing negligible cytotoxicity, and the dual drug loaded nanoparticles, they were showing better cytotoxicity as compared to both the free drugs. from where we speculate that the dual drug-loaded nanoparticles, they were showing synergistic effect of both the drugs, doxorubicin and curcumin, and hence the cytotoxicity was enhanced as compared to the free drugs. Then we check the cellular internalization of the nanoparticles through confocal laser scanning microscopy using the two cell line HCT116 colorectal cell line and HEK293T human-derived normal cell line. So it was found that in case of the colorectal cell line, with time, the internalization of the nanoparticle was enhanced. But in case of the HEK293T human-derived normal cell line, there was very minimal internalization of the nanoparticles. From this data, we confirm that our system is specific for targeting only the colorectal cancer and is showing minimal toxicity to the normal cells. Then we performed the in vivo and ex vivo studies. First of all, we checked it in the mice model, where we saw that after 24 hours, most of the nanoparticles, they were accumulated in the colon region only. And then after 24 hours, we dissected the mice and we checked the fluorescence signal in different body organs of the mice, from where we saw that only the colorectal region was showing the signal for the presence of the nanoparticles, and rest all other organs were not showing any signal, thus confirming the fact that our system is targeting only the colon site only. Then moving on to conclusions, we have developed colon targeted dual drug delivery system. There was no usage of any external cross-linker. Both the drugs were showing quite high encapsulation efficiency into the nanoparticles, and both the drugs were released in a better way at the cancerous microenvironment, and there was enhanced cancer cell killing efficiency of the dual drug loaded nanoparticles as compared to the free drug. So this work got published recently in the Carbohydrate Polymers. So at the end, I would like to acknowledge my supervisor, Dr. Garima Agrawal, for her constant support and guidance throughout the work. I would like to thank IIT Mandi and AMRC for providing all the sophisticated instrument facilities, MHRD for funding, and collaborators and lab members for their guidance throughout the work. Thank you.
Thank you, ma'am. Thank you for the nice presentation. Now there is any question? Is there any question? Shall we move on to the next session? Thank you, Asta Gupta. You can.
Okay, ma'am.
Okay, thank you. Next, I would like to call Gina MG. Ma'am, are you there?
Yes, ma'am.
You can start your presentation.
Okay, ma'am.
She's from Central Coir Research Institute, Kalavur PO, Alapura. Our topic is antimicrobial loaded cellulose nanofibers from Coir, prospects on synthesis, characterization, and antimicrobial susceptibility.
Am I audible, ma'am? And is my screen visible?
Yes.
Okay. Good afternoon, all. Myself, Gina MD, PhD scholar, Central Coir Research Institute, under Coir, Alapura, Kerala. Today, I am here to present on my research topic, antimicrobial loaded cellulose nanofibers from Coir, prospects on synthesis, characterization, and antimicrobial susceptibility. The contents of my presentation include introduction, synthesis, characterization, results, conclusion, and references. Introduction. Cellulose is proved to be a versatile material due to its unique chemical structure, which provides a superior platform for several new biomaterials. The cellulosic materials have a great potential as nanomaterials because they are abundant, renewable, have a nanofibrillar structure, and can be made multifunctional. The coir fibers obtained from coconut husk during the extraction can be considered as one of the major raw materials for the extraction of cellulose. As it is known, the coir fibers are major composed of cellulose, hemicellulose, and lignin. Coir pig and coir fiber can be used as a suitable substrate for the production of cellulose. If The cellulose can be successfully mass-produced. It will eventually become a vital biomaterial and can be used in the creation of a wide variety of medical devices and consumer products, and thus can become a boon to the biomedical industry. Moving on to the synthesis step, the coir fibers are soaked in 2% sodium hydroxide overnight, and it is then steam exploded and then bleached. The steam exploded coir fibers are treated with 2 to 3% sodium chloride and then subjected to the second step of steam explosion for bleaching. This process is repeated until the material gets completely bleached. The bleach sample is then acid hydrolyzed with 5% oxalic acid before going through the final phase of steam explosion. The acid-treated sample is then completely rinsed with water until the pH reaches 7. Then it is air-dried and ground in a mixer grinder to obtain the nanocellulosic fibers. These are the different characterization techniques used for the analysis. First is the chemical composition analysis, then scanning electron microscopy, Fourier transform infrared spectroscopy, XRD, X-ray diffraction, drug loading studies, and antimicrobial studies. This table shows the chemical composition analysis. When treated with sodium hydroxide and subjected to steam explosion, the proportion of cellulose increases. Lignin will react with sodium chloride to form lignin chloride. The percentage increase in pure cellulose and decrease in the lignin and hemicellulose contents with each processing step is another major observation, which in turn confirms the effectiveness of the extraction process. Cellulose content varied from 39.3 plus or minus 2.3% in raw coir fiber to 93.7 plus or minus 1.2% in the final acid hydrolyzed fiber. From raw to bleached fiber, the moisture content gradually increases because of the percentage increase in cellulose content during the process. The moisture absorption rate increases with cellulose content for the reason that each unit in pure cellulose has 3 free hydroxyl groups. The scanning electron microscopic images shows the first image is of the raw coir fiber, which shows surface roughness, which is an attribute of the presence of polyphenolic chemicals, which causes the coarse granular morphology. It was found that the fibers were softened after steam explosion using sodium hydroxide, which is the second image B. And when the steam exploded fibers were bleached with sodium chloride, substantial changes in the morphology were seen, and the product became fibrillated, and the size was reduced to nanoscale range, which comes to 50 plus or minus 10 nanometer after acid hydrolysis and grinding, as seen in the image. Next is a Fourier transform infrared spectroscopy. The first graph shows that of the final form of cellulose. These are different graphs shows the FTR spectrum at different stages of processing. The first one is a raw coir fiber, and the second is a alkali treated fiber. The third is the sodium chloride treated, and fourth oxalic acid, and the final one is the coir nanocellulose. The stretching vibrations of OH and CO from either groups were responsible for the prominent spectral bands at 3348 and 1042 centimeter inverse. The antisymmetric and symmetric vibrations of CH2 groups resulted in a peak in the region of 2902 centimeter. The vibration at 2850 centimeter inverse caused by CH stretching in lignin was absent in the treated sample, confirming the removal of that fraction. The sample's peak at 1642 centimeter inverse represents absorbed water, and the extracted cellulose sample spectral intensity was linked to elimination of hemicellulose fractions during processing. And due to the elimination of these aromatic compounds, the shoulder peak at 1545 centimeter was also removed in the extracted coir nanocellulose. In the sample, the band at this 1432 centimeter inverse indicates CH deformation as well as deformation of this bonding carbohydrates in presence of C double bond O as it is moved down from its normal location. Because of the treated material was first neutralized with NaOH, the acid extracted product did not show bound sulfate groups at 1210 centimeter inverse, but it did show absorption peaks at 1110, 1042, and 896 centimeter inverse, indicating enhanced asymmetric stretching of the ring and vibration of CO in cellulose. In the majority of the spectral bands, extracted cellulose, nanocellulose, was identical to the reference cellulose sample, indicating strong correlation. Next is a XRD, X-ray diffraction studies. There are crystalline and amorphous region in the fiber. The raw coir fiber consists of both crystalline as well as amorphous region. The amount of crystalline cellulose present in a cellulosic fiber or the degree of crystallinity cannot be precisely described, and the alkali treatment removes cementing components such as lignin, hemicellulose, and pectin, causing the percentage of crystallinity of the fiber to increase. The XRD analysis of coir microcellulose exhibited a characteristic peak in the 2 theta scale range around 22 to 23 degrees, showing crystalline structure of the cellulose. And this is the first one is that of the nanocellulose, and red and blue, this graph shows that of a drug-loaded cellulose, nanocellulose. Two drugs were used, ciprofloxacin and gentamicin, to impart antibacterial activity, and after drug loading also there was no change in the crystalline structure of nanocellulose. These are the drug loading studies what we have done. Drug loading and drug entrapment studies were performed for the two different drugs, ciprofloxacin and gentamicin. The percentage drug loading for cipro and gentamicin was found to be 16.82 plus or minus 1.27 percentage and 19.27 plus or minus 0.96 percentage respectively. And the drug entrapment efficiency was calculated to be 33.64 plus or minus 2.54 for ciprofloxacin and 38.54 plus or minus 2.19 percentage for gentamicin. These are the results of the antimicrobial studies, where we have taken two microorganisms, Staphylococcus aureus and Pseudomonas aeruginosa, and the two drugs, drug-loaded cellulose nanosquare nanocellulose. And the table shows the antimicrobial studies, and the image shows the disk diffusion study what we have done. The results of the agar disk diffusion method for estimating the antimicrobial activities of ciprofloxacin and gentamicin loaded samples revealed considerable antibacterial activity against both gram-positive and gram-negative bacteria. On both the studied bacteria, Staphylococcus aureus and Pseudomonas aeruginosa, ciprofloxacin loaded microcellulose demonstrate considerable antibacterial activity. Staphylococcus had a clear zone of inhibition measuring 2.3 cm against the positive control of 2.73 cm, and Pseudomonas aeruginosa had a clear zone of inhibition measuring 2 cm against the positive control of 2.13 cm. Similarly, gentamicin-loaded microcellulose also exhibited antimicrobial activity against both the tested strains, Staphylococcus aureus and Pseudomonas aeruginosa, with a clear zone of inhibitions measuring 1.76 cm against the positive control 2.06 cm for Staphylococcus aureus and 1.8 cm against the positive control 1.9 cm for Pseudomonas aeruginosa. To conclude, cellulose could successfully be extracted from coir fiber and converted to nanocellulose. The coir nanocellulose was characterized using SEM, FTIR, and XRD, which confirms the size, chemical composition, and crystallinity of cellulose. Two major antibiotics used to treat the serious bacterial infections, ciprofloxacin and gentamicin, were utilized for imparting antibacterial properties to coir nanocellulose. Two different microbial strains, Staphylococcus aureus and Pseudomonas aeruginosa, which are among the leading causes of skin and soft tissue infections and surgical wound infections, were employed for antimicrobial susceptibility studies, and drug-loaded nanocellulose was found to be effective against both. The unique properties of cellulose, such as its biodegradability, low density, availability, low pricing, and easily adjustable surface properties, has to be utilized to find its potential opportunity to develop new materials for diversified biomedical applications. These are some of the references of the study. Thank you.
Thank you, ma'am. Thank you for the wonderful presentation. Now for open discussion. Is there any question? Is there any question, or we can move on to the next session? Next, we have Vidya. Ma'am, are you there?
Yes, ma'am.
Can you present?
Yeah, ma'am.
Yes, okay. You can share your screen. Ma'am, is there any problem?
No, ma'am. Right.
Okay.
Visible, ma'am.
Yes, ma'am, you are visible.
Okay. Good afternoon, everyone. Myself, E. Vidya, research scholar. My research advisor, Dr. S. Vijay Kumar sir, Assistant Professor, Department of Botany, AVVM Sri Pushpam College, Pundi. Now I share about copper nanoparticles derived from Asimum americanum, ecosynthesis, characterization, and biological applications. Introduction. Copper nanoparticles play a considerable interest due to their essential constitution and importance in the enormous area of physical, chemical, biological, and material science. Green route biogenesis of nanoparticles as cost-effective, eco-friendly, and coping agent. Recently, many reports stated that biogenesis of copper nanoparticles grown excellent manner. Traditionally, the leaf extract has been used to treat diabetics, constipation, diarrhea, piles, dysentery, and skin diseases. As a result, the reduction of copper ions by Asimum americanum plant extract is the fundamental concept of our technique for the production of copper nanoparticles. Therefore, in the present goal of the studies has successfully synthesized copper nanoparticles using Asimum americanum leaf extract, and it's exempt for antimicrobial, photocatalytic, and anti-cancer efficacies. Next, objectives. To synthesis of copper nanoparticles using aqueous leaf extract of Asimum americanum, to characterization of biosynthesized nanoparticles using UV visible spectroscopy, FTR, XRD, FESM with ADAX respectively, to evaluate the antimicrobial activity of green synthesized copper nanoparticles against skin disease causing pathogenic microorganisms such as Bacillus cereus, Clostridium perfringens, Klebsiella pneumonia, Salmonella paratype, Candida albicans, and Aspergillus niger. To analyze the anti-cancer activity of synthesized copper nanoparticles against human skin cancer cell line. To analyze the photodegradation activity of synthesized copper nanoparticles and materials and methods. The overall methodology of Asimum americanum leaf extract was added to the 0.5 molar of copper sulfate pentahydrate. Then I was taken by 50 ml of distilled water after the 10 ml of Asimum americanum. Next, the stirrer 80 degrees Celsius for 2 hours after centrifugated for 30 minutes. Then dried precipitate was heated for 2 hours at 800 degrees Celsius in a muffled furnace. Next, green synthesized copper nanoparticles to analyze the characterizations such as XRD, UV visible, FTR, and FESM with ADAX. Then, biomedical application of antimicrobial activity, anti-cancer activity, and photodegradation. Next, result and discussion. Figure 1 shows the UV visible spectrum of copper nanoparticles. The prominent absorption peak at 350 nanometer corresponded to copper nanoparticles. Next, figure 2 shows the XRD of biogenesis of copper nanoparticles as the intensity of 20.96 degree in attributes to the purity crystalline from the copper nanoparticles. Figure 3 shows the FTR spectrum of biogenesis copper nanoparticles, which were recorded 500 to 4000 centimeter per minus 1 were numbers. The strong bond of 3769 centimeter per minus 1 OH group. Then 2304 centimeter of 2 OH stretching vibration. The bond of alkaline at 785 centimeter. The figure 4 shows the FESM microscope of copper nanoparticles and ADAX analysis of copper nanoparticles and frequency distribution of histogram. FESM is spherical shape of copper nanoparticles was seen. ADAX in the purified form the copper nanoparticles. Histogram size distribution at 25 nanometer observed. Next. The figure 5 shows the cytotoxicity effect of copper nanoparticles using MTTSA. The substance has the concentration of cytotoxicity effect on A431 skin cancer cell line. Next, figure 6 shown the anti-proliferative effect on human skin cancer cell line. Human skin cancer cell line for copper nanoparticles has range of 1 to 1000 μg per ml. Next, antimicrobial. This figure shows the 7 antimicrobial analysis of biogenesis copper nanoparticles against microbial pathogenesis. Next. Photodegradation of MB with biogenesis of copper nanoparticles. MB dyes was degraded using biogenesis copper nanoparticles. 90.6% was degraded in 15 minutes. Summary and conclusion. In the present study concluded that the copper nanoparticles are successfully synthesized using Asimum americanum leaf extract. Copper nanoparticles produced by green method were confirmed by various optical, structural and morphological studies. The dimension of the produced copper nanoparticles is 25 nanometer. Our results that green synthesized copper nanoparticles have excellent antimicrobial activity against skin disease causing microorganisms. Various approaches were used to characterize the conformation of nanoparticles. Copper nanoparticles have excellent antimicrobial, anti-cancer, A431 skin cancer cell line, and photodegradation properties. Therefore, synthesized copper nanoparticles suggested that broad spectrum of antimicrobial agent for many infection diseases. Thank you.
Thank you, ma'am. Thank you for the nice presentation.
Thank you, ma'am.
And now the session is over. We can move on to nanoparticles. And I would like to call
Madam,
Yes, sir.
can I present now, madam? My participation code is SIL14. Due to some technical difficulties and poor connectivity, my connection is lost in between the presentation.
Is your connectivity okay now?
Yeah, madam, it is quite okay. Because due to heavy rainfall, madam, the connection is fluctuating actually in Odisha.
Okay, we can try.
Okay. Can I present, madam?
Yes, you present.
Okay. Thank you. Is my presentation visible, madam?
Yes, sir. Yes, sir. You can start.
Yeah. Again, thank you for providing me another opportunity to present my research work. Thank you. My good name is Amit Kumar Gantayat, and my topic is analysis of graphene expert and reinforced axially functionally graded non-uniform polymer matrix nanocomposite beam. And as the title indicates that the graphene is a reinforcement in the beam structure, we are going to dynamic structural analysis, and we studied the many parametric effects and how it is effects in the X pattern distribution of the graphene along the axial distribution in the beam. Before going to that, this is the presentation outline, and introducing the axial functionally graded nanocomposite beam. The conventional pure materials are not able to used in an optimized way due to there is some technical service condition, and otherwise we are providing more FOS. We can go for the better material, and this is the functionally graded material is a one step forward to the advanced material, and in that functionally graded material we can get a desired property at different point of the material as per our requirement, and that function we can provide, and as per our functional requirement we can provide the reinforcement at each point as a design. And during design we are going through these references. These are helpful for our design procedures, and the advantage we can go for the polymer nanocomposite is that conventional composite, because they are comparing to conventional composite, these are the lighter and more reliable, and the barrier properties are improved as compared to the neat polymer matrix, and the mechanical thermal properties are more superior than the conventional composites. And in this topic, the gap which is arised from the research that we are covering, that there is no analysis in that non-uniform structure, and with the X pattern graphene reinforcement is done yet. And for different boundary condition also, we have analyzed our result. And in this research work, we have taken graphene because some advantages of graphene over the carbon nanotubes, that is, it is more crack resistance or the crack propagation resistance due to its two-dimensional structures, and also the bonding as compared to carbon nanotube. Graphene as a seed-like structure, it provides better metrics to reinforcement bonding. Our objective in this work is that to model an axially functionally graded beam with epoxy as a polymer and graphene as a reinforcement. Graphene is a nanomaterial. Nanomaterial reinforcement is there, and the concentration of reinforcement, that is graphene nanoparticle, varies along the axial direction to so as to grade the beam. Ma'am, am I audible now? Hello?
Yes, sir, you are audible.
Okay. Then here we have our modification is that geometry, that the beam geometry is non-uniform, that is it varying from one end to another end, and also the reinforcement pattern, the reinforcement concentration, that is graphene reinforcement concentration, is also varying from one end to another end, as we are considering as a beam structure. And how the reinforcement pattern is varying is like the X function, and X pattern function variable, and we are using the MATLAB software to analyze and simulation the whole model. And first we validated with our result with the uniform beam, and next the parametric analysis has been carried out for the non-uniform structures for various end condition, also for various slenderness ratio with the non-uniformity exponents. We will see here that how the workflow diagram is here. First we model our geometry, that is non-uniform geometry has been modeled, and next we model the material properties, then we go for the simulation, and result has been discussed in the next slide. First, as we go for the geometric modeling, as discussed, that we go for the non-uniform. The non-uniformity means here the cross section is different, and here the cross section is different, and the geometry is continuously varying along the axial direction as per this function, exponential function, and this exponent governs the geometry. That is, the non-uniformity governed by this exponent, and at each point the x indicates that the coordinate that at along the length x, at any point x we can get that the geometry, and the cross section area as well as the moment of inertia at each cross section or at each point of the material x we can get that moment of inertia. Then we go for the material modeling. For material model, we use the Helpin TSI micromechanics model, which is best suitable for the short fiber as well as the nanofiber composites, because here it is considers the nano geometry. Means as we are consider the graphene, its graphene geometry is considered in this model, in this micromechanics model, and it is a semi-empirical model, and which holds good, so that we consider the Helpin TSI model. And here LGPL, HGPL, and WGPL are the length, height, and width of the GPL, means graphene platelets. As it is considered the graphene particles, it is giving more better result than other micromechanics model. And for the density and the Poisson's ratio, we consider as the conventional rule of mixture model to for the material. At each point x we can get the Poisson's ratio as well as the density. And as we discussed that our graphene reinforcement is in a x pattern, means this function is carries, and at each point x our volume fraction of graphene platelets are varying, and this pattern shows like this, and the gradation is like this gradation. And then we go for the input material properties, and the material properties we have considered from literature, that is the epoxy as a polymer matrix, and the GPL is the nano filler or the nano reinforcement. and these are the properties considered from literature. And when we go for the simulation part, first the beam is divided into number of elements, and each element's mass and stiffness matrix is obtained from the kinetic energy as well as the potential energy equation. From kinetic energy equation we get the mass matrix, and the potential energy we can get the stiffness matrix as our conventional way. And the problem is formulated as an eigenvalue problem. From that we can get the natural frequency as usual. But here we did one thing, that the natural frequency is non-dimensionalized to clearly visualize, means the to contrast more the result in frequency. And if we discuss the result here, that here the parameters is, here is the geometric exponent that is varying, means here the geometric exponents alpha is 0, means it is a uniform beam, no cross sectional varying from one end to another end. As 0.2 alpha means some extent it is varying. As the exponent increases, means non-uniformity of the beam increases. Here we plotted the here in the axis we have fundamental frequency, and in this figure we discriminate that for different boundary conditions, that CC means clamped conditions, clamped simply supported condition, clamped free condition, and simply supported condition. These are the condition. Clamped condition means both end are fixed. As both end are fixed, at this condition we get the more fundamental frequency as compared to the clamped free condition, because from that we can say that as our degree of freedom for the end condition is increases, the fundamental frequency is decreases. As the degree of freedom of the end constraint is less, then our frequency is more. And this is for the L by H ratio is equal to 100. If we go for the L by H ratio is nothing but the slenderness ratio, length to height ratio. As we increase L by H ratio, for this L by H ratio also we see that for the same effect, that for clamped condition we get more fundamental frequency compared to the clamped free condition. And for as we getting the higher slenderness ratio also, the end condition does not affect that. The clamped condition shows the for more fundamental frequency compared to the clamped free condition. And in next slide we can clearly contrast that with effect. Here we see the effect of slenderness ratio, that is L by H ratio. Here we mark one thing, that as the L by H ratio, here the black line is so that L by H ratio for 100. As we see that L by H ratio is increasing 100, 120, 150, then fundamental frequency is decreases. And along the geometric exponent, as the geometric exponent increases, means non-uniformity increases.
Sir, excuse me.
Yes.
Can you please conclude it in 2 minutes?
Yeah, definitely. 1 minute I can conclude.
Okay.
As the non-uniformity is also increases, our the fundamental frequencies decreases. This pattern is follows for all the end conditions also. And here in the slide we can see that for higher modes, these were fundamental modes, but here we can see that for mode 1, mode 2, mode 3, mode 4, as as the mode is increasing, the fundamental frequency increases, as well as the geometric exponent is increases, the frequency decreases. And here the conclusion, that as we get the more constraint effect, that is degree of freedom is less, we can get the more frequency, as well as the degree of restriction is increases, we can get the more fundamental frequency. As the degree of restriction decreases, we can get the less. And also this is valid for the slenderness ratio. As the slenderness ratio increases, the frequency decreases. These are the references. Thank you.
Thank you, sir, for the wonderful presentation. Now it's open for the questions. Is there any questions? we can move on to the next topic.
Yeah, madam. Thank you. Can I stop my presentation, madam?
Yes, sir. Yes. Okay.
Yeah, madam. Thank you. Thank you for giving me another opportunity, and really, I thank you again.
Thank you, sir. Thank you.
Thank you. Okay.
And next, our topic is nanoparticles. I would like to call Shirin Masroor for to have the chair. Ma'am, can you hear me?
Hello. Yes, please.
Yes,
Hello.
ma'am.
Excuse me,
Yes, sir.
Hello.
I'm Dr. Lakhajuri Bhattakur.
Hello.
In that sense, yes, I'm Dr. Lakhajuri Bhattakur. In the agenda, in the program, I was given as the chairperson for this session. Is it this session
Hello.
or something else?
Hello.
He was saying something. This Bhattakur was saying something that he was to chair something.
Hello.
Ma'am, you can chair the session.
Hello.
Hello, yes, ma'am. Ma'am, you are audible. You can chair the session. You can start the session.
Okay. Uh, hello. Hello.
Yes, ma'am.
Okay. Okay. Now, the present session belongs to topic nanoparticle, and myself, Dr. Shiri Masroor. I'm from Department of Chemistry and College, Patliputra University, Patna, Bihar. Now, it's time for a short invited lecture, which has to be presented by Ashish Kumar. Hello.
Good evening, ma'am.
So, Ashish Kumar is present?
Yes, ma'am. I'm there. I'm audible to you?
Yeah, audible. But I want to know your designation. Either you are faculty or a research scholar.
Ma'am, I am a PhD research scholar at Chitkara University, Punjab.
Okay, you are going to present your work here.
Yes.
Ashish Kumar, Nanoparticle Research Lab, CURIN, Chitkara University, Punjab, India.
Yes, ma'am.
Okay, okay.
May I start
So,
the session, ma'am? Just wait a second. I'm going to share my screen.
yes, you can share your slide.
My screen is visible to all, ma'am?
Yes, it is visible to me.
Okay. Greetings of the day to each and everyone present over there. Today I'm going to present one of the supporting study and sub-objective of my PhD work, that is the effect of varying calcination temperature on the structural and optical properties of tin oxide nanoparticles. So in this presentation, I'm going to start with the introduction to the nanomaterials, selection of suitable nanomaterials, material identification, experimental work, characterization, and finally, I will conclude my work. So as we all know that nano is something which lies in the range of 1 to 100 nanometer. If we compare it with a meter, it is 1 billion, it is a billionth part of a meter. So at nanoscale, we get extraordinary magnetic, optical, and various electrical properties. So the main reason for differing properties of nanomaterial from their bulk materials are their increased quantum confinement effect and surface to volume ratio. When we move from bulk to nanoparticles, so we see increase in surface area, chemical reactivity, electron band gap, and number of applications. So recently I have just discussed about the quantum confinement effect and large surface to volume ratio. where we under quantum confinement effect, when we go from bulk to nano, we restricted the movement of the particles, and the reactivity increases when we go from bulk to nano with the surrounding material. That's why we call it as a large surface to volume ratio. Now, in my PhD, I am studying the electronic properties of tin oxide nanoparticles, but there are certain parameters which are used to fine tune the properties of the nanomaterial. One from them is the calcination temperature. So I am studying the effect of calcination temperature on the properties of tin oxide. So why tin oxide? Because it is oxygen deficient n-type semiconductor and exhibit band gap of around 3.6 electron volt. Moreover, it is having rutile structure. So rutile are widely studied due to the ease of preparation and several industrial applications. Furthermore, at room temperature, rutile is thermodynamically more stable. As you can see in figure 2, we are having a unit cell illustrating the rutile crystal structure of tin oxide. So why we selected this material? Basically there are two series of compounds of tin. One is tin second or stannous compounds, and one is tin 4 or stannic compounds, which are white in color. So both of which are of stable oxidation state, and the melting point of tin oxide is around 1630 degrees Celsius. So as you can see in figure 3, the unit cell depicting apical and equatorial positions of oxygen anions from tin. So the very first step is to synthesize pristine tin oxide nanoparticles. So conventional soil gel route was used for the synthesis of tin oxide nanocrystal. 3 parts of tin tetrachloride pentahydrate of same quantity were weighed using highly sensitive microbalance. In 3 separate beakers, the stoichiometric quantities of tin tetrachloride pentahydrate were dissolved in 100 ml of ethanol. The solution was magnetically stirred till it became colorless and transparent. The obtained solution was heated at around 100 to 120 degrees Celsius till HCl and water were completely evaporated. So the 3 beakers, dark brown color gels were obtained. The obtained gel was dried in hot air oven at 100 degrees Celsius for 1 hour, and finally the dried samples were heated with the help of programmable muffle furnace at 400 degrees Celsius, 600 degrees Celsius, and 800 degrees Celsius. And finally, we are having 3 samples at 400 degree, calcined at 400, 600 at 8 and 800 degrees Celsius. Now moving on to the characterization part. So the very first step is a structural study, where we will do the X-ray diffraction to know whether the sample prepared are crystalline or not. So XRD spectra of tin oxide nanoparticles calcined at different temperature is shown in the figure 5. So the x-axis where the angle of diffraction, that is 2 theta, is taken from 20 degree to 80 degree, and on y-axis intensity at different calcination temperature is shown. The peaks obtained matched very well with the JCD PDS, so this confirms that the synthesized tin oxide nanoparticles have rutile type tetragonal structure. The sharp peaks of observed spectra are 110, 101, 200, 111, 210, 211, 220, 002, 310, 112, 301, 202, and 321 planes. So the XRD spectra exhibited the intensity and sharpness of the peak increased as the calcination temperature elevated from 400 to 600 and 600 to 800. So we calculate the crystallite size from the scalar formula, and from the crystallite size we calculate the dislocation density and we calculate the microstrain. So it is observed that the sharpness and the crystallite size increase as we move from the 400 to 600 and 600 to 800 degrees Celsius. So the average crystallite size for 400 as shown is 7.8, and for 600 degrees Celsius, it is 22.7 nanometer, and for 800 degrees Celsius, it is 24.84 nanometer. As you can show, the dislocation density and microstrain are inverse of the crystallite size. So we observed from the structural studies that as we increase the calcination temperature, the crystallite size increased from 400 to 600, that is 7.8 nanometer to 22.71 nanometer, and at 800 we are having 24.84 nanometer. Now for microstructural study, we did the FESM analysis. So FESM analysis shows that the FESM images of tin oxide nanoparticles calcined at three various temperatures are shown in the figure A, B, and C. So all the three samples show the presence of spherical and pseudo-spherical shaped particles with somewhat agglomeration in nanoscale sizes. Now, the next very important characterization is the optical analysis. So the optical properties of the nanostructures were studied in the UV and visible region with a wavelength ranging from 200 to 800 nanometer at room temperature. The band gap energy of the samples was calculated using the top plot. So the figure shows variation of absorbance of the three samples calcined at 400, 600, and 800 degrees Celsius. So it is observed that the samples calcined at 400 degrees Celsius show larger absorption in the visible region and nearly UV region as compared to the samples calcined at the 600 and 800 degrees Celsius, which reveals that the number of defects are larger in samples calcined at the 400 degrees Celsius as compared to the higher temperatures, that is 600 and 800 degrees Celsius. Moreover, a sharp absorption edge was observed at 800 degrees Celsius, which shows high crystallinity with less defects. So moving ahead, it is really very important to calculate the band gap energy. So as I have previously described that we calculate the band gap energy using the top plot. So the optical band gap energy was calculated. So the calculated band gap energy is found out to be, it is 4.139 electron volt at 800 degrees Celsius, 3.147 at 600 degrees Celsius, and 400 degrees at 400 degrees Celsius we are having 3.03 electron volt. So there is a trend with the decline in the calcination temperature, the band gap energy is also declined. So finally, I'm going to conclude the polycrystalline tin oxide nanocrystals were synthesized via sol gel autocombustion. XRD studies reveal that all the composition exhibit rutile type tetragonal symmetry. The crystallite size increased from 7.8 nanometer to 24.84 nanometer as the calcination temperature elevated from 400 to 800. And finally, the band gap energy decreases from 4.1 to 3.03 as the calcination temperature falls from 800 to 400. So that's all for the presentation. So finally, I would like to thank my guide, Dr. Mansi Chitkara and Dr. Gulshan Dhillon. I would like to thank Chitkara University for all the support and funding for characterization. Thank you so much. Your queries and suggestions are most welcome for me. Thank you.
Hello.
Yes, ma'am.
Okay. So you have concluded your PPTs in a well-defined manner. Now the session is open for questions. Any questions from the listeners? Hello.
Yes, ma'am.
I think there is no question from the audience side. You can stop presenting your work.
Okay, ma'am.
The next speaker is Benzer, Mr.
Yes, ma'am.
Benzer.
Good evening, ma'am. Shall I present my screen, ma'am? Am I audible, ma'am?
So may I know your designation? Either you are faculty or
I'm a PhD scholar at St. Joseph College, Trichy. I work in
okay.
CNSCT.
Okay, so today's talk is on the effect of manganese dopant on the structural, optical, and photocatalytic properties of zinc oxide nanoparticle. So
Yes,
you can
ma'am.
start.
Thank you. So, ma'am, is my screen visible?
Yes, it is visible to me.
Sure. Esteemed professors and peer group, good evening to everyone. I'm Ebenezer Taninayagam, and I'm going to talk about the research that we are doing currently. Is the effect of manganese dopant on structural, optical, and photocatalytic properties of zinc oxide nanoparticles. The people who work on this work is Gopi Arar, Dr. H. Joy Prabhu, who is my supervisor, Dr. I. Johnson, and Ms. C. Subhashini. And we are from Center for Nanoscience and Applied Thermodynamics, Department of Physics, St. Joseph College, Trichy. The objective of this study is to synthesize manganese-doped zinc oxide nanoparticles via chemical precipitation process and to study its optical, electrical, and photocatalytic activities of the and comparing it with doped as well as undoped manganese-doped and manganese undoped ZNO particle. And this results from this study has shown the enhancement of photocatalytic performance in degrading phenol and benzoic acid, which is the basic components of the azure dyes. The chemical used in this process is magnesium chloride dihydride, zinc acetate dihydride, sodium hydroxide. The methodology is 0.23 grams of manganese chloride is added with 5 grams of zinc acetate dihydride, and the solution was vigorously stirred. Adding NaOH drop by drop until the pH 8 is obtained. The precipitate is washed it multiple times with ethanol and distilled water. The solution is then dried in a vacuum oven at 100 degrees Celsius for an hour and annealed at 600 degrees Celsius for 2 hours. Then we obtain the manganese doped ZNO nanoparticles. The obtained manganese doped ZNO nanoparticles and the pure ZNO nanoparticles are then characterized and compared with each other. This is the X-ray diffraction analysis of both ZNO and Mn doped ZNO particles. So from the image or the graph, we can say that both exhibit a hexagonal Buzzite type structure, and they are on excellent accord with conventional JCPDS conventional research. References JCPDS card number 891397 data. In manganese doped sample, the intensity of the peak decreases and shifted towards the lower angle. This indicates that the substitution of Mn2 plus into the ZNO host lattice ions. The observed change in the lattice parameter is consistent with the smaller radius of the Mn2 plus ion, which is 0.71 Armstrong, relative to the Zn2 plus ion radius, which is 0.74 Armstrong. And hence we can see in the cell volume that in pure ZNO nanoparticle, the cell volume is 47.78 Armstrong cube, whereas in manganese doped ZNO, it is 46.79 Armstrong cube. The manganese doped zinc oxide has a minimum cell volume compared with the pure zinc oxide. This proves that the zinc ions are actually substituted by manganese ions. This is the transmission micrograph, and from this images, from this micrograph, we can see that both have ellipsoidal pseudospherical morphology and a homogeneous particle dispersion. They both have average particle sizes. For pure ZNO, it is 25 to 30 nanometer, while the manganese doped ZNO, it is 22 to 26 nanometer. So both these data correspond closely with the average crystalline size obtained from the XRD data. From the EDAX analysis, we can see that this sample primarily consists of zinc, oxygen, and manganese components. The predicted stoichiometry ratio is actually coincide well with the ratio that we have obtained. The zinc, oxygen, and manganese atomic ratio here we obtained is 1.78:2, 3.08:0.8. From the FTIR analysis, we can see that the zinc oxide absorption peaks migrated downward for manganese doped samples, indicating that manganese was replaced by zinc at the lattice site of ZNO. In the wave number, we can see at 3441.87 centimeter inverse. It's the OH hydroxyl functional group. 2957.48 centimeter inverse. It's the acetate functional group. 1451.67 is the carboxyl functional group, and 521.33 and 690.21 is the zinc oxide stretching group. And the application that we are focusing on, there are 3 applications we have done in this study. First one is the photoluminescence spectra analysis, and the PL spectroscopy is a valuable tool for investigating characterization of materials and dynamic processes occurring in the material, particularly the optical properties. Here we take the PL for the Mn doped pure and Mn doped samples, measuring from 300 to 600 nanometer with a 325 nanometer helium cadmium laser. From the data, we can see that in the UV emission range, we get the maxima at 360 nanometer and 391 nanometer. Violet and blue-green emission at 412 nanometer and 492 nanometer. Finally, green emission at 521 nanometer. The emission peaks at 412 nanometer, 492 nanometer, and 521 nanometer are attributed to a radioactive transition between donors of zinc interstitial atoms to the oxygen vacancy. The fact that this intensity of the emission peak increases in manganese doped sample indicates that optical property of ZNO has been greatly enhanced. The electrical measurements have been taken using the LCR probe method, and from we can see that the behavior of the semiconducting nature is that the resistance value falls progressively with increasing in temperature. And from the graph, we can say that as resistance increases, temperature increases, the resistance falls quite steeply. The resistance value is determined to be 33.2 kilo ohm for pure zinc oxide nanoparticles and 16.7 kilo ohm for manganese doped zinc oxide nanoparticles at 500 degrees Celsius. The large improvement in the electrical characteristics for manganese doped sample is mostly due to the increase in mobility, addition to the decreasing band gap energy and particle size. These are essential to improve the electrical property. Finally, the photocatalytic study. The photocatalytic activities of the pure and manganese doped samples were investigated under UV light radiation based on its ability to destroy various colors in azodides such as phenol and benzoic acid. And the color diminishes linearly with the color concentration in both cases. And the photocatalytic activity of Mn ZNO doped catalysts have been increased by 2-fold after 100 minutes of UV radiation. We can see from the table here. For phenol, we get that for pure ZNO, the degradation percentage is 33.1, and for manganese doped ZNO, it is 71.5. For benzoic acid, it's 38.2, and for manganese dope, it is 76.5. The photocatalytic activities of manganese doped ZNO is significantly improved due to the decreased band gap energy and grain sizes. In conclusion, we have seen that the vast array of photocatalytic application has emerged in fields such as clean water, air, or hydrogen protection, etc. Due to its capacity to oxidize organic and inorganic substances, this technique has been proposed for mediating environmental degradation. Pure and manganese doped ZNO nanoparticles have been synthesized using chemical precipitation approach. Powder XRD measurement indicates that both pure and Mn doped ZNO nanoparticles have hexagonal work-site structure, and the results are in excellent agreement with the conventional JCBDS data. The TEM micrograph reveals that pseudospherical and ellipsoidal morphology and having an average diameter of roughly 21 to 28 nanometer. The manganese doping is greatly enhanced by the optical characteristics of ZNO confirmed by the photoluminescence spectrum study, and the results of electrical experiments suggest that manganese doped samples boost the mobility of the carrier charges, and a high performance photocatalytic system has also been seen. By doping ZNO with manganese, photocatalytic performance on degrading phenol and benzoic acid was dramatically increased. This catalyst would be promising for practical usages in pollutant breakdown. And these are the references, ma'am. So thank you for accommodating me and guiding me in this process. Thank you very much, ma'am. If you have any questions, you can proceed.
Thank you, Mr. Venza.
Thank you, ma'am.
May your talk has motivated students from different fields to work over the optical or photocatalytic uh, properties of any metal, as you are working in zinc oxide
Yes,
nanoparticles.
ma'am. Yeah,
Now
we have
the session is
also
open for questions. Yes, what?
done with gold nanoparticles and copper
Okay.
nanoparticles. Yeah.
Okay. So, any question from the audience? I think there is no question.
Okay.
Okay.
Thank you very much, ma'am. Thank you.
Okay, that's wish. The next speaker in the queue is Ankita Dhiman.
Yes, ma'am.
Hello. Ankita is present?
Yeah, ma'am, I'm here.
Okay. So you belongs to School of Basic Science and Advanced Material Research Center, Indian Institute of Technology, uh, Mandi, HP, Himachal Pradesh.
Yes,
Am
ma'am.
I right?
Yes, ma'am.
Okay. So you are going to deliver on the topic development of pH and redox responsive sodium alginate nanoparticle for controlled agrochemical delivery.
Yes, ma'am. Shall I present?
Yeah.
Ma'am, my screen is visible. Hello.
Yes, it's visible now.
Okay, ma'am. Thank you.
Okay.
Good afternoon, one and all. Myself, Ankita Dhiman, and I'm a PhD student at SBS IIT Mandi, Himachal Pradesh. Today, I'm here to present my research work entitled Development of pH and Redox Responsive Sodium Alginate Nanoparticles for Controlled Agrochemicals Delivery. And the content of my presentation is divided into 5 parts. First one is introduction, then fabrication of OALGDP nanoparticles, then their characterizations, and then I will show you the agrochemical release studies followed by conclusions. First of all, introduction. So here I will explain why we are interested in agricultural sector. And as we all know that world population is growing very fastly and it will reach 9 billion by 2048, which is a huge number. So, ma'am, my screen is full screen or not?
Yes, ma'am. You can continue.
Hello.
Yes.
My slides are moving, right?
Yeah, I think it's your third slide.
Yeah, ma'am. Okay. Thank you. Okay. So as we all know that population is increasing very fastly and it will reach 9 billion by 2048, which is a huge number. And so the population is very high in 2048, so the requirement of food will also increase. And this graph is showing the global progress in food consumption, and by 2030 every person need more and more food resources per day for their survival. And as the population will reach 9 billion, so to meet the demand of food for that much population, we need to enhance the agricultural activity. But there are several factors in the agricultural sector that needs immediate attention, like the agricultural yield is affected by the diseases, the attack of insects and pests, and even the unwanted weeds which is growing besides the crop can also adversely affect the quality of food. So to get rid of all these factors, people start using insecticides, fungicides, herbicides, and even they provide nutrients to the plant, either in the form of macronutrients or in micronutrients, so that they can enhance the quality as well as the productivity of the agricultural products. But still, there are several challenges in the agricultural sector that needs to be addressed. And these challenges are excessive usage of fertilizers, insecticides, and low moisture retention ability of the soil, which leads to consequences like eutrophication, leaching, infertile soil, salt burn, and nutrients runoff. And researchers are continuously working in this area to get rid of these challenges and the consequences caused by them. So, by taking the motivation from the work which has already been done in this area, we constructed a polymer based nanoparticle to minimize these challenges. And this is the journal schematic representation to fabricate OALG-DP nanoparticles, where first step is the oxidation of sodium alginate, and this oxidized moiety was further treated with a cross-linker containing NH2 groups, which further condensed to form OALG-DP nanoparticles. We utilized these nanoparticles to load the diuron, which is a model herbicide, and release studies was checked in different millimolar concentration of GSH and different pH variations. So as we prepared our particle via condensation reaction between these two.
Are you changing your slide?
No, ma'am. Now I will change.
Okay. Actually, it's constant. That's why I asked you. Okay.
Yeah. Now it is changed, no, right? After that, the OLG-DP nanoparticles were characterized via DLS. And we found that the hydrodynamic diameter is 286 nanometer and the zeta potential was minus 36 millivolt, which exhibited the quite good stability of particle, as well as it tells that the particle carries the negative charge on its surface. After that, the morphology of the prepared nanoformulation was checked with scanning electron microscopy, where the mean size was coming out to be 161 plus minus 21 nanometer. As my particles are pH and redox responsive, so I checked the pH and redox responsiveness by adding millimolar concentration of HCl and millimolar concentration of GSH. And I observed that after 24 hours of treatment, a clear solution was there, which was due to the degradation of acyl hydrogen bonds in the presence of HCl and degradation of disulfide bonds in the presence of GSH. Then the reconstruction of particles were there when we add basic media and oxidizing agent into it, which further confirmed that the particle is pH as well as redox responsive. The recentration of particle was further checked by scanning microscopy images, which showed that the particle regained their shape even after pH and redox responsiveness check. Then FTIR was taken for starting material, intermediates, cross-linker, and the nanoparticles, which are constructed by a condensation reaction between oxidized moiety and DP. And FTA spectra also exhibited that the
Excuse me, ma'am.
particles are formed. Yes, ma'am.
Are you currently in the third slide itself, the introduction part?
No,
It's not.
no,
It's
I'm
not
in
moving.
11.
Oh, it's
Sorry,
not.
actually, I asked, but they were like.
Yeah.
Not sure.
Currently, yeah, it's okay right now.
Now I'm on 11th slide.
Yeah. Okay. Continue. Please continue.
I was on third slide from. Hello.
Now it's 11th. You may proceed.
Shall I start from starting, because I
No.
think
We are already getting late, so you must start from 11th slide where you left over.
Okay, ma'am. Either. So my FTI spectrum was also showing that the particles are formed successfully. After that, now my slide is moving or not?
Yeah, it's you are displaying 11th slide, which is of FTIR.
Yeah, now it is 12th slide.
No, still it's 11th.
No.
But I am on 12th slide.
You may conclude your work. Just come on the last slide, conclusion.
Okay, after that, I loaded my particles with the diuron, and I have checked the release studies in different GSH concentration and different pH medias. And the reduced form of particle was also utilized to capture the heavy metal ions. So we can say that our particle is showing the dual functionality because it is releasing the agrochemicals in controlled manner as well and capturing the heavy metal ions present in the soil. So it is capturing those ions and it is reducing the absorbance of these heavy metal ions by the plants. Hence it is a potential system that can be used to control delivery of agrochemicals. At last, I would like to conclude that my system is biocompatible, biodegradable, and dual responsive. We are using less agrochemicals, so we can reduce the adverse effect on environment. Apart from that, we can use such system for micronutrients in fungicides, insecticide delivery. At last, I would like to acknowledge my supervisor, Dr. Garima Agarwal, my research group, IIT Mandi AMRC for instrumentation facilities, MHRD serve for financial support, ICN 2022 for giving me this opportunity to present my work in front of everyone. Thank you.
Okay, so a nice presentation by Miss Ankita.
Thank you, ma'am.
I think your work will definitely help the students who are working in the field of agricultural.
Thank you.
And so, any question from audience side? I think there is no question. So, thank you, Ankita.
Thank you, ma'am.
The next speaker in the queue is Sri Lakshmi PS. Is she present?
Yes, ma'am. Yes, ma'am.
Okay. Sri Lakshmi PS. So, you are from Department of Physics, Maharaja College, Endakulam, Kerala.
Yes, ma'am.
And today's topic is study of structural and optical properties of green synthesized calcium oxide nanoparticles.
Yes, ma'am.
So you can start your presentation.
Thank you, ma'am.
Okay.
Ma'am, is my screen visible?